wonderful conference and the fine minds. Good conversation. So I have a lot to get through in this talk. I really have. I'm really going to be giving 3 talks in one. Uh, so some people here would be aware of work that I've been doing the last 35 years. I didn't want to give a talk where I'm reviewing the same old stuff. I wanted to talk about some new things I'm doing. But then for those who don't know about what I've been doing, I'll give some introduction background. So hopefully 15 minutes, 15 minutes, and 15 minutes, 3 talks. All right, talk number 1, introduction and background. Let's start with the 1927 Solvay conference, where de Broglie presented his pilot wave theory of a many-body system. And again, physicists, historians, let's please get at least the basic historical facts right. As someone pointed out on Friday, to get the history right is an ideal and perhaps unattainable, always gray areas, but please, at least the basic facts. Many physicists and historians have thought that de Broglie only had this simple one-body theory he had. Anyway, if you want to know what really happened at the 27 conference, had this book from 2009, which contains a complete translation from the French of the whole of the proceedings with detailed commentary, analysis. Hopefully, we at least got the basic facts right. So, what did de Broglie present at the conference? He presented this many-body pilot wave theory, where we have a pilot wave in configuration space that satisfies the Schrödinger equation, and there's an equation of motion for the trajectories. And so in configuration space, the motion of the configuration is determined by this pilot wave. This is a deterministic theory of motion. And if we consider an ensemble of systems with the same wave function and different initial configurations, you have an ensemble distribution. So I can consider how that evolves. If you assume an initial distribution given by the Born rule, so the initial points are distributed according to mod squared of psi, then this distribution is preserved in time by this dynamics, as I'll show in a moment. And in that case, you do recover quantum mechanics. Now, the Solvay conference, Broglie had some simple applications, a 2-slit experiment, some inelastic scattering, but the discussion of the full quantum theory of measurement had to wait until Bohm in 1952, who also extended it to the electromagnetic field. Let me just show you quickly how is it that this distribution is preserved in time. Let's see if we just get the logical structure right. So I'm finding it a bit weird standing here. So for one particle, just to illustrate, we have the Schrödinger equation. Remember, this psi is not a probability wave. It's just a wave that's guiding the particle. It's a property of an individual system. Schrödinger equation implies that the modulus squared, the amplitude squared of this wave satisfies this equation. Now, de Broglie postulates that each particle follows this velocity field. Okay, that's a postulate of the theory. Now, if I have an ensemble of such particles which have the same psi but different initial positions, how does the distribution of particles evolve? Well, if each particle follows this velocity, by construction, the density rho must evolve according to this continuity equation with that velocity field. And now we see, well, hang on, psi squared obeys exactly the same partial differential equation. So we have a simple theorem that if rho and psi squared are initially the same, they remain the same. Of course, this proof goes through for higher dimensional systems. You could have a field theory on a background space-time. The mathematics is all the same. You just have a higher dimensional configuration space. Now, the thing I want to focus on in this talk is the status of this Born rule. Okay, there's been a tendency, well, more than a tendency, most people would say in the last 70 years or maybe 60 years have said that, look, this theory, there are 3 postulates. There is this law of motion for psi, there's a law of motion for the particles, and there is this law. This is somehow supposed to be a 3rd postulate. I think that's wrong. There's a conceptual distinction between laws of motion and initial conditions. All right, if I drop a ball, the motion of the ball is determined approximately by Newton's laws, and Newton's laws is something that's just fixed. the initial position of the ball is a contingency. It didn't have to start here. It could have started somewhere else. Where the ball actually started is something, it's empirical. You go out and measure it. It's not a law. You don't try to justify it by some deep philosophical principle. So the key point is that pilot wave theory interpreted correctly. When I say interpreted correctly, I mean as I interpret it. Okay. The Born rule is not an axiom or law, but a state of statistical equilibrium analogous to classical thermal equilibrium. This goes way back, and many of the people here have heard me talk about this so many times, so I'm going to really rush through this to get on to some newer work that I've been doing. But let's just consider the example of the two-slit experiment, all right? I have a particle comes in at some unknown position. It follows a trajectory. It lands somewhere. Its motion is guided by the wave function according to this equation of motion. Now, I've just told you the theorem. If I have an ensemble of similar experiments where I have the same initial guiding wave coming in, but the initial position of the particle can vary from one end of the experiment to the other. If the initial distribution of particles coming in happens to be equal to psi squared, then by that simple theorem, the distribution later on at the backstop will be psi squared. And trivially, by construction, we explain the total interference pattern with each particle going through one hole. However, I could, in principle, according to this theory, at least as I see it, I could begin with a distribution of initial positions is different from psi squared, and then I will get something different at the backstop. So as an extreme case, if every particle started here, every particle would end up here, and I wouldn't see this pattern. I would just see a little, whoops, I would, oh my God, what did I do? I would just see a little blob here. Similarly, you may notice by symmetry, if all the particles started in the top half here, they would all end up in the top half here, and this part of the interference pattern would be missing. So what is the lesson from this simple example? The lesson is a general lesson that is true generally in pilot wave or de Broglie-Bohm theory, that quantum theory is a special case of a wider physics. Okay, what we see, if you're restricted to the Born rule, as Bohm showed in detail, in 1952, you get this empirically equivalent to quantum mechanics, but there is a larger physics outside of here that is perfectly allowed in pilot wave theory. But then there's an immediate question. Experimentally, we always see this distribution, psi squared. Why? This is an example of a 2D box, a single particle in a box where the wave function is a superposition of 16 modes. Why do we always see this distribution for an ensemble of similar systems? Some take it to be a postulate. I suggest no, that we can explain it by quantum relaxation. So if I begin with a distribution that's not psi squared, then with some conditions at least, it evolves towards equilibrium. So here is the time evolving psi squared. This is just comes from the Schrödinger equation. Here I have an initial distribution that is not psi squared, and I'm evolving each particle forward in time according to de Broglie's equation of motion, and with a little bit of coarse graining, as analogous to the coarse graining one does on phase space in classical theory, you get very quickly, this is a periodic system, over one time period, it gets very close to psi squared. Now, a little bit of details, what does it look like, what's going on in here? So a typical particle trajectory will look like this. It starts here, you can see it's quite erratic. They tend to explore the region. And that is what is going on. You can quantify relaxation with the coarse-grained H function, which is minus the relative entropy. The bars are coarse graining. Over bars, you divide configuration space into small cells. It's bounded from below. There's an H theorem analogous to the classical coarse graining H theorem, which I first learned about in Paul Davies' wonderful book, The Physics of Time Asymmetry. Anyway, so I proved an analog of that theorem, which of course doesn't tell you reach equilibrium. It just gives you a sense of what's going on and that you're starting to move in the right direction if there's no initial fine-grained structure here. In any case, detailed numerical simulations show that this coarse-grained H function tends to decay approximately exponentially in time. Here's an example for that same I was showing you in the 2D box. We're plotting log H against H bar against T. And there we are. So the idea is that we see psi squared in the lab today because something like this has taken place in the past. Okay, every system that we experiment with in the lab has a history. Sometime in the past, it will have already relaxed to the Born rule, and that's what we see now. So we have this special case of a wider physics. We're stuck in here because of past relaxation. Quantum theory is an effective description of this special state. Now, when did quantum relaxation happen? You know, I'm doing for, no, already. Did we start a bit late? Yes. Okay. All right. When did it happen? Presumably a long time ago in the very early universe. Okay, the particles we see in the lab weren't sitting there in a vacuum for billions of years. They have a complex past history, astrophysical, cosmological, stretching back to the Big Bang. Presumably, if this process happened, it will have happened soon after the Big Bang. So we might expect that quantum theory could break down close to the Big Bang. Now, this can be tested assuming inflationary cosmology to be broadly correct, which it may or may not be. I don't have strong feelings about that, but many cosmologists think it's the way to go. The temperature anisotropies in the cosmic microwave background are ultimately generated by early quantum noise, which is approximately given by, again, Paul Davies, the Bunch-Davies vacuum. So sorry about this. Sorry, Paul. There we are. Yes. So you have this scalar field, inflaton field. It is a vacuum state. If you use the Born rule to calculate the quantum fluctuations of that field, those fluctuations seed the density perturbations that later seed these anisotropies. So by looking at the statistics of these, you are in effect testing the Born rule in the early universe, assuming inflationary cosmology to be broadly true. Now, I've did a lot of work on this over the years. And I'm not going to go into details. I just said, well, are there signatures of quantum relaxation in the CMB? Those who are interested, I have a series of papers going way back. These two papers were actually funded. This one was with Samuel Kalau, was funded by Templeton. We did numerical simulations of quantum relaxation for a scalar field on expanding space. Long story short, for long wavelength modes, the relaxation tends to be suppressed. And so we predict, we predict a large-scale power deficit, also statistical anisotropy at long wavelengths. And this paper here is a very detailed analysis of the CMB data and other data, trying to fit to the predictions that we have here there was a sort of a power deficit function that goes as an inverse tangent of the wave number. I think it's fair to say that we predict the right kinds of anomalies. Anomalies have been reported. Large-scale power deficit, statistical anisotropy at very large wavelengths, but the data are sparse at large scales. There are no clear quantitative conclusions, and the anomalies are in any case controversial. If you pick a random experimental cosmologist dealing with this, some think that there's something going on. The fact that you have more than one kind of anomaly in the same region, for instance, the Planck team, many of them, they seem to think there's really something going on here. Other people think, look, the statistical significance is too weak. It's probably just a statistical fluctuation. It looks as if we're going to have to wait for the Lightbird satellite launch in 7 years' time for things to shift. There's new data coming in from certain telescopes, but they only look at part of the sky. So you can't get data relevant to very long wavelengths. So while we're waiting for that, let's do something else. So a few comments I want to make. We have philosophers in the audience. Please beware of Bohmian mechanics. There's a school of thought which is particularly influential among philosophers, not very much among physicists. Let's first again get basic historical facts right. This theory was first, Broglie has its priority. I tend to call it either pilot wave theory or de Broglie-Bohm theory, which seems fair enough. There's a paper very influential among philosophers arguing that the Born rule typicality for the whole universe implies Born rule probability for subsystems, and there seems to be an argument that you have to have the Born rule. That you know, this guy Valentini with his non-equilibrium is just wasting his time. I think the argument is circular. It's essentially circular. It assumes the Born rule for the universe. There's no reason why it might be true, it might not be true that the universe started off with the Born rule. I think it's an empirical question. For detailed critique of this school, I'd refer you to this paper. Not only on this point, a lot of other points about fermions, all kinds of things. I think there's a lot there that's just been done incorrectly. But if on this point of the status of the Born rule, I think that the simple point is this, that initial conditions are empirical. Okay, what was going on in the early universe? Well, we can constrain that, for example, from the CMB. I would say, you know, one-line summary, this is a question for experiment and not philosophy. Philosophy is very important, but I don't think you can realistically constrain initial conditions just on that basis. Anyway, moving on, sorry, the rush. Can't resist a quick advertisement. I have a popular book just published 2 months ago in which I expound on my views about de Broglie-Bohm, his history. There's a chapter on cosmology, black holes, everything's in there. 35 years of thinking, condensed in you know, and aimed at the general public. The key idea is really this, that I see the Born rule as a state of what I call quantum death. Okay, CF, the classical thermodynamic heat death that people worried about in the 19th century, where the whole universe reaches the same temperature and there's a universal background thermal noise at temperature T. I think an analog of that has already happened in our world. Okay, where there is a universal quantum noise that we see everywhere that I think has come about by a past process of relaxation. And as a result, just as in the state of classical heat death, if you could have observers in such a world, which of course you can't really, but just hypothetically, people living in a state of heat death, you know, there would be no sunshine, there would be no steam engines, there would be no life. And they might think, for example, that it's a law of physics that you cannot convert heat into work. Not true. If you have temperature differences, then you can convert heat into work. But if you're living in a world where there are no temperature differences, you might think that's a law of physics. Similarly, the main message of really the thing that's motivated my thinking for 35 years has been this idea that we're stuck in a very restricted state of quantum death, where you have universal quantum noise, the uncertainty principle, and effective locality. You just give a very brief indication of what happens, what is the new physics outside of here. For a start, you have superluminal signaling. So entangled systems, I change the Hamiltonian here. In this theory, the velocity over there responds instantaneously. If you average over a Born rule ensemble, then the marginal distribution here is local. We know with quantum mechanics, okay? But if you have a non-equilibrium ensemble, the marginal distribution here responds instantaneously to what you do over there, and you could signal instantaneously at the statistical level. And so, of course, you have to revise relativity. That means when you do field theory in de Broglie-Bohm, you write down the theory in a preferred reference frame. If space-time is curved, if it's a globally hyperbolic space-time, you assume that there is a preferred foliation, and the dynamics is written down with respect to that. So the world is fundamentally non-local. And the only reason we can't use that non-locality for practical superluminal signaling is because we're stuck in this state. Similarly, the uncertainty principle, very briefly, if I couple a system to a pointer, if the pointer obeys the Born rule, then in order to get information about the system, you make the wave function separate, in the total wave function separate, and you can't see the actual trajectory. You can just see which branch you end up in. However, if I have a pointer, this is the wave function of the pointer, and the actual probability distribution of the pointer is very narrow, very narrow. I can couple the pointer very weakly to the system, so the wave function hardly changes. the wave function of the pointer barely shifts, but because the distribution is so narrow, it shifts enough for you to notice and measure the position of the particle without significantly disturbing the wave function. So out of equilibrium, you can observe, you can track trajectories inside the wave function, and that means you can eavesdrop on quantum key distribution and so on and so forth. So there's a whole new physics outside of here that we don't see because we are trapped in this region. All right, now some recent references. So I'm going way too slow, but that's the end of the first talk. Some recent references, those who maybe not aware of my work. This is quite a mathematical treatment, also quite a bit about high energy physics, field theory, and so on. But that's a sort of recent summary of the state of the art, at least as I see it. Here, there's a sort of summary. It was for Shift for De Broglie, Centenary, about search for new physics, and some of the things I'll be talking about now. For a more philosophical, historical summary of my views, there's this um, article recently published. All right, so okay, so now the second talk. We're trapped in quantum equilibrium. I'm claiming that we're stuck in here because of a process of past relaxation. I spent years looking for evidence of past relaxation in the CMB in the early universe. We've talked about that. There's some tantalizing hints, but nothing definite. What are we going to do? We're going to wait for the Lightbird satellite in 7 years. Let's think about now, okay, let's assume we are stuck in here. In principle, there's new physics outside of it. Is there a way to escape? Okay, in the lab. Can I go in the lab and somehow get out of this state? Can we create non-equilibrium from initial equilibrium? So, I go in the lab, maybe if I hit things very hard, can I knock things out of equilibrium? Now, apparently not. In pilot wave theory, as we usually have and as I've presented it, this distribution is preserved by the dynamics. Okay, once you're there, you're stuck there. And you might, I remember at the beginning, I was looking at all kinds of clever tricks. Well, what if we look at this particle, and we correlate where? Can we somehow get out of this state? Apparently not, at least in non-gravitational physics. If I have pilot wave theory just on a fixed space-time background, it seems that you are stuck there. But now, here's an idea that maybe quantum gravity changes the game. And this is something I've been doing the last 4 years or so. So, my word. Okay, second talk. Beyond the Born rule in quantum gravity, there are 3 ideas really I want to get across. So I think that for time reasons, I'm going to have to skip through some of the technical slides. But really, there are just 3 ideas that I hope can come through. Is number one, that in my view, if you look at canonical quantum gravity with the Wheeler-Dewitt equation from a de Broglie point of view, then the right conclusion to draw is there is no such thing as the Born rule at the fundamental level. There is no Born rule. There can be no Born rule. The Born rule emerges only in the semi-classical regime. What do I mean by that? When space, so of course, remember in quantum gravity here, we are quantizing space-time as well, not just the fields or particles, we're quantizing space-time. In the semi-classical regime, we have an approximately classical space-time background and quantum fields and particles propagating on it. Then you can get quantum relaxation and you end up with the Born rule that we see. Third idea is that quantum gravity corrections to the semi-classical limit can make the Born rule unstable. And the original Born rule state can evolve into a non-Born rule state. Goes without saying these effects are very tiny, but I'll show you. So just to put a bit of flesh on these ideas, when I say there's no such thing as a Born rule, so the Wheeler-Dewitt equation is a time-independent equation for the wave functional psi. And I'm saying that, look, mod psi squared is not a probability. The Born rule emerges only in the regime where you have an effective time-dependent Schrödinger equation, for example, for a scalar field on a classical background. Then psi squared can be a probability. Psi is an effective wave function for the field. Then after relaxation, this can be a probability. Small corrections can make rho is psi squared evolve to rho not equal to psi squared. All right, so all right, let's run through. First of all, Why is there no such thing as a Born rule in quantum gravity? The Wheeler-DeWitt equation, the essential point is that the solutions of the Wheeler-DeWitt equation, which looks like this, here Gij is the 3 metric, R is the curvature. Don't worry too much about the details. The point is that the solutions are non-normalizable. Here, for simplicity, there will be other terms here. If I have matter fields, there will be other terms here, the Hamiltonian density. I've just written down the gravitational part just to keep it short and simple. But the solutions are non-normalizable, and this is well known. And the essential, there's a mathematical reason. The Wheeler-DeWitt equation is mathematically like the Klein-Gordon equation. There's a mathematical correspondence. This is, remember, there's no time here. There's no time. This is just a functional differential equation on the configuration space of the metric. Here's you've got the Klein-Gordon equation on Minkowski spacetime, but they're mathematically similar. And if you try to normalize a solution here, it's like normalizing a solution of the Klein-Gordon equation over the whole of spacetime. This is very well known. This study of good data, for example, like Kukash back in the 90s, it's all very well known, all right, that it's not normalizable, and this is what's going on mathematically. Now, a common explanation, and here I've put in a matter field, the common explanation is that the reason this is naive as a probability is because time is somehow hidden in the 3 metric. For example, maybe I could treat the scale factor in an expanding universe as time. It's still controversial. Do we really recover standard quantum mechanics? What happens to time if the universe expands and then recontracts? Does time stop and then reverse? You do get issues. Some people think that, look, there's nothing wrong with this. Time as we know it emerges only in certain conditions. Others, such as myself, think that there's something wrong here. The explanation I'd like to give is that the reason this probability is because there's just no such thing as the Born rule. You're making a mistake, assuming that psi squared will give you a probability, or it is even possible as a probability. We can talk about probabilities, certainly in a de Broglie-Bohm approach, but they're not tied to the Born rule. In fact, physical probabilities must, by construction, be normalizable. This is not normalizable, so they can never be equal. So the claim is in the deep quantum gravity regime, you're in a perpetual state of non-equilibrium. And I think this is the true significance of this non-normalizability. So just quickly looking at the pilot wave theory of quantum gravity, which has been written down by a number of people, Pinto Neto in Brazil applied this extensively to quantum cosmology, bouncing models, and so on. Again, I've left off matter terms here, but just for the pure gravitational, okay, you have the Wheeler-DeWitt equation. This is your de Broglie guidance equation. This is the analog of momentum equals gradient of phase. This is just saying that the canonical momentum is the phase gradient. This is a phase gradient with respect to the metric. And this is the standard classical. If you look at classical Hamiltonian general relativity, if you look at the relationship between G dot and the canonical momentum, it looks like this. And if you replace the canonical momentum with a phase gradient, this is your de Broglie guidance equation. Now, I claim that, well, an arbitrary ensemble with distribution P will evolve by the continuity equation in the configuration space, which is just an infinite dimensional analog of this continuity equation for one particle. It's just saying that each metric evolves according to that equation of motion. Okay. Now, my claim is that this theory has no equilibrium state. And you can illustrate this with a model of quantum cosmology. We have an expanding universe, scale factor A, and a homogeneous matter field. If you find this Wheeler-DeWitt equation, you might be interested to know that if I change variables here, if I replace A by a new variable alpha that is equal to log A, then this becomes the Klein-Gordon equation with a potential term, and that's where the non-normalizability comes from. But anyway, in this model, in a Broglie-Bohm version of this model, if you do the usual polar decomposition, you get what I call a pseudo-continuity equation. The actual equivariant density, instead of being psi squared in this model, it's actually A squared psi squared. Just a peculiarity of this configuration space. I could remove it by redefining the volume element. But anyway, you've got this non-normalizable density. The de Broglie velocities, again, come from canonical momentum as phase gradient. It looks like this. I've got a de Broglie-Bohm theory of this model, Now, what I claim is that once you've written down this theory, a general probability density should evolve according to this. This is just telling you that each element of the ensemble evolves with these velocities. And now the question is, well, will P now evolve towards psi a squared psi squared? Of course it can't, because by construction, this is normalizable and this is not. So inevitably, you can never reach equilibrium. Formally, the coarse-grained H function, it has no lower bound, and equilibrium can never be reached. Now, you might think there was an idea that was suggested by a former student of mine, Indrajit Sen, saying that, well, maybe even for non-normalizable wave functions, maybe quantum relaxation occurs locally. Maybe in some region things still relax. It's a reasonable idea. I don't think it works. I've done numerical simulations with another former student, Aditya Kandhadai, for this system. Essentially, those familiar with these things, the kind of examples that have been studied numerically, the time-dependent wave functions, the nodes of the wave function play an important role in driving relaxation, and they move around. The points where psi vanishes, the velocity field tends to rotate around the nodes, and as the nodes move around, you get this sort of stirring and mixing, and that drives relaxation. For this system, it seems to be dynamically just very different. Because the wave function is static, the nodes are static, and the results that we have numerically, you don't get relaxation, not even locally. Things just seem to get trapped, and it doesn't explore the region. So the implications is that you get no relaxation in the deep quantum gravity regime. You can get relaxation only in the semi-classical regime, where you have an effective time-dependent Schrödinger equation for a quantum system on a classical background. How does that come about? Those of you who are familiar, the semi-classical approximation, you have a solution of the Wheeler-DeWitt equation, which you have an approximate WKB solution for this classical background. This is standard stuff in quantum gravity. You might look at a paper, Kiefer and Singh, 1991, and you have this, remember, there's no time here. You have a wave function for your quantum field psi and Gij. If Gij is approximately classical, I can define an effective time-dependent wave function. These are the approximately classical trajectories for Gij. Whoops. Oh. Okay, and you can define an effective time-dependent Schrödinger equation with an effective Hamiltonian with a normalizable psi squared. And once you have that, then the usual discussion of quantum relaxation becomes relevant, and you expect to find conventional quantum relaxation. So the idea is that at the very beginning, in the deep quantum gravity regime, there is no equilibrium state. As the universe expands and cools, and that will of course happen very quickly, as soon as you emerge from the Planck scale and you're in the semi-classical regime with an approximately classical space-time background, then you will get relaxation, and there you are. So you still explain what we see, okay? Even though fundamentally in quantum gravity there's no Born rule, you still explain why we see the Born rule today. Now, but then you might think, well, what I thought we were going to try and find a way of getting out of this quantum death. You're telling us that we still end up in quantum equilibrium anyway. But now, if we go a bit further, small quantum gravitational corrections to the Schrödinger equation, derived by, again, Kiefer and Singh in 1991. And some of the terms are non-Hermitian, which of course is a problem in standard quantum mechanics, but not a problem in pilot wave theory. Let me be very quick here. And Kiefer and Singh, PhysRev 1991. Again, standard stuff in the field. Those who perform a semi-classical expansion in powers of a parameter here, which these days, in later papers, they take the parameter to be square of the Planck mass. For some reason, they did it with different parameters, slightly odd. But anyway, it's the same thing. They find a corrected Schrödinger. So here you're finding the effective Schrödinger equation for a scalar field on the classical background with quantum gravitational corrections. This is the standard Hamiltonian for a free scalar field on the classical background. These are the corrections. Okay, the first correction is Hermitian, and it's basically the square of the field Hamiltonian with the suppressed by a Planck mass. This term is non-Hermitian. Note the factor of I here. and it depends on the fact that this background is time dependent. Sorry, did someone say something? Okay. Okay, so there are Hermitian and non-Hermitian terms. Now, how can we deal with that in pilot? So I should say that there's a long series of papers by Kiefer and collaborators where they've also derived similar terms in quantum cosmological models. And they have calculated, for example, what is the effect of the Hermitian term on the CMB. The effects are extremely small. We can't really measure them, but they're there in principle. And you ask, well, what do they do with the non-Hermitian terms? The answer is they just drop them and ignore them. Some have tried, there's some papers where they try to argue that we need to redefine the wave function in a way to get rid of these terms. Some people think that if we do the semi-classical, that there may be a way of not having these terms. So I think it would be a fair view to say, well, maybe these are just artifacts. But maybe they're not. Maybe these redefinitions and so on are ways of sweeping under the rug something that is real. And the only reason you're sweeping under the rug is because in standard quantum mechanics, you don't know what to do with it. Whereas in pilot wave theory, it's very simple. Just generally, I have an effective Schrödinger equation with a Hermitian and a non-Hermitian term. So H2 is Hermitian, but I've got a factor I. If you look at this, I get all these details, but going back to the Wheeler-DeWitt equation and the guidance equation for the Wheeler-DeWitt wave functional, if you look at that in the semi-classical limit, you find that the guidance equation, the effective guidance equation for the scalar field comes out to be just the usual one associated with the uncorrected Hamiltonian. So you recover the usual guidance equation for the field in the semi-classical limit. And so the continuity equation for the density will just have the usual velocity field. But because of this non-Hermitian term, the continuity equation for psi squared now has a source term. I remember why did that now has a source term, and so these two continuity equations no longer match. So that theorem we had way back at the beginning, rho and psi squared obey the same partial differential equation. If rho is psi squared initially, rho remains psi squared. That breaks down because of this term. An initial equilibrium can evolve to non-equilibrium. And I have an estimate for the time scale, which goes like this. All right, now. Could such effects be observed? Well, it seems to me that I've looked at a number of things, CMB, various things, if you look at my papers, but the thing that looks most promising is evaporating black holes. There was an estimate given in this paper in the 90s. If I have, let's say I have a Schwarzschild black hole of mass m, it's evaporating. So the mass m is decreasing with time. And in the space-time around the black hole, I have a scalar field, just a free scalar field, and I'm looking at a mode of the scalar field, and it has a Hamilton. There's a standard Hamiltonian for that mode of the scalar field. There is a non-Hermitian correction to that Hamiltonian coming from quantum gravity that looks like this. Here we've got the Planck mass. This is the mass of the black hole at time t. There's a factor of order 1. They were arguing that maybe this has something to do with information loss, but of course it's a bit tricky because you can't really deal consistently with a non-Hermitian Hamiltonian in standard quantum mechanics. Anyway, here we're saying that, well, what this term is really going to do, it's going to create non-equilibrium. It's going to drive the scalar field away from the Born rule. But if you look at the time scale, it's a Planck time, mass of the black hole, Planck mass. It only becomes significant when the mass goes down close to the Planck mass. So it's only going to be the final burst that you might see something. In principle, it is thought by many that there is a population of primordial black holes in the universe left over from very early times, and some of them should be exploding around now if they have a mass of about 10 to the 15 grams. And people do look for there are satellites looking for gamma rays, X-rays, into telltale signatures. In principle, the idea is that, well, an incoming gamma ray, let's do a 2-slit experiment. Could we see a deviation from the Born rule? Interestingly enough, there was a German satellite mission recently launched, which has an interferometer on board designed to test the Born rule in space. And they do cite my paper, as well as 1 or 2 other papers, as motivation. They're not doing this. What they have, it's a small satellite. They call it a micro satellite. Anyway, it's the size of a shoebox. It has an onboard optical photon source, and it has an interferometer that is designed to test the Born rule. And another motivation is from sort of Raphael Sorkin's ideas about possible violation of the Born rule. Anyway, and the idea is to test the Born rule in space. Apparently, they're going to have results published imminently by the end of this year, they say. Anyway, once such a thing is up and running, if tomorrow, if, for instance, I don't know, one of the X-ray, gamma ray satellites detects radiation from exploding primordial black hole, which could happen tomorrow. There is actually a galactic excess of gamma rays coming from the center of the galaxy, which some people think might be from annihilating dark matter. A bit controversial. Anyway, then, well, let's take their interferometer, and instead of having photons from the onboard source, let the photon come from the distant source. And anyway, so it's not something that we're going to do tomorrow morning, but perhaps in the not so distant future, this could be done. All right. Concluding from this conclusion of the second talk, quantum gravity is fundamentally a non-equilibrium theory. There's no Born rule, and that's the significance of the non-normalizability of the state. We find the relaxation, the Born rule, only in the semi-classical regime. There are corrections to that regime that yield a small instability. The effects are very small, possibly observable one day. All right. Now, coming to my third talk. So how much time do I have? I wanted to have at least 10 minutes for questions, but I have 5 minutes. All right. All right. Let me go quick again. Okay. I said, is there a way to escape? And there's been this idea, well, maybe quantum gravity can help us. It turns out the effects are very tiny. I may have to wait until we spot evaporating, exploding primordial black hole. Isn't there something we can do in the lab? Do something in the lab. Again, let's now forget about gravity. Let's say we're in the lab, and again, there's this problem that P is psi squared is preserved by the dynamics. Well, that is true, at least in the usual pilot wave theory. If I start with, do you want to come in there? Okay. Yeah. Okay. If I start with psi squared, I seem to be stuck there. However, perhaps the dynamics of pilot wave theory are not exactly correct as written down by de Broglie. So here's the third talk, Beyond the Born Rule in High Energy Physics. These two papers I've already mentioned. I'm working with Mira Varma, who is a graduate student in Yale. There is a field that is become surprisingly very active the last few years. A lot of people in experimental high energy physics are looking at data and using it to test the foundations of quantum mechanics. I think it's Alan Barr here somewhere. Alan, there you go. Alan is one of the movers and shakers here in Oxford. A lot of interest in this in the US. Anyway, I'm going to give just a very quick sense of what's in this paper and this paper. So here's the idea. I claim that I think it's just a clear fact. Pilot wave dynamics predicts its own demise when psi vanishes. Okay, for standard Hamiltonians, we have a velocity proportional to the phase gradient. This generally diverges when psi is 0. Now, the nodes of psi measure 0. And for this reason, they're usually ignored. It's a little bit like in the classical Newtonian gravity of point particles. If the particles actually sit on top of each other, then the force diverges and there's a problem. But it's well known, Newtonian dynamics of point particles, there are theorems about, there's a set of initial points of initial conditions of measure 0, where you'll find that as you evolve, the particles actually hit each other. Okay, so in practice, you can ignore this, but I claim that, well, they are there. And so new physics must set in close to these points. Nature presumably doesn't, nature abhors a singularity. You might also think of classical gravitational singularities also in general relativity. There's a difference. In general relativity, matter tends to be sucked in and towards and absorbed into singularities. Here, because of the mathematical structure, when I have a node, the de Broglie velocity field, it tends to circulate around the node. It's not sucked in. And of course, because the usual probability vanishes at the node, you're very unlikely to be there in equilibrium. But nevertheless, you can be arbitrarily close to a node. And so there will exist arbitrarily high velocities. simple example, for instance, the hydrogen atom has a stationary state. There is a nodal line all along the z-axis. The de Broglie trajectories circle around, and the magnitude of the velocity actually diverges. This d is the distance between your distance from the z-axis. It diverges. All right. Now, you might think, surely that's just an artifact of the low energy theory. If I look at, for instance, the pilot wave theory of Dirac fermions, where I have the guidance equation is the Dirac equation, and you have this continuity equation, the de Broglie velocity is always finite. It is bounded by the speed of light. So you may think, okay, so no problem. That's just an artifact of the low energy theory. Not true, because if you look at bosonic fields, high energy bosonic field. For instance, this is the pilot wave theory of a free scalar field on Minkowski spacetime. This is the functional Schrodinger equation. So this is your pilot wave in an infinite dimensional configuration space. You have the continuity equation. And here's the velocity field. The de Broglie velocity is a gradient, It's a functional gradient. It's still a gradient. And again, it diverges at nodes on the field configuration space. So there is a problem. Now, this problem, the only place I've seen this discussed, you're probably familiar, Bell had a paper, I think it's Quantum Mechanics for Cosmologists. There's a footnote in the paper which mentions this problem and proposes that he doesn't give any equations, but he just says, you can get rid of this problem. It's probably one of those things. This paper was presented at a conference. Someone asked, what happens at nodes? And probably afterwards he's added this little footnote. But anyway, it's a very good footnote. He says, look, if I smear quantum current and psi squared this is a very narrow function. Think of it as a very narrow Gaussian on configuration space, narrow and positive. I can define a regularized de Broglie velocity, which is ratio, and it's easy to show now that you have a new equilibrium state that is just this smeared psi squared. All right. So now I looked at this a bit. If you just a simple theorem here, general functional configuration. If I smear it, this is a very narrow function of width a. In small, this smeared function is just the original function. The correction is proportional to the local Laplacian. If you apply this, for instance, in 1D, psi squared will be corrected by this term. So nodes, points where psi literally vanishes, are replaced by minima. Now you get this kind of thing in field theory. Here, I have a single mode of a scalar field, and these are the real and imaginary parts of the Fourier component. The de Broglie-Bohm theory, these are the velocities. They can diverge at points where psi vanishes. So this is, I think, a genuine problem in the high energy field theory. Now, if you have this kind of smearing, this regularized, as I call it, de Broglie-Bohm theory, you might expect to see a smearing of cross sections at small scales in high energy scattering. This is something a work in progress. But let me just rush and tell you about something more interesting. Is that I've considered what I call an extended regularized theory. If we let this smearing function be time dependent, okay, the idea is there's some new physics at nodes, which of course we don't really know what it is. If it's there, perhaps in short timescale processes, let's just model it. This is sort of crudely trying to model and give a crude phenomenological model of some physics that we don't know what that physics is. But if this be time dependent, then the smeared psi squared now satisfies a continuity equation with a source. And it no longer matches the continuity equation for rho. And again, you get this thing that an initial Born rule, but a smeared Born rule, can evolve into a non-equilibrium. You're different from the smeared Born rule. So you could create non-equilibrium at short time scales. Now, here's a question. Could we see this? Could we test this in high energy physics for collisions over very short time scales? The sort of thing you'd expect to see. If here's your collision, have photons coming out. If I pass it through a polarizer and a second polarizer angle theta, the probability of transmission could deviate from the Born rule. This Malus law is a prediction of quantum mechanics, comes from the Born rule. And there's an argument to do with additivity of expectation values that I can't go into here, but this is actually a nice general signature of non-equilibrium. Now, here to test this, it would be a good idea. Let's focus on photons that are created at the shortest accessible timescales. Now, The shortest timescales currently accessible at colliders are of order 10 to the minus 25 seconds. And one very interesting case is top quark decay. This has actually been, there's a paper, when was this, 2 years ago, observation of single top quark production in association with a photon. This is proton-proton collisions. There's a mess of stuff going on with gluons on the bottom quark. Here's the top quark that is so massive, it decays very quickly. And before it decays, it emits a photon, and they're actually able to identify events where you have a top quark decay, and they can identify these photons. The top quark is decaying on a time scale of order 10 to the minus 25 seconds. So this photon that's produced is arguably sensitive to physics on this very short time scale, and they've detected nearly 6,000 of these photons. Okay, the idea is they would be good photons to do this experiment with. How are we going to model the possible deviations from the Born rule? Seeing as this is a two-state system, in effect, that we're looking at, we don't need to bother with all the complexities of de Broglie-Bohm theory. We can look at, just as a way of parameterizing non-equilibrium, we can look at the Bell hidden variable model of a general two-state system. Here's your quantum state, the mean polarization vector. Here's the measurement axis along with this is the Bloch sphere. If you're measuring, say, the spin along this axis, there's a hidden unit vector. This is the hidden lambda, which is usually assumed to be uniformly distributed on the sphere. And there's this rule that if this thing is positive, then you get +1 in the measurement. If it's negative, you get -1. So this area, if lambda is in this area here, when you measure the spin along the axis M, you get -1. Now, as Bell showed, if you know, assuming this distribution, then expectation values match the Born rule. If you have the whole concept of equilibrium and non-equilibrium is not just for de Broglie-Bohm. It's similar in any deterministic hidden variables theory. You have the same point. If I have a mapping from hidden variables to outcomes, if I have a distribution that recovers probabilities of quantum mechanics, well, if I change that distribution, then I get different probabilities. Here you can get nonlinear expectation values, and for photons, you get a correction. For example, it's just an example of the sort of thing that can happen. Instead of having just the usual cos squared theta, you can have cos cubed 2 theta, where this is presumably an extremely tiny parameter, if it exists. And I've been working with Mira Varma on trying to constrain this. How could this be constrained from data? This is where we stand. So this is my, oh, that's my last slide again. Top quark decay, we would need to measure, these are gamma ray photons. It's not yet feasible to measure their polarization for single gamma ray photons. So this would be an experiment for the future. But we've also looked at experiments with the probe the average polarization of tau leptons from Z boson decays. The CMS collaboration has studied this and compared the standard model. So here we'd be looking at just the average. You're not looking at a probability distribution, you're just probing the average energy, the helicity, but anyway, the polarization of tau leptons, and this has been compared with the standard model prediction. So from this data, we can already put some crude constraints on possible correction to the average polarization. Please see our paper for details. Conclusions from the third talk is that the Born rule should be tested in high energy collisions, in particular very short times. You can repurpose collision data to test the Born rule and put new constraints on the validity of quantum theory at high energies in very short times, which is worth doing anyway, even independent of all of these motivations. Overall, very last slide, overall conclusions. Pilot wave theory is historically one of the original formulations of quantum mechanics. Historians, physicists, the basic historical facts, right? All right, this is not some afterthought tacked on in 1952, as many people try to claim. I mean, Bohm, of course, did very good, important work, but the theory was there already in 1927. At least the way I interpret it, quantum theory is a special case of something broader and deeper. We should be looking for that new physics. Possibly it existed in the early universe. I've sketched a little bit of work I did on that years ago, funded by Templeton. Now, New work. Well, I think this spider wave theory can also answer some key puzzles in quantum gravity. It predicts a small instability of the Born rule in the semi-classical regime, at least if you take those non-Hermitian corrections at face value. Finally, regularization of the theory node suggests a smearing of the Born rule at short distances and a possible instability at very short times, motivates testing the Born rule at high energy colliders. And I think that's it. Thank you so much. Thank you.
Thank you for the 3 excellent talks. Let's start with Tim Palmer. Tim first, yeah.
I just want to go right back to the very beginning of the first talk, and in relation to perhaps the second bullet here. No, don't bother.
Oh, okay.
You said early on that you, to get the Born rule, you'd done some coarse graining over some configuration space. My question is whether there is any interesting physics in the fine scale structure that you've coarse grained over.
Yeah.
And in particular, I'm thinking about simple examples in chaos theory. You can certainly average over flaps and butterflies effects to get probabilities. But if you do that, you miss out on some very, very deep and important geometric structure that exists in those differential equations. And in coming to something which is broader than quantum mechanics, maybe there's something interesting in that in that structure you're not exploring.
So very good question. I mean, I can tell you in that paper, Proceedings Royal Society 2009 with Hans Westman, those simulations with a 2D box. So what you're doing is the configuration space of the box, you're dividing it into very small coarse graining cells, very small, and you're averaging over those. Okay. Now, what happens inside the cells is very interesting. If you look at the density row, if you look at the fine-grained structure at short distances, it's incredibly spiky. And we have in that paper we homed in on a small region. I think it was 0.01% of the area, something like that. And we plotted the exact fine-grained density. And it goes like this. The spike in it is extraordinary. Now you might, there's a question. Well, could it be that if we home in on short enough lengths, would we see something?
There must be, because you've got deterministic equations. You're starting presumably with some simple initial. So there must be some deterministic structure there.
No, in principle, yes. No, definitely, I agree completely. The question is, in practice, how small are these scales likely to be? Because here we're just evolving over one period of a simple quantum system, and already it is very fine, very, very tiny. Now, if you're thinking realistically about particles that have been knocking around for billions of years, I once tried to look at this and think, is this? But my guess is that it would be at hopelessly small scales, and that you wouldn't see anything. But I might be wrong. Good point. Thank you.
Jim, next.
Thank you. A very basic question referring to your second talk. You mentioned a possible test of violations of the Born rule from gamma rays from primordial black holes.
Yes.
What is it about the gamma ray that enters the two-slit setup that tells us it's come from the early universe when Born rule didn't hold?
Sorry, do you mean how do you know? Well, so the idea is that so, for instance, if there is a population of primordial black holes in our galaxy, and there are prominent theories like Bernard Carr, for instance, who think that they're probably a significant component of dark matter. I mean, they're almost certainly there. How many there are, you're not sure. But now, if they're exploding now, then you know that their mass must be about 10 to the 15 grams. So you know where the spectrum is peaked. And I think, is it 100 GeV? I don't remember off the top of my head, but you expect to see gamma rays. So there are astrophysical issues. How do I know whether this gamma ray is really coming from an exploding primordial black hole and not something else? You need to have some good model of what's going on there. But what I'm saying is, if the astrophysicists agree, We have discovered primordial black holes, and these things are being searched for. For instance, the Fermi satellite has been searching for these things, and there is a gamma ray excess, famously, from the center of our galaxy, which is controversial. Some astrophysicists think it's just some process that, some messy thing going on in there. Others think that it's probably massive WIMPs, weakly matter particles that are annihilating. But
my point isn't whether or not there are primordial black holes, but it's that photon that enters the two slits. What is it about it? What is it about its nature that's different? That means you're going to violate.
I see. Okay, so the nature that's different. All right. So what it is, it would be, in the case of a photon, it would be. Remember, of course, the whole idea of a breakdown of the Born rule requires you to have an ensemble. So it's not just going to be one photon. You need to be a repeat. So the real question is, what is it that's different about that ensemble of photons coming in? And the point would be the distribution of initial conditions. Now, if it was a de Broglie theory with photon trajectories, which some people try to do, and I don't think really works, but anyway, then it would be the initial positions of the photons would be different. What I think is proper way to do it is a field theory. There is a field configuration that evolves, and it will be the probability distribution over the fields associated with these photon states that will be anomalous. So that's the difference. It's the difference in the initial conditions. So remember, if these photons have been produced by the exploding primordial black hole, remember I talked about there's a non-Hermitian correction to the Hamiltonian of the scalar field in the vicinity of the hole that will push the probability distribution for the field configurations away from the Born rule. So it's the probability distribution for the field configurations associated with those photonic excitations that would be different. That would be it.
Let's take a quick one from John T, and that'll be all we have time for today.
Thank you, Anthony. Very, very nice talk. Given we've already heard a little bit about the first talk and the second talk, my question is about the third talk, specifically the experiment you gave at the end on photon polarization.
Yes.
I was just wondering, I mean, it kind of links a little bit to Jim's question. If you're expecting to see a kind of a smearing around the Born rule, insofar as you're kind of effectively in these from these photons that are coming through, isn't there a risk that any kind of signal of non-equilibrium behavior could be kind of almost sort of swamped out by that? You might need to look more sophisticated kind of assessments of probabilities than the one that you gave on the slide, or am I missing something a little bit?
Well, sorry, so it sounds as if you're saying that I mean, the smearing, it was more, I think it's more to do with cross sections. The polarization, because it's a two-state system, you're getting plus ones and minus ones, and there's a distribution. I'm not quite sure that's irrelevant. But the point about the smearing, something that is a sort of work in progress, again, I'm doing with Mira Varma, is the idea that it's not so much about the instability, it's more about, let's say there's a small smearing at short length scales. And, we've been looking at how can we look at current data on cross sections to sort of put constraints on the smearing. And it turns out, I mean, great intuition. Are you an experimentalist by trade sometime? Anyway, it's a very good intuition, because it turns out that I didn't know this, and then we discovered this really looking at in detail at the way the data is produced. Is there are, let me see if I can get this right. For instance, if you have an energy detector or something, there's a small error in, there's an experimental resolution in the energy, okay? And the people who actually run these experiments at the LHC and so on, what they do is they model this resolution with a Gaussian smearing, and Alan's nodding his head, he knows all about it. They model it with a Gaussian smearing. So in other words, they have already smeared a thing. And there's a question, well, hang on a second, how are we going to distinguish our smearing from something that's already smeared? And that's why I put work in progress. We're still trying to figure this out, but very good point.
Yeah. We'll be back at 11:30 for David Wallace's talk, and now we have a coffee break. So thanks again to Anson.
Thank you. All right.
Okay, welcome back everyone for the next session. So now we have a talk from David Wallace. So please go ahead, please.
Thank you. So the quantum measurement problem's been in quantum mechanics pretty much as long as quantum mechanics itself has been. And pretty much ever since it's been in quantum mechanics, it's had a lot of skepticism coming from various bits of the physics community as to whether the whole thing is a kind of waste of time. And part of what I want to do today is sort of give an apologia for the measurement problem. But I want to sort of start by kind of sketching what I take to be the rationale that leads a fair amount of the physics community, I think somewhat understandably, to think that the measurement problem is not something for serious scientific activity. Maybe you do it in the bar after you've finished calculating, but it's not the thing you do in the day. And I think the sort of sketch of how the measurement problem's thought about that leads you in this direction, and which I think you do see in a non-caricatured form in a lot of the philosophy literature, looks something like this. We've got the formalism of quantum mechanics, which is common, which is agreed on. Then we've got interpretations of the formalism, and the word interpretation has some movable feast, but at least you've got the Copenhagen interpretation, you've got the Everett interpretation, you've got cubist interpretations, slightly fuzzier if you want to say pilot wave theories are interpretations. It's not that you're stretching the word to the screaming point when you get to collapse theories, but the basic idea is you've got this family of interpretive choices all sitting on a shared core formalism. Almost all these interpretations are supposed to be empirically equivalent or empirically equivalent in most circumstances, and they share that underlying formalism. And then philosophers and physicists have a different kind of attitude to that. I think the philosopher route goes something like, this is underdetermination of theory by evidence. We're off. This is something we know how to think about. What we need to be looking for is what are the extra empirical virtues and vices that allow us to choose between these empirically equivalent, but nonetheless conceptually, philosophically distinct ideas. So you get ideas like, let's look at probability. We can't justify interpreting the mod squared amplitudes in quantum mechanics as Everettian probabilities. Yes, we can. Actually, in the Everett interpretation, we understand probability better than we ever did in the non-Everettian context. Or maybe we're going to talk about the theory having redundant bits. The Bohm particles are epiphenomenal. They just add something to the theory that does no work. No, they're the whole thing that phenomena supervene on. Everything, it's the wave function that's invisible. The particles are exactly the things that we see. Or we can say, many worlds is a wildly extravagant ontology. No, many worlds is much simpler, and Occam's razor isn't about the amount of stuff, it's about simplicity. Or maybe it's unitarity, it's inelegant, it's empirically unjustified to add a collapse rule for quantum mechanics. There's no evidence against unitarity. No, the whole presence of definite outcomes is our evidence against unitarity. Or maybe we look at realism. Physics should be about an observer-independent world. No, it shouldn't. And this is the kind of thing that you can spend your entire career as a philosopher doing. And I think that put it that way, you can see the force of the temptation for the working therapist to say, why am I bothering? If you can do all these things, it doesn't matter scientifically which of these you pick. Maybe they have various heuristic or pedagogical vices and virtues, but fundamentally it doesn't matter. Shut up and calculate. And a lot of what I want to do in this talk is say that I think that whole picture of the measurement problem is just wrong. It quite badly misdescribes the actual scientific situation we find ourselves in, and that the measurement problem addressed. And this isn't really a history talk, but I'll kind of wax a little historical about how I think aspects of the measurement problem have sort of changed across the time we thought about in understanding quantum mechanics. So here's a different sort of sketch as to how we think about, how we have thought about, and how we do think about quantum mechanics and its empirical content and its connection to experience. I'm going to describe slightly pejoratively the way maybe we thought about quantum mechanics for perhaps the first half of the 100 years of quantum mechanics as the way of confusion. And I'm going to suggest that the sort of renaissance in thinking about the content of quantum mechanics that happens sort of from the 80s onwards as suggesting three different successors to the way of confusion, which I'd call the way of modification, the way of the lab, and the way of decoherence. And as a spoiler alert, I'm ultimately going to advocate the way of decoherence. But I'm also going to claim that we've learned quite important things, scientific as well as philosophical things, from these various ways of thinking about quantum mechanics. So what do I mean by the way of confusion? Well, the kind of way you see quantum mechanics talked about at textbook level, not infrequently even in the published literature, for a large part of its early existence, involves a series of slightly inchoate appeals to a bunch of different vague ad hoc principles that conceptually are mostly in the business of linking classical mechanics and quantum mechanics. So, for instance, we have the obvious choice, the collapse of the wave function, but we also have the correspondence principle, we have the uncertainty principle, understood not just as a obviously correct formal statement about Fourier structure, but as a more conceptual claim, and often linked to some epistemic idea of the fact that we're empirically unable to make certain measurements, that we can't build devices of this kind. And of course, wave particle duality. And I think textbooks tend to drag some way behind the research frontier. I mean, even when I was an undergraduate in these very halls 30 years ago in the 1990s, then you go to the atomic and laser physics courses were still extensively appealing to correspondence principles, appealing to various sorts of quantum classical relations in a way that was fiddly to make sense of and quite unsystematic. And I think that has substantially broken down. I think it's true even that the teaching of quantum mechanics in the 2020s, then in these hallowed halls, and also in other lesser centers of the learning of physics. So you do a conference in Merton, I have to do a certain amount. Has moved much more to a sort of more principled way of thinking about and teaching quantum mechanics. But if we see what made the pressure on these various sort of somewhat ad hoc quantum classical transition ideas become intolerable, what I think we see is the breakdown of the ability to suppose that the quantum mechanical is subordinate to the classical, and that the conceptual structure of quantum mechanics can be inherited from classical mechanics. So here are some words that we see in contemporary physics: quark, gluon, fermion, laser, Bose-Einstein condensate, anomalous symmetry breaking, dimensional transmutation, superfluid. All of these are inherently quantum mechanical concepts. I mean, I could have put spin up there. This was I was talking to Simon about this. This was known to start to be a problem even back 100 years ago, but the pressure has become intolerable. All of those terms on the slide are things we have a perfectly clear conceptual grasp of in physics. But all of those grasps are quantum mechanical. Quark are not little points that move on trajectories. They're just not. The idea that the proton is a function of three of these little things held together by strong forces is something between, if you're generous, a sort of helpful metaphor that gets you off the ground when you're starting to learn chromodynamics. And if you're feeling less generous, it's a story we tell children. That doesn't mean that the quark is fundamentally mysterious. It means that our understanding of the quark is quantum mechanical. It comes from a quantum theory. It's not something we can get at or express or understand. So a picture of quantum mechanics that leans so extensively on the language of the classical has become less and less viable as physics has developed. And that shows up in particular when we start thinking about actual experimental gear. Now, if you actually want to build a measurement device of some sort. So, okay, somebody said earlier that theorists aren't allowed in the lab. I don't think philosophers are even allowed in the building of the lab. But I'm told that measurement devices are built. And increasingly, they're built themselves with quantum mechanical principles. So while it worked okay for Bohr to give inherently classical descriptions of the measurement apparatus, in modern physics, we need to give quantum mechanical descriptions of the measurement devices themselves. And in fact, we sometimes need to push at those quantum mechanical descriptions, even at the theoretical level, to answer what otherwise become paradoxes and puzzles if we too uncritically apply these various ad hoc way of confusion ways of doing quantum mechanics. So my favorite example of this is continuous measurement. So if you think about the Schrödinger cat experiment, it is cashed out in a Foundations of Physics or Philosophy of Physics text. Almost always what we have is something like a discrete measurement of spin, and then we kill the poor cat if the particle is spin up, and we don't kill it if it's spin down. Because that wasn't Schrödinger's original experiment. Schrödinger actually puts the cat in a box with a Geiger counter and a radioactive source, and waits until there's been a 50% chance, theoretically, of there being a single decay. What does that look like quantum mechanically? How do we think about that process? We've now got a situation where effectively the radioisotope is decaying. We have a perfectly good quantum theory of that. The Geiger counter is continuously monitoring that. How, if we're thinking in terms of ideas like collapse of wave function or something like that, do we think about that process? And the mathematics of decay, for instance, looks perfectly happily something like that. That's the quantum mechanical description of a decay process. I've got an undecayed state with an exponentially decreasing amplitude and a superposition of decay products exponentially weighted at all the various times it might occur. And that gives me a perfectly good probability of a decay. I can apply the Born rule to that perfectly happily. If I try to collapse the wave function, it's very unclear how I might end up doing it. I can discretize, but there's no intrinsically discrete structure in the Geiger counter setup. I can imagine that I should take the limit if I discretize and make the intervals smaller and smaller. If I do that, I just Zeno freeze the entire system and nothing happens. And it's worth thinking that the Zeno effect was being genuinely described when it was first presented in the mathematical physics literature as a paradox, because it was said by Ms. Darshan that that we should think about continuous observation as the limit of increasingly frequent observation, and it was then a theorem that in that situation, dynamical evolution was entirely frozen. I'll come back to the Zeno example in a moment, but it's there as an illustration that that's simply supposing one can treat the measurement process outside as undynamical can lead us into very substantial confusion. Okay, but we've learned things, we've moved on. There's a bunch of ways you can think about the measurement problem. I like ways of thinking about the measurement problem that foregrounds the fact that we're confused and therefore doesn't try to place a clean, unconfused statement of the situation front. A way of thinking about the measurement problem is that the way of confusion is indeed confused, and that we need to find more principled ways of using quantum mechanics, of understanding the application of the quantum formalism, to some extent understanding the formalism itself. And that leads me to the three ways I described in the setup. So let me start with the way of modification, which philosophers are particularly keen on. And the starting point of the way of modification is something like the problems of the ways of confusion are unfixable problems with extant quantum mechanics. They point to fundamental contradictions in the theory. The theory is unfixable. It's not that we're failing to understand the theory carefully enough, it's that the theory is broken. We've found a bunch of ad hoc ways to take this broken theory and get content out of it, but ultimately the task of trying to de-ad hoc those ways isn't going to work. We actually need a theory that doesn't have the sort of original sins of quantum mechanics. So this, of course, leads us to asking what is that theory, and this leads us to in particular, this leads us to the dynamical collapse and hidden variable approaches that we've had two lovely talks on today and yesterday. It leads us to retrocausal ideas, it leads us to modal ideas, it leads us to a plethora of ideas of how you might change the formalism. In each case, one way or another, it's leading us to new physics, or attempts to find new physics. And in the best of these approaches, it's leading us to new physics that is in principle possible compared to previous physics. I think it's a great virtue of both Wayne's presentation yesterday and Anthony's this morning, that they foreground the fact that we want these theories to disagree with quantum mechanics in the regime where we haven't tested them. But of course, the point of the motivation for the way of modification, I take it, is at some level, not simply that we want to do new physics for the hell of it, but that there has to be some replacement of the quantum formalism because of the sort of deep problems in that formalism. I mean, Wayne said that it was a virtue of dynamical collapse theories that they were work in progress. And fair enough, but of course, if I decided to replace classical electromagnetism with a new theory of charge, and I said I said it's a work in progress and I haven't got it yet, people wouldn't be terribly impressed. The point is that there's a prima facie reason to think there might be something wrong with the theory in quantum mechanics, such that that work has some reason to be accepted to progress. What are the problems for the way of modification? Well, a bunch of philosophical problems have come up. People worry about actions of distance, worry about relativistic covariance. Depending on your aesthetic taste and your degree of confidence that aesthetics is a good way to select scientific theories, then people worry about these things being inelegant or ad hoc. Theories have various ontological problems concerning tails. Some miscreants have argued that the de Broglie theory is ever in denial. But I want to focus on the scientific problems, which, if you like, are the flip side of the exciting aspect of these projects as developed by Wayne and Anthony. Here's one scientific problem. We don't have a hidden variable theory that adequately reproduces most of modern quantum mechanics. We don't have a dynamical collapse theory that adequately reproduces most of modern quantum mechanics. We don't have a retrocausal theory that to be honest, reproduces any of modern quantum mechanics, but a fortiori reproduces most of modern quantum mechanics. These are, as Wade put it, these are work in progress. These are projects underway. We have proofs of concept. We have demonstrations that in the regime of non-relativistic particle mechanics, then it's possible to build hidden variable theories, dynamical collapse theories that solve the measurement problem. That is, give us an applicable, third-person understandable perspective of the theory without running into the apparent paradoxes of quantum mechanics. But while there's been a lot of interesting work pushing and exploring what these things might look like in the domains that we normally describe by quantum field theory, then we don't have accepted check-through to multi-loop order calculation, interacting field theory descriptions. We may get them. There is a scientific project to obtain them. The project is vulnerable. We don't, at this point, have them. It's a matter of contention how difficult it is. I'm very pessimistic about this ultimately being viable for reasons largely connected to how we think about renormalization in these frameworks. But that could be disputed. The point is that dispute is a scientific dispute in the construction and then ultimately testing of theories. At the moment, the way of modification is a research program. If we were trying to understand quantum mechanics as we have it, then we're not currently in a position to do that. And just to push that point home slightly further, sometimes we talk about non-relativistic quantum mechanics as if it covers like all the world except the sort of exotica of highly relativistic high energy scenarios. But it's important to remember that among the phenomena described by quantum field theory is the interaction of light with matter, which is in most senses of non-relativistic a standardly non-relativistic phenomenon. So I used to live in warmer places. The explanation we have of why the sky is blue is ultimately an electrodynamic explanation. If you want to quantitatively know how blue the sky is, you need to do a calculation in QED. We understand that calculation perfectly well, textbook level. It's not to fully embed it inside a consistent quantum field theory requires that field theory to handle renormalization and embrace the notions of effective field theory or some gesture that alternative way of handling the infinities of naive quantum field theory. Doing that at the moment is still work in progress on the way of modification. Let me go on to the way of the lab. The central idea of the various approaches that come under this envelope is quantum. There are pioneers of this idea in the room here, that quantum mechanics isn't, after all, a dynamical theory. It's not like classical mechanics in that sense. It's not like electromagnetism. It's more not in the business of trying to describe or represent the world in itself. The appearance of observation or measurement or agents in the kind of ad hoc, way of confusion, way of putting things, isn't a problem, as the way of modification would generally say. It's a sort of hint to some deep change in the way we understand physics, maybe the way we understand science. And the right way of understanding quantum mechanics will see that it's essentially connected to observation, to measurement, to agency. What is QM then? It's not a dynamical theory, it's some sort of inferential theory or epistemic theory or pragmatic theory or pool or advice-giving body of some kind. And I'm thinking certain takes on the Copenhagen interpretation fit this space, cubism fits this space, the sort of pragmatist approaches that Richard Healy's developed fit this space. I should be a bit careful with the term Copenhagen interpretation in this framework. I think actually when physicists say Copenhagen interpretation, roughly what they mean is something like the way of confusion. Obviously, actual people in Copenhagen said much more coherent things like this and didn't say the same things. There's a different sense of Copenhagen interpretation where you could say it's what war meant, and even if it's unclear which unobscure reading of Bohr is the correct reading, then Bohr had something much more coherent in mind than the way of confusion. And perhaps if that's what we mean by Copenhagen interpretation, then that fits in this kind of story. But then if quantum mechanics isn't a dynamical theory, it's some kind of theory of inference, what are those inferences about? Where did the dynamics part of physics go? What are we trying to make predictions about, infer about, have primitive advice about? Sometimes one has the idea that the answer is that the measurement process in quantum mechanics is the reclusion of primitive. That what quantum mechanics is about is calculus for measurement devices that are not to be analyzed, that are just to be given. And obviously, as a heuristic in quantum information, there's a lot of power to that move, and there's a lot of reason it's sensible to take it on. More broadly, it describes our actual empirical situation and the way experimental physics actually uses. That you can imagine a world where measurement devices were found scattered across the desert, and they were stamped with self-adjoint operators. And we dug them up, we took them back to the lab, and then we plugged them into sort of black box systems, and then we studied them. But again, they don't let me in the lab, they don't let me in the building, but I'm reasonably confident this isn't how experimental physics works. So I don't think the primitive move is really viable here. The cubist approach takes quantum mechanics to be a theory that, and this is developed in various ways, and I don't want to be sure I've got exactly the right statement of the latest state of the art in cubism, but at some other broad setup, cubism is taking quantum mechanics as essentially a theory of an agent's belief. And you can debate whether that's what we want scientific theories to be doing, but just as a more practically pertinent concern, we have the issue that if we look at quantum mechanics or specific quantum theories, if we open a particle physics textbook or a solid state physics textbook, we don't find quantum theories that make claims about beliefs. We find them making claims about positions and momentums and spins and quarks and things of this kind. So there's a concern that if one has that kind of take on quantum mechanics, if quantum mechanics is going to be about my beliefs, then my ability to connect that kind of thing to the sort of dynamical language of any specific concrete application of quantum mechanics needs to be addressed. Now, I mean, looping back to Guido's talk 2 days ago and Simon's comment on it, or at least as I understand Bohr, had a perfectly logically coherent answer to this. Bohr, if quantum mechanics was not necessarily, if you thought it was a dynamical theory, what was the dynamics? The dynamics was classical. The theory was about the classical. The concept all came from the classical. And I think that's a perfectly logically consistent way of thinking. And I think it was a perfectly reasonable thing to advocate in 1925, with perhaps niggling worry about the Stern-Gerlach experiment somewhere there. But to reprise the list I gave earlier, it's not viable for the physics of the 21st century. We talk too much about specific quantum mechanical concepts that don't have classical analysis for that. So to sort of sum up for the problems I'd see for the way of the lab, philosophical problems, which often get the focus in my communities, things like, one could say, well, isn't the job of physics to describe or represent the world? To which I think various advocates of these other approaches will say, no, it's not. And that's the sort of inconclusiveness that sometimes can plague philosophy. Don't we want to be realists? No, not especially. Or else we do, because realism gets used almost as a virtue term, and then there's a fight about what realism actually means. Isn't operationalism bad? No, it's fine. I'm more concerned with the scientific problems for this class of approaches, and the sort of questions I want to get out of a satisfactory inferential style reading of quantum mechanics aren't things like, does this describe an observer independent world? I want to know the answers to questions like, how come integer spin particles are bosons and half-odd integer spin particles are fermions? Why does helium-3 become superfluid at a lower temperature than helium-4, etc.? These are all questions, I want to say, that have perfectly good answers inside physics. These aren't mysteries. I could have put down some genuine mysteries, like why is the Higgs as light as it is? What's dark matter? These are questions that I think we have satisfactory understanding. Most of them I could even try sketching that satisfactory understanding myself, but the understandings are deeply quantum mechanical. They're the challenge. The challenge for a way of modification is to build concrete dynamical theories that reproduce the empirical predictions of relativistic quantum field theories. And I take the challenge for way of the lab approaches is to explain how we're supposed to make sense of these very specific concrete claims about specific quantum systems. Which brings me to the way of decoherence. Here's what goes on in the way of decoherence, and it might help to say that the other name for the way of decoherence is the church of the larger Hilbert space. Come to the way of decoherence, quantum theories, and I use the plural advisedly. Any given quantum theory, non-relativistic spin half particle theories, QED, the particular harmonic oscillator theory, a particular laser theory, the standard model, hoped for quantum theories of gravity. Quantum theories are dynamical theories, just like classical theories. And the dynamic, at least at the fundamental level before you start doing coarse graining and other statistical mechanical good stuff, the dynamics are always unitary. Measurements are just one more physical process. A special case of the dynamical behavior of the system's quantum mechanics models are the interactions of a measurement device in the lab with the system that the measurement device is measuring. And any time you want to analyze that in detail, we just do so by moving to a bigger Hilbert space that includes it and staying unitary at that larger level. And I'll pause briefly there just to loop back to the Zeno effect, because of course that's the resolution of Mr. Starshan's paradox. If you actually want to concretely model the device that's doing a continuous measurement, what you want is a device where if the system being measured is in a certain state, then the measurement device remains in its ready state. And if the system is in some different detector state, then the measurement device evolves into some recording state, not magically, not like that, as a dynamical process of the timescale. And then it's the timescale of that measurement process that to be compared with the timescale of the underlying dynamical time of the system being measured to tell you whether Zeno freezing occurs. Geiger counters do not, in fact, freeze radioactive systems in place because the response time of Geiger counters is very slow compared to the nuclear timescales on which radioactive decay occurs in the first place. We can do experiments where we actually demonstrate Zeno slowing in the lab, and the relevant parameter is precisely whether actually the speed of the detection device does move to being comparable to the transition speed of the system doing it. Perfectly straightforward, lovely physics. It requires us to adopt the church of the larger Hilbert space to step out to include the measurement device in the quantum theory. Observers are just one more physical system. Sorry, guys, you're just more physics. And classical mechanics on the way of decoherence doesn't have any conceptually special status. It's just something that comes out emergently from quantum mechanics in appropriate regimes. It's related to quantum mechanics in the same way as all manner of higher level emergent theories in science are related to lower level physics. And we understand quantitatively in some detail a great deal about how that emergence works. I should say, incidentally, I said this wasn't a history talk. Obviously, one can find precursors of these ideas all the way back to the birth of quantum mechanics. You can find Mott's work in 1928, looking up pieces of this. You can find von Neumann's modeling of measurement processes picking up on this. Anytime as an undergraduate, you do one of those calculations about how quickly wave packets spread out and point out that in the limit of large mass, they spread out very slowly. And that's why we can understand, why we can apply classical mechanics to people at tables. We're picking up sort of aspects of what becomes more systematically the way of decoherence. And there's no qualitative distinction between macroscopic and microscopic superpositions. There's no fundamental difference between applying quantum mechanics to a microscopic system like an electron spin and a mesoscopic system like a dust mote and a microscopic system. All of these things can be put in superpositions. All of these things are governed by quantum mechanics. Why are we unable to detect macroscopic superpositions, and are able to detect microscopic superpositions, and are fitfully able to detect mesoscopic superpositions, dynamic, specifically decoherence. The physics of decoherence, which I want to understand not just as a spatially external environment interacting with a quantum system, but short wavelength degrees of freedom of the same macroscopic system interacting with the larger scale collective degrees of freedom of that system. It's decoherence that tells us that in practice, interference phenomena are undetectable for macroscopic superpositions. It's decoherence that tells us how it is that the interference results that mean we can't consistently and right across physics treat mod squared amplitude as probability do allow us to treat mod squared amplitude as probability in macroscopic context. And it might not have escaped people's notice that really that set of claims are pretty much the defining set of claims of the Everett interpretation. Just to reassure Nicole that the Scooby-Doo references work on both sides of the Atlantic. So what are the problems for the way of decoherence? Well, there are philosophical problems. Is it even coherent, so to speak, to imagine macroscopic objects in superposition states? Are we committed to this vast and untenable ontology? If it's really the case that the formalism is not treating, doesn't give us any grounds to treat superpositions of cats any differently from superpositions of electrons, isn't our theory committing us to there being live cats and dead cats at the same time, to many copies of ourselves, to the kind of multiverses that are already making Emily wince in pain? And that's the one that's had the most attention philosophically. How do we justify the Born rule conceptually? How do we make sense of interpreting these mod squared amplitudes as probabilities? We understand through decoherence that they have the right formal properties to as probabilities when interference is suppressed. Is that sufficient to justify treating them as probabilities? These are all philosophical problems. There's nothing wrong with philosophical problems. They pay my salary. But it's worth saying that these are not bars or blocks to the scientific application of the way of decoherence in doing physics. And as a brief aside on the last of those problems, 20 years ago, my main focus was understanding probability in the many worlds theory. I gave a whole bunch of talks to physicists, particularly quantum information people. I found that it was quite difficult for them to, some of you have heard this story before, so apologies. I found it was quite difficult to explain to them why one should care about the probability problem. I got moderately good at giving the spiel that explained to them why there was a problem before explaining why, after all, there wasn't a problem. After a while, it dawned on me there was a quicker route to the same conclusion. We move on to the scientific problems for the way of decoherence. I don't know any. The quantum mechanics understood through the way of decoherence does seem sufficient to make perfectly good sense of all the way we use quantum mechanics, indeed to a kind of rational cleaning up of the way we use quantum mechanics. And this is the sense of my title, that when people talk about shutting up and calculating, it's a theory. Well, prior to the 80s, I think the answer was if you shut up and calculate, you were shutting up and calculating in the way of confusion. And sometimes you got confused. By 2025, I think if you shut up and calculate, you're shutting up and calculating in the way of decoherence, which is to say, in the Everett interpretation. So that's the end of the main flow of the talk. What I want to do at the end, though, is just do two things. One to sort of circle back to the measurement problem and the role it's played in thinking about quantum mechanics over the last 100 years. And one is to go back to the question in the first panel discussion, what quantum? So as to the first of those, in defense of the fact it was, after all, worth thinking about the measurement, what have we got out of that thinking? Well, I think each of those ways of approaching quantum mechanics has taught us a lot about the theory and a lot about the world. The way of modification was most of the motivation for thinking about and exploring the Bell inequalities, huge amount of the motivation for the various no-go results that have characterized a lot of quantum foundations. Our space of how to think about testing quantum mechanics is enormously informed by these attempts to modify it. We have a parameterization of the ways in which you might test superposition and unitarity and the Born rule coming from these various ideas. The continuous state localization theory, last time I looked, is at the point of being paid the second highest honor any scientific theory can be paid, which is to be a scientifically serious theory that has been refuted by evidence. The way of the lab has given us a lot of quantum information. It's given us an understanding of an exploitation of the analogies that seem to lie between quantum mechanics and classical probability theory. The most problematic aspect of all of the approaches, in my view, from a scientific point of view, of all the approaches to quantum mechanics that treat the quantum state as representing physical goings on, and if they're not careful, sometimes as even representing a thing or a field, is that they can hide from us how deep the analogies are between quantum theory and classical probability theory. And exploring those analogies has been incredibly fruitful and would not have come, I think, without this kind of way of thinking about quantum mechanics. And the way of decoherence has given us a detailed dynamical understanding of the quantum classical transition, given us decoherence theory itself. It's given us a way to speak of the physics of quasi-classicality and medoscopic goings on and things in a way that vastly transcended what we could do when we were waving our hands with the correspondence principle. And with the historical matter, it gave us some of the seeds of quantum computation. So these sets of ideas have been enormously influential in helping us understand this theory whose centenary we're celebrating. That's my kind of apologia, if you like, for why it was worth the effort of thinking hard about the measurement problem and why it's still being proved. The other thing I want to talk about is what is the answer to the what quantum question? What did we get when we got quantum mechanics? And I want to say, in an unapologetic way of decoherence, way of thinking about it, parche the idea that we need to replace the formalism or the idea that we need to reinterpret as something non-dynamical. What quantum mechanics gave us was our third dynamical framework. I originally wanted to say second. Prior to quantum mechanics, the first, if you like, dynamical framework we had was the one that was bequeathed to us by Newton and developed into its formal shape across the course of the 19th century. Classical mechanics, governed by Hamilton's equation or the Euler-Lagrange equation, with the state of a system being a point in phase space or a pair of positions of momenta or the appropriate generalizations of those ideas. There's actually a second framework I think worth pulling out and thinking about in its own right, which is classical statistical mechanics, understood in where now states are probability distributions that evolve on a state space where the dynamics is now Liouville's equations. Obviously, right from the inception of that, we've had some idea that classical statistical mechanics fits not just formally but conceptually on classical microdynamics. But it's worth noting that the viability of using the classical statistical mechanical dynamical framework well outstrips any conceptual comfort we have in just what these probabilities would have been in classical physics. And our third framework, of course, is quantum mechanics, with the dynamics being Schrödinger's equation or path integral framework with states with density operators, or in special cases, Hilbert space rays. And it's worth saying that in many ways, that third framework is an amalgam and then an extension and development of both of the first two frameworks. One way to understand where the measurement problem comes from is that quantum mechanics behaves in some ways like its framework is an analog of the second framework, and in some ways, an analog of the first framework. And I want to just finish by just stressing the point of that dynamical framework way of thinking about the theory and the way that links back to my advocacy of the way of decoherence as the way to understand the physics we have at the moment, whatever the routes forward are. It's striking that on the first day of this conference, where there was a lot of history, we heard a lot about, electron, argon, blackbody radiation, specific physical systems for which quantum mechanics was producing specific quantitative predictions of their behavior and the results of measuring them. And yesterday, where we were more focused on sort of the contemporary foundational structure, we had very little of that kind of concrete physics. We had issues of the very general shape and structure of quantum mechanics. And that's perfectly appropriate, and that's not a problem. This is a conference on quantum mechanics. It's not a conference on particle physics or solid state physics. And what counts, if you like, of work on quantum mechanics in the 21st century is work on what it is that quantum theories have in common. And to a very large extent, quantum information and quantum thermodynamics are explorations of what you can learn about systems simply by virtue of the fact they fit the quantum framework. And it's striking how deep and how much you can get at. But when we're trying to understand the theory as a whole, I think it's very important to remember that nonetheless, this is an abstract framework in which concrete theories sit. And it's those concrete theories which are the reason we take this quantum framework so seriously. So if I ask what would I expect in the next 100 years, or hope for in the next 100 years of quantum mechanics, I'd certainly hope that we come to understand the quantum framework more deeply. I hope we can test and challenge that framework. And if it turns out that we can break that framework, move on to a fourth dynamical framework, move on to something beyond dynamical frameworks altogether, great. But I also expect that within this amazing framework for doing physics, we will develop deeper and more powerful theories of physics. I'll stop there. Thank you.
Thanks for the excellent talk. So we'll start with Anthony Valentini at the back there.
David, won't surprise you that I'd like to focus on this point about, and I think it's a good point, that there is all of this physics of renormalization, interacting quantum field theory, that people in quantum foundations don't tend to discuss much. A couple of minor points. I mean, I think maybe you overstate a little bit. There was something like Rayleigh scattering. All you really need is non-relativistic atoms coupled to the electromagnetic field, and that to calculate that. And that was, well, that theory was written down by Bohm in 1952, and he used it to discuss Compton scattering photoelectric effect for non-relativistic particles. But anyway, minor point. But look, I think that one other minor thing I'd like to say is I think there's a comparison between some of these theories like de Broglie-Bohm and path integral theory in the early days. It wasn't until the 70s, I think, that people started applying it to quantum field theory. And it took quite a lot of effort to figure out how to deal with, for instance, gauge theories and so on. And, you know, if we were in the late 50s, we could have said, well, path integral theory, how do you apply it to fields and so on and so you could. Anyway, and so few people have worked on this. There's clearly work to be done. But look, a more substantial point. For example, de Broglie-Bohm has been applied to lots of things, quantum cosmology, quantum gravity. Nobody's really looked at this area of interacting QFT properly with renormalization. And it seems to me that there are some scientific issues there that would be issues also for Everett. A scientific problem for Everett. And it is this, that interacting quantum field theory, usually it's used to construct an S matrix. All the talk about renormalization, the initial time and the final time are asymptotic. You start at t is minus infinity with some state. You're calculating probabilities to get various states at plus infinity, and there are ways of dealing with the infinities and so on and so on. And some people will take the view that quantum field theory is just a way of calculating an S matrix, and there isn't really a quantum state evolving in time in between. We don't really have a good way of doing that. And to my mind, this is why it's very difficult to do a de Broglie-Bohm theory, because you don't really have a time evolving quantum state. But it seems to me it would also be an issue for Everett. Without a realistic sense of, you know, how do I calculate an actual time evolving quantum state at finite times? I mean, just briefly, we do this, for example, in cavity QED, when you have atoms in a cavity and they're just coupled to one or two modes of the electromagnetic field, and people observe photons emitting and absorbing over finite time. But they're highly truncated models. just a couple of modes. To get that from the fundamental theory would be highly non-perturbative. And I'm not quite sure anyone really knows how to do that. So I would see this as a problem in a sense also for Everett.
So the short answer is I'm just much more comfortable than I think you are with what the foundational status of contemporary QFT looks like. I mean, it would get us too far off topic, so I won't go detailed because we can talk offline. But I think we have a perfectly good evolving quantum state understanding of QFT, and I think our understanding of the conceptual foundations of the subject are just vastly on better ground than they were, prior to the renormalization revolutions in the 70s and the effective field theory ideas in the 80s. Yeah, if you like, this was my complacency talk about quantum mechanics. I could be given a different complacency talk about effective field theory. So I want to just disagree with those claims about QFT, but I'm not sure it's probably sensible for me to try to.
Maybe we can talk about that afterwards.
Sure.
Yeah, I think next was Matt. So,
So what I want to complain about is this dividing line between what's a philosophical problem and what's a scientific problem. There's a certain amount of arbitrariness in that, and if you put it, if you put more things in the philosophical side, then it's going to look like one point of view is better than another. In particular, the probability problem in Everett is arguably a scientific problem because if you, I mean, so you can say it's the problem of justifying the Born rule. We have the Born rule, we know that's correct, but why in many worlds theory? But many people take the view that there isn't a coherent justification. I know that you disagree with this, and other people take the view that there's some other rule which is obviously the right one, and in which case it makes different predictions for quantum mechanics and it's a modification. And maybe there's even some other rule that we haven't come up with yet that would be, empirically adequate so far, but predict tiny deviations or something like that. So to that extent, I think it is a scientific question and would probably be put on the other side. What do you think about that?
So the line's obviously somewhat arbitrary, but insofar as I wanted to make it principled, I'd say that what I'm calling scientific problems are problems that actually get in the way of you applying the theory to concrete situations rather than feeling bad about blind. So, so nothing about the probability problem would get in the way of you using unitary quantum mechanics to model and test a given concrete physical situation. You might feel, you might feel there was a deep and unresolved philosophical problem about why you were allowed to compare this mod squared amplitude with the relative frequencies you observe in the lab, but nothing would stop you doing it in the first place. So that's the kind of what I have in mind in that distinction. I mean, just as a sort of side point off that, I think sort of comment to philosophers, I think very often when people are worrying about sort of anti-realist or operationalist approaches to quantum mechanics, the way they do it is towards a sort of general appeal to why it's sort of philosophically unsatisfactory not to be a realist. I think it's worth remembering that a large amount of why those approaches to those sort of operationalist positivist approaches to scientific theories fell from grace in the mid-20th century wasn't that we had some horrible realization that we weren't describing the real world and that was a sin. It was because actually drawing those kind of distinctions between observation and theory didn't turn out to be viable. You couldn't actually take a physical theory and understand it this way. You just didn't have the means to do it. The bits didn't fit together, right? So this is the kind of thought I have as to the philosophical versus scientific distinction. Can you, however unprincipledly, can you use the theory to do physics for the particular system you want to study?
Yeah, thanks.
David, I don't know if you can just go back to the slide with your three frameworks.
Yeah, sure.
Because I just wanted to talk a little bit about the framework number 2, which was the
this one.
Liouville's equation. Now, in classical physics, Liouville's equation, it's a linear equation in probability density. We know it's not a fundamental equation because we can take ensembles of nonlinear, highly nonlinear deterministic equations and just coarse grain them, to use Anthony's word, and they have to they have to satisfy Liouville's equation, because all that is doing is a statement of conservation of probability. So Liouville's equation says nothing about the fact that there is typically in classical mechanics, there's a deep underlying generically nonlinear structure to these probability distributions. Now, Schrodinger's equation is incredibly close in density operator form to Liouville's equation. I mean, we all know this.
Yeah.
And I think, therefore, there's a kind of an onus if you promote what you're doing, the decoherence, if you like, the line that all there is the Schrodinger equation, to explain why is it that that Liouville's equation has this clear deterministic underpinning, that is not the case for Schrodinger's equation, despite the incredibly close formal similarity between the two equations. I mean, this for me is the primary reason why I can't believe that the Schrodinger equation is the final word.
I mean, I can, just as a psychological comment.
Right. Well, it's a philosophical comment, if you like. It's a philosophical.
So there's a lot more I could say, and I'll try to answer briefly. I think I pulled the second framework out because again, it's not as if we've ever had a completely agreed upon it by everyone understanding of what these classical mechanical probabilities are, and more importantly, because I think from a quantum perspective, then the second framework tends to end up coming out directly as a limiting case of the third framework. So if you think about, some people have heard me this example, if you think about, say, how I treat a quantum mechanical dilute gap, system is described fundamentally by a quantum mechanical description. It's emergently extremely well described by a kind of Liouvillean account that talks about something like a BBDKY analysis. That works very well. The microphysical account gets everything completely wrong. The wave packets, particles spread out quickly. If you try to put an individual gas molecule in a wave packet state, it will just spread out very fast. So there's no sense in which it's approximately true, according to the theory, that the dilute gas in the room is well described by framework 1, assuming quantum mechanics is a deeper description. But nonetheless, it is very well described by framework 2. So I think often one of the things quantum mechanics does is make us rethink the relation between framework 1 and framework 2. Now, none of that gets in the way of the possibility that there might be something underlying framework 3 that is to framework 3 as framework 1 is to framework 2. But again, that's in the space of a scientific research project. I have no problem with that research project. Again, that research project at the moment is not capable of reproducing the predictions of quantum field theory.
If you adhere to the way of the lab, I can't see, or actually, I believe that you have all the tools available to predict that helium-4 is superfluid. And I've never understood, because I think I asked the same question before in the talk you gave years ago. I've never understood why you think there's a problem, why you think there is this particular scientific problem in the way of the lab. Because you can use all the formulas of quantum mechanics, make all the predictions that you can make from the decoherence viewpoint.
So what I would say is that when you're doing that, to make the prediction in enough detail, you're actually in the decoherence viewpoint. I mean, if you want to say, I will do physics exactly the way the decoherence viewpoint tells me to do it, but by the way, I don't believe in all the things that exist in it. I don't believe in macroscopic superpositions, even though they're in theory. That's fine. I'm not here to force anyone to believe in things they don't want to believe in.
But then isn't this a sort of a false distinction you're making there?
I don't think so.
Because why would if you choose if you choose to treat your measurement apparatus and the system as the system of interest, well then you will have the same tools available that you have available in the decoherence viewpoint. So I don't think there is a
So I wonder if we don't mean the same thing by way of the lab. I mean, I don't simply mean like I'm going to quantum mechanically model a measurement. I mean that the kind of thing that plenty of people will explicitly advocate. The quantum framework is not a dynamical theory; that it's just an inferential tool. Insofar as it's just an inferential tool and doesn't do dynamics, what does it mean when it talks about helium or boson? I mean, what are those? What's my understanding of the content of those claims if it's not something that comes out of the dynamical details of the theory that governs them?
So then can I just remind you of your own little joke about the quarks in a proton? That's just image children. I mean, if you make the same predictions, you have the understanding that the quantum mechanical tools you're using, I mean, they are in the end they're tools, and the stories you tell, they're stories you tell, but they are not the real thing in some ways.
Yeah,
So,
but I think what you're describing is my way of decoherence. Was it Wayne? I think it's Wayne.
Thank you. This was really good. I'm not convinced, though. For quiescence or quantum mechanics, and I really liked your metaphor of classical electrodynamics because you compared the wave modification to modifying classical electrodynamics because some disquiet about nation of charge. And what's striking about that metaphor is subject that we now call classical electrodynamics did not exist until the 20th century at a time when it was clear that it had to be superseded by something quantum, and then people said, okay, here's the domain of this theory, and here's the things that we don't have to outside the scope of the theory. If you read, say, Maxwell or Lorentz or anybody in the 19th century, it's very much a work in progress. And there's a sense in which completed theories are, fossil theories, right? And I think that the motivation of the wave of modification is, I'm not willing to think of quantum mechanics as a fossil theory in that sense. So, like, one thing I really was struck by Anthony's talk is, unlike, say, the Bohemian Mechanics School, he's thinking of this as a research program very much in progress. And, I think of the collapse program as very much a work in progress. And I think quantum theory is still a work in progress. So we don't have a final version of it.
So I think that plays a little bit on an equivocation of what we mean by quantum theory, and it sort of goes to my framework point. Do I think quantum theory is a fossil theory? No, I don't think it's a theory at all. It's a framework for theories in it. And do we have a last word theory in that framework? No, of course we don't. The best we currently have is the standard model, or maybe the standard model plus low energy gravity. We know that's not the final theory. Our very conceptual grasp of that theory relies on it not being the final theory. All of that is consistent with the framework being fine. And it might not be, who knows? But we don't. It's not like we have a massive inductive base here. We haven't had lots of frameworks for dynamical theories. Depending whether you buy my framework 1, framework 2 distinction, we've either had one previous framework or two, and if it's two, the second didn't supersede the third. First, it coexisted with it. We've only once kind of changed our mind in a big way on dynamical framework, unless you sort of count Newton versus Aristotle or something. It might be that we need to, but I think the idea that somehow our physics is fossil physics, unless we commit to the need to replace the framework with a new framework, overstretches there, and absent some first order reason to think there's something wrong with the framework. It's fine to think one of the new frontiers of physics can be changing our framework, but one can perfectly well be perfectly through the framework and think that the frontiers of physics are going to lie in cosmology and particle physics and quantum gravity, all of which are going to be quantum theories inside the quantum framework.
I don't know why you did like quarks. Deep inelastic scattering shows them as particles. I like very much your talk, and I agree with everything. I still want this semantics. I'm happy that you said the coherence is also internal decoherence. This is not like it was usually used. Usually it's only with external thing. And it seems to me just trivial consequence of Schrödinger equation for macroscopic bodies. So it's exactly Everett. You wait to promote Everett. It's kind of too radical, and you want to call the coherence?
I think I did promote Everett.
You know, why introduce this word? You think it's better?
So part of the reason is I think it is the case that if you accept that collection of views and you then want to make conceptual sense of that theory, you basically have to make sense of the many worlds theory. But I want to leave over the scientific. I see Elise. I want to leave open the space for people to say, "I'll do quantum mechanics this way. I'll treat quantum mechanics as thoroughly dynamical. I won't give any special role to measurement. I'll treat the classical as purely dynamically emergent." Nonetheless, the right way to think about that is not many worlds. I don't think that route is available. Pedagogically, I think at the very least it's super helpful to have that way of talking here, but I haven't actually given a knockdown argument for that here. And in terms of where I want people who don't like many worlds to think, I would prefer them to think about alternative ways of making sense of the way of decoherence, rather than or too strong. I'd like that to be a more live option for people who don't like many worlds.
Thank you.
Everyone should, of course, like many worlds, but alas, we are a fallen species.
Okay, we're going to break for lunch now. We'll be back at 1:45 for Emily Alarm's talk. Thanks again for David Wallace.
Hey, let's get going. My name's James Ladyman. I'm from the University of Bristol. I've been thinking about these issues for a small fraction of the last 100 years. I'm a lot younger than most of the people here. It's my very great pleasure to introduce first for this penultimate session of this wonderful conference, Emily Adlam, who's going to talk about relational interpretations, why and how.
Great. Thank you very much to the organisers for putting on this wonderful workshop. And thank you for the invitation. It's been very nice to be back here. I also should thank the John Templeton Foundation for their support for the Southern California Quantum Foundations Hub, which has made this work possible. So what I want to do today is talk about relational interpretations. So first, explain why I think we should be taking relational approaches to quantum mechanics seriously, and then think about a variety of choices that we have to make in setting up a relational interpretation. And the point I kind of want to make here is that there are a whole bunch of sort of different choices that we have to make in setting this up. And so there's quite a wide space of possible options that one could possibly consider within this sort of regime of relational interpretations. And there are a couple of positions in this space that have been occupied, and people have tended to flock towards those sort of occupied positions. So one of the things I want to sort of emphasize today is that I think there are all these other options that perhaps have been less well explored and which deserve further exploration. So I will advocate specific answers to these questions that I personally find most compelling, but the more general point I want to make is that we do have all these questions to answer. There's more possibilities out there than what has sort of currently been well explored. So why should we take relational approaches seriously? There are motivations here coming from within quantum mechanics and other motivations coming from outside of quantum mechanics on the sort of gravity side. So first of all, within quantum mechanics, perhaps the most obvious motivation is the Wigner's friend style scenario. So as we know, in a Wigner's friend scenario, we're going to put our friend Alice in a box, and we're going to have her perform a measurement on a system S in a superposed state as shown here. We'll have our other friend, Bob, standing outside of the box. He's going to have complete coherent control over the whole contents of the box. So now if we apply unitary quantum mechanics from Bob's point of view, Bob is going to conclude that Alice and S are in this entangled state shown here. And presumably Bob could in principle confirm that they really are in this state by performing appropriate tomographic measurements. So the point of the paradox is that it seems like something weird has happened here. Presumably Alice has obtained some result to her measurement, but from Bob's point of view, it kind of looks like she's in some mixture of seeing both outcomes at once. What is going on in this situation? So obviously one option we have here is just to say that unitary quantum mechanics is not universally right. Perhaps the wave function collapses for everybody around the time of Alice's measurement, in which case the state I showed on the previous slide is not the right one for Bob to use. But for reasons of sort of simplicity, theoretical elegance, and relativistic covariance, we might like to try to maintain that unitary quantum mechanics is always right in the sense that it's going to make the right predictions for both Alice and Bob if they just evolve unitarily up until the time that they make their own measurement. So what happens in this situation if we assume that? Well, in that case, immediately after Alice has performed her measurement, the state of S, which correctly predicts the result of the next measurement she makes, if she makes one, is going to be either 0 or 1, depending on what outcome she obtained. And meanwhile, the state of S, which correctly predicts Bob's next measurement, is going to be this mixed state here that I obtained from the state on the previous slide by tracing out Alice. So obviously we can see that these are different states. Alice and Bob are using different states to predict the outcomes of their measurements on the same system at the very same time. So I guess what we kind of learn from the Wigner's friend scenario fundamentally is that if unitary quantum mechanics is always correct for all observers all of the time, some relativization of states in some sense is inevitable. We have to use different states for Alice and Bob in this situation. Now that doesn't necessarily mean that we're involved in anything that's sort of radically subjective or sort of very weird metaphysically. All we're really saying here is that Alice's measurements have different predictions from Bob's measurements, and that's fine. Those are different sets of measurements, they're different physical events. Moreover, only one of Alice and Bob can actually be the next person to measure S. So there's nothing sort of paradoxical or contradictory about just saying we're going to make different predictions for those sets of measurements. And so we have various kinds of relativization like this emerging even within sort of fairly standard realist approaches to quantum mechanics. In Everett, we have relative states. So we have states that are relativized to branches. In the situation we've just looked at, Alice and Bob have different predictions because they're in different parts of the wave function, and so they're sort of working with different relative states. In de Broglie-Bohm, we have conditional wave functions conditioned on collections of de Broglie-Bohm particles. And then, of course, there are other approaches which do take a more sort of radically subjectivist view, like relational quantum mechanics. But all of these are implementing some kind of relativization in this kind of situation that we have dealt with. So what we learn from Wigner's friend is that, at least at an effective empirical level, some kind of relativization is going to happen, but we've got a variety of choices about what exactly that might look like. The next type of motivation comes from outside of quantum mechanics itself, and in particular, there's a variety of motivations coming from our understanding of gravity and GR. So obviously in classical physics and to some degree in most applications of quantum mechanics, descriptions of physical systems are being given relative to an assumed fixed space-time background. But in a relativistic context, we don't have a fixed space-time background to work with anymore. So the standard interpretation of GR says that histories related by a diffeomorphism are physically identical. That means that variables defined at individual coordinates, such as the momentum of the particle at time t, are not by themselves physically real, and descriptions of things relative to space-time points are not meaningful. So what is physically real in that theory? Well, the observables are usually considered to be either the highly non-local quantities defined or integrated over the whole of space-time, or relational quantities built out of correlations between field values. Obviously, those highly non-local quantities are not going to figure very much in our experience of the world. So most of the things we observe in our everyday lives are going to turn out to be relational observables. So for example, the momentum of the particle at time t is going to have to be rewritten as something like the momentum of the particle relative to the clock reading time t. So in effect, many of properties of systems that we would normally have thought of as being intrinsic in sort of physical physics are going to turn out to be relational in nature. These are properties that have to be stated relative to other physical systems. So that's true for things like orientation, position, charge, momentum, and so on. Exactly what is included in that, we could discuss further, but certainly many intrinsic properties are going to turn out to be relational. And because quantum states either sort of characterize these properties or assign probabilities over them or something like that, there are good reasons to think that at least sometimes quantum states are also going to have to be relational because the properties that they are being used to predict values for are themselves relational. So obviously the specific details of that depend on how one goes ahead and implements a theory of quantum gravity and so on, but certainly there are reasons to think that we should expect to see relational behavior from quantum states too in that kind of context. Moreover, it's been argued that since we're seeing some kind of relational thing happening in quantum mechanics with the Wigner's friend stuff, and we're also seeing some kind of relational thing happening in gravity with these relational observables, that's an indication that relationality is kind of the key to unifying them, and that's the route we should go down if we want to get the unification right. So Vidotto is making that argument here, saying that the relationality in relational quantum mechanics is just the same as the relationality in GR, and that's telling us it's the right way to think about quantum mechanics. So I think we should be a bit careful with this because the word relational is extremely broad in general. More or less anything can be said to be relational if you kind of squint. So we perhaps shouldn't make too much of this connection. But I think it's fair to say that we do know that in some sense, relationality is going to play an important role in a diffeomorphism invariant theory. We should at least be thinking about what that might mean for the interpretation of quantum mechanics. Okay, so I'm going to assume now that I have convinced everyone that we should be doing relational interpretations, and we're going to think about what that might look like and what choice options we have in trying to set up a relational approach. So first of all, if quantum states and quantum descriptions are relativized, what are they relativized to? So we know from the Wigner's friend scenario that we probably want them to be relativized to observers or physical systems playing the role of observers in some situations. But are they only relativized to observers, or can they be relativized to something else as well? So I sort of noticed two different schools of thought around this in the literature. And one is what I'll call the anthropocentric view, which suggests that quantum states are relativized to observers or something sort of closely related to observers. So to conscious observers or to human observers or to measuring devices or laboratories or macroscopic environments or something that's sort of in the vicinity of observers. So that includes various Neo-Copenhagen approaches, maybe cubism, maybe pragmatist approaches. I would have to discuss with those people to see if they think that's the right way to think about those approaches, but certainly there's quite a few approaches which do focus on observers. The alternative is what I'll call quantum universalism, which says that quantum states can be relativized to any physical system whatsoever. So that includes relational quantum mechanics, it includes some perspectival modal approaches, It also, I think, includes much of the quantum reference frame formalism. Quantum reference frames are not an interpretative approach to quantum mechanics, but one of the motivations of the formalism is to learn how to describe quantum states relative to all sorts of different physical systems. So there does seem to be some kind of universalism going on there too. So both of these approaches, I think, have some drawbacks. The anthropocentric approach is not generally very appealing for realists, and those who think that we should be able to describe observers in physical terms and we shouldn't have to use them fundamentally in the statement of the theory. It's also, I think, not a great fit for other relational stuff going on elsewhere in physics. In GR, for example, there doesn't seem to be any suggestion that relational observables need to be relativized to humans or to measuring devices or anything like that. They can seemingly be relativized to all sorts of things. So insofar as we're motivated here by trying to make a connection with that kind of relationality, perhaps the anthropocentric approach is not the right way to go. The universalist approach, I think, is for me more appealing on a conceptual grounds, but it runs into technical problems, because if you're going to assign a quantum state to a system relative to some reference, you presumably want that to have some kind of content in terms of interactions that they could have, or observations that the reference could make, or at least relations in which they can stand. And for very small reference systems, it doesn't look like there's going to be enough structure there to really give any meaningful physical content to a description of a quantum state relative to that thing. So it starts to become quite hard to understand what it would mean to assign a quantum state to something relative to a qubit, say. So Bruckner makes a point like this in his paper, Qubits Are Not Observers. So he's criticizing RQM specifically here, but I think the kind of concern he's articulating is plausibly relevant for other kinds of universalist approaches too. So in RQM, the way in which ascriptions of quantum states relative to things is made meaningful and given content is by saying that when two systems interact, an observation is made where a variable of one system becomes definite relative to the reference system, and the probabilities for those variables becoming definite are given by the quantum state. That's what quantum states mean in this context. But obviously, to make that more precise, we're going to have to say something about which basis this observation is supposed to take place in. And for very small reference systems, start to become not obvious how you're supposed to really meaningfully give content to that. So the point Bruckner makes is that certainly there's a natural way to think about what you might want to do here, which is to take advantage of the Schmidt basis. So when two quantum systems interact and become entangled, there's always a Schmidt basis in which the resulting state looks very simple. That's the one here without any cross terms. And it seems natural to think that if an observation is being made, it should be made in the Schmidt basis, because there's a sort of obvious interpretation of that top state there, where the first term is system is in state 0, reference saw outcome 0. Then the second term is system is in state 1, reference saw outcome 1. And so we can kind of understand that as representing an observation. It's less obvious to see how you would interpret the non-Schmidt basis and what the 0, 1, 1, 0 terms would mean if we're trying to talk about an observation. So if you have a unique Schmidt basis, then maybe you're sorted. Maybe you could just use that to define the basis of interaction. But the Schmidt basis is not going to be unique if there's any degeneracy in the coefficients. So if you're dealing with very large systems, assuming that it's very unlikely that more than a few of the coefficients would be degenerate. And so plausibly the Schmidt basis can be seen as being like approximately unique. Most of the bases will be ruled out. You'll have at most a few options. Most of the space will be not allowed. Or of course you have the basis that's favored by decoherence that you might appeal to. But if you're looking at an interaction between a pair of maximally entangled qubits, Schmidt basis is not even approximately unique. You can generate, given any Schmidt basis, you can generate another Schmidt basis by just applying a joint unitary rotation to the whole thing. So what that means is essentially any possible basis of observation is going to correspond to some Schmidt basis for that pair. And so there's no way to sort of use that to narrow down the basis of the observation in any way at all. Any basis is allowed. So the worry here is that for a pair of qubits, there just doesn't seem to be enough structure here to meaningfully single out a basis in which one qubit observes the other qubit. So that's just one example of this kind of problem, but I think you can sort of start to see how it could be quite hard to give meaningful content to whole quantum state relative to something like a qubit. So for that reason, I think there's a third alternative that we should plausibly be taking into account here. And that's going to involve saying that the state of a system relative to another system should reflect the actual physical resources available to that reference system. And what that means is that we can always give a description of one physical system relative to another physical system, but that description is not always going to be a full quantum state in the usual sense. what we're going to get is something that approximates the full quantum formalism only in the limit as at least one of the systems becomes large. I don't have time to go through the details of this paper by Poulin. This paper and other papers have made attempts to look at what happens when you describe one system relative to another one. And it does seem to be true that, roughly speaking, what happens is that the full quantum formalism in the ordinary sense emerges in the limit as the reference system becomes large. You don't really get the full quantum formalism for two very small systems. So the thought here is that the quantum formalism should be understood as the correct way to describe, for example, the physics of microscopic particles relative to a macroscopic observer or a macroscopic laboratory or a macroscopic measuring device, not necessarily going to be the right way to characterize microscopic particles relative to other microscopic systems. So from that point of view, the quantum formalism should be thought of as kind of the large reference limit of a relational theory. In particular, that's going to allow us to solve Bruckner's problem because a qubit doesn't have many resources. The state relative to a qubit should be simple. And in fact, I think you can sort of straightforwardly see that the state relative to a qubit is just going to be a classical probability distribution over the outcomes of one measurement. You only have one possible basis there. You can't possibly have a preferred basis problem. The emergence approach, I think, takes on some of the advantages of both of these routes. The emergence approach shares with anthropocentricism the I think, important insight that at least some characteristics of the quantum formalism probably reflect special features of human observers rather than necessarily inherent features of the systems we are trying to describe. In this case, the special feature that's relevant is our size. It's the fact that we are large systems, which allows us to arrive at the quantum formalism relative to us. If we were a different size of system, we would get a different kind of formalism. On the other hand, the emergence approach also shares with universalism the idea that human observers shouldn't be privileged in the formulation of the theory. Human observers are just going to be some limit. The quantum formalism is going to be some limit of the theory that emerges in that appropriate limit. So we don't, in that sense, have to treat human observers as sort of special or fundamental. Okay, so whether or not you think the emergence approach is interesting, I hope I've at least convinced you that this is an important question to address in setting up a relational theory, and that there are a variety of options for how to think about what quantum descriptions should be relativized to in that context. The next question I want to ask is about the nature of the relationality. In particular, is the relationality of quantum mechanics inherent or effective? So what I mean by effective is for types of relationalism where we say there is always an absolute underlying quantum state, but in some situations it's appropriate to write down an effective quantum state relative to an observer or a branch or something like that. So that's the kind of relativization that we have in Everett and de Broglie-Bohm and so on. In their standard formulation, those views do have an absolute non-relativized underlying quantum state, but they just also have relative states that are appropriate to use in some context. That contrasts with the inherent approach. In the inherent approach, we say quantum states are inherently, by their very nature, relational. What a quantum state is a description of how one system relates to another system. So from that point of view, it's kind of a category error to write down an absolute non-relativized quantum state. It doesn't make sense to do that. So that's what relational quantum mechanics says, what various neo-Copenhagen approaches say. Plausibly, we should think of cubism and various pragmatic interpretations as saying that too. So there's a sort of disagreement here on the nature of the relativization and the extent to which that spreads across all of quantum. So which of these approaches should we take? I think there are good reasons to take the inherent approach quite seriously. The worry I have about the effective approaches is that they're sort of committed to saying that the theory has two quite conceptually different modes. There's sort of the underlying absolute mode in which states are not relativized to anything. And then there's the relational mode in which states are relativized to branches or de Broglie-Bohm particles or observers or whatever it might be. Moreover, in general, in these views, it's only the sort of universal quantum state, which is absolute. States of the individual entities we deal with in the laboratory are always going to be relational, i.e. relative to the branch in Everett. So all of our actual experience of quantum states with things we have done in the laboratory is going to be with relative states and not with absolute ones. Moreover, there's this nice result by Chen and Tumulka showing that there's really significant epistemic barriers to knowing really anything at all about the universal quantum state. Under those circumstances, you might think, do we really have any good reason to posit an absolute mode? In some sense, that's a really significant extrapolation of the theory beyond anything we have been able to interact with or test. Maybe we're sort of making this absolute in a way that isn't actually justified by the experimental situation. So for that reason, I think we should at least take seriously the idea that given that we have always dealt with these relational quantum states, maybe quantum states are just relational. That's what they are, and that's what they mean. We shouldn't be using them in an absolute way. think there's also motivation for that view coming from the gravity side. In particular, obviously, if we're thinking about relativization of quantum states as being in some way analogous to the relativization of variables in terms of relational observables, in the GR context, those intrinsic properties like charge, spin, position are always relativized. They don't have a separate absolute mode where they are non-relative. So if then that's the motivation here, then presumably quantum states should also always be relativized. They should be understood as inherently relational. There's also plausibly some worries with the notion of a global state in terms of what it's defined on and whether that has to involve picking out a preferred reference frame. And then there's worries coming from the fact that when we do canonical quantization, of course, we run into the problem of time. We plausibly can't have a global evolving quantum state anyway. In that case, it seems that we're sort of forced to move towards local relational descriptions in any case. So again, that's a reason to think that maybe we should always have understood quantum states in this relational way, and we should understand them as being relational by their very nature. Great. The next question I want to ask is about what does it mean to relativize a quantum state? In particular, what is being relativized here? Is it facts or dynamics that are being relativized? So suppose that I say the state of S is psi A relative to some system A, and the state of S is psi B relative to some other system B. What am I actually asserting there? So there's, again, two sort of rough schools of thought in the literature about this. One is what I'll call the facts-based view, which says that what this means is that the facts about S are themselves relativized. So facts themselves are relative in a sort of metaphysically strong sense. There's no underlying absolute description of S or the relations in which it stands or anything like that. All we have in this situation are a bunch of relative facts relative to different systems. The contrast, that includes views like RQM in at least its standards form and certain Neo-Copenhagen approaches. Contrasting approach is what I'll call the dynamical view, where we say the fact that we have these two different states is just saying that the dynamics of the interaction of S and A is different from the dynamics of the interaction of S and B, and so the predictions for the outcomes of measurements performed by A on S are different from the predictions for the outcomes of measurements performed by B on S. So in the sort of dynamical view, all we're really saying when we relativize things is taking note of the fact that different observers can have different dynamical interactions with the same system, because they are entangled in different ways with the target system, and so we have to use different states to capture different dynamics. So that's the kind of relativization that we see in Everett, for example, and de Broglie-Bohm. Neither of those views have relative facts in any sort of metaphysically strong sense. They just have dynamics that vary in different situations. So which of these views should we prefer? I have a lot of worries about the facts-based view. One worry about the facts-based view in particular is that it does sort of inevitably seem to push us towards a regressive relativization where we end up saying that everything is relative. So the reason for that is, suppose we relativize, say, spin. We're going to say the spin of system S is +1 relative to system B. You can then ask, okay, is that statement about the spin of system S relative to system B, is that itself relativized to anything? And if it's not relativized to anything, then it's very tempting to say, well, the real facts are just facts of the form, the spin of system S is +1 relative to system B. No facts are really relative in any metaphysically strong sense. It's just that some properties that we might have thought were intrinsic are in fact relational properties, and we have to make sure we keep that in mind as we just sort of think about how to state those facts. So if one is really committed to saying that, no, the facts themselves are relative in this sort of metaphysically strong sense, one will probably have to insist that the spin of system S is +1 relative to system B is itself relativized to something, and then that relative statement will itself have to be relativized to something else, and so on and so forth. So it seems quite hard to avoid this conclusion that if you really want facts themselves to be relative, you have to keep relativizing forever. You can't have underlying absolutes. So we end up with a situation where we have to say everything, in fact, is relative. That brings me to the last question I wanted to ask, which is about where is the line between what is relativized and not relativized? So the facts-based views tend to say, well, there is no such line. Everything is relative. We don't have to make a distinction here. I have worries about that because it makes these kinds of approaches quite non-obvious when we're trying to actually apply them to any particular experimental situation. And that's because given any practical experimental scenario, if we want to use a relational story to make some predictions, we're going to have a concrete framework for deciding what are we going to relativize and what are we not going to relativize while making that prediction. So for example, in the Wigner's-Friend scenario, the standard relational account of that scenario says that we should relativize the quantum states, we should relativize the quantum measurement outcomes, We shouldn't relativize the description of what experiment is being performed. So it's assumed in the setup that Alice is performing a certain measurement, that both Alice and Bob agree that Alice is performing this measurement. They know that that's happening, and that is a fact that is in some sense shared between both of them. So in order to make a prediction, we have to have that. We have to know what facts are being treated as shared between them, what facts are being treated, at least for the present, as absolute, versus which facts are going to be relativized in the course of that calculation. Now, we can maybe hand wave this away in the context of sort of fairly obvious cases, such as the Wigner's friend scenario, because there we have an intuition about what result we expect to see, and we can kind of choose what to relativize to produce the results that we want. But this has become more pressing in sort of more novel applications when we maybe don't have as strong an existing intuition for what the results are supposed to be. So for example, there's this really interesting recent paper by Hausman and Renner, where they argue that the black hole information paradoxes are really just examples of Wigner's friend paradoxes. And as part of that, they propose a relational resolution to one of the black hole information paradoxes. And their relational resolution requires that, in addition to relativizing quantum states and quantum measurement outcomes, we also have to relativize to an observer the fact that the evolution of the fields outside of the black hole is a typical unitary. So I don't have a strong feelings about whether we should or should not relativize that sort of dynamical fact. But the point is that is sort of a significant extension beyond the idea of just relativizing states and outcomes. And it's sort of not obvious to me how you would know prima facie, just looking at that situation, that that particular fact about the dynamics should be relativized, even though other facts about the description of the situation are not going to be relativized. So all of that is to say, to actually apply a relational theory to that kind of situation and predict something, I need to have a fairly concrete framework to tell me what am I supposed to relativize and not relativize in the course of the calculation that I'm going to do. So I think the fact-based views tend to have a problem with this. If you really want to say that all facts are relativized, it's not obvious how you would provide a sensible framework for deciding what I should relativize and not relativize in the context of a specific calculation. So these approaches seem to me to be quite difficult to actually apply in any actual case outside of the obvious paradigm cases for which they have been designed. The other main concern I have about the fact-based approaches is to do with intersubjectivity and the connections between different observers. The worry here is that if everything is relativized, then there cannot possibly be any absolute fact of the matter about the relationship between your observations and my observations. In particular, that means that if I have a conversation with you and I try to tell you about the results I have obtained in my experiments, it's not true in an absolute sense that we succeed in communicating. It might be true relative to some reference frame that we succeed in communicating, but not in an absolute sense. That to me is worrying because, of course, the practice of science does rely very crucially on sharing information with other observers. The objectivity of science, I would argue, owes much to the practice of sharing between observers, and thus any interpretation of quantum mechanics which doesn't allow us to share in an absolute sense our information with other observers seems to me to be kind of internally inconsistent and self-undermining. It's undermining the very methodology that we have used to arrive at quantum mechanics in the first place. So from that point of view, the sort of purely first-person, single-user views of quantum mechanics just seem to me to be misunderstanding like the nature of scientific practice and the way in which quantum mechanics has been arrived at. This theory, which was arrived at by the whole community, for the whole community, just could not possibly be a purely single-user theory. It's not the kind of thing you could get out of that kind of process. So that, I think, is a reason to be wary of these fact-based approaches, because they do seem to push us towards a sort of very first-person way of thinking about the theory. I'm going to go through a couple of responses that I sometimes receive when I make this point. First response, is it enough to just say that Alice and Bob can share information relative to some other observer, Chidi? I think not, because if I am Alice, that's really no help to me at all. The fact that there are some facts about my relation with Bob relative to some other guy really is no use if I'm trying to, from my own point of view, make some inferences about what Bob has seen. For example, I want to know whether Bob has seen regularities similar to those that I have seen. What I want to do is to be able to listen to Bob and feel some confidence that what he tells me reflects the real regularities we've really seen. The fact that there's some relation between us relative to Chidi doesn't really seem to help me with that at all. In particular, the relation between me and Bob could presumably be different relative to different external observers. There doesn't seem to be any obvious way to decide which one of those different relations I should use to make inferences about what Bob has seen. It's also not obvious that I can even find out what those relations are relative to other external observers. So from Ellis's point of view, this kind of fact relative to Chidi doesn't seem to help with the problem at all. Our next question, can't we just use the facts about this relation relative to Ellis? Can't we just say it's true relative to Ellis that Alice and Bob have succeeded in sharing information, so no problem? The problem with that view is that it kind of isolates Alice in this island of her own facts. Sort of she, by construction, has no access to anybody else's facts. She will only ever learn about facts that are ultimately relativized to her. In particular, that means she's never going to have any grounds to empirically confirm a theory which seeks to describe facts relative to other observers as well. She could never have any reason to think that Bob sees regularity similar to her. She could never have any reason to confirm a theory like quantum mechanics, which is trying to describe things that are true for all observers and not just for Alice. Final question, what if the relation is just invariant across everybody? I think it probably should be, but I think if it is, then it's not relativized after all. In that sense, it's somewhat absolute facts, and so we're not in the regime where everything is relative anymore. We're looking at another kind of approach, which is more dynamically relativized. Okay, so for those reasons, I think we should be looking to make a distinction between what is relativized and what is not relativized. There should be some kind of fact which we are willing to sort of put a stake in it and say this type of fact is not relativized. And as a matter of fact, there is a natural way to answer this question. The approach that's already taken within the relativization in the context of DR and also within the quantum reference frame formalism, and it's to link the quantities that are relativized to physical symmetries. In both of those formalisms, the facts that are relativized because they are facts which are not invariant under transformations which are considered to be symmetries of the theory, and therefore they have to be stated relative to some external reference frame in order to be meaningful. So that is a sort of a natural way of thinking about what should and shouldn't be relativized. It provides us with a way of making that distinction in a principled way. And I'm now going to argue that it also potentially offers an interesting new way of thinking about extended Wigner's-Friend scenarios. Okay, so I talked earlier about the original Wigner's-Friend scenario, that in recent years that we have seen the emergence of a variety of extended Wigner's-Friend scenarios in which we put together a few different Wigner's-Friend experiments and draw some conclusions by showing that certain assumptions about those experiments are incompatible with the predictions of quantum mechanics. I'm going to talk about the Bong et al. Paradox, which Eric already talked about a bit on Friday. I like this one because it's a first-person paradox, whereas the others are more third-person in nature. What I mean here is that many of the other paradoxes rely on the assumption that quantum mechanics is always correct on any space-like hyperplane, whereas the Bong et al. Paradox just requires us to assume that quantum mechanics is correct as applied by any one observer. It is, I think, a stronger result and more constraining in that. So to set up that paradox, we're going to have our friends Alice and Chidi performing measurements on two halves of an entangled 2-qubit state. And our friend Bob is going to keep Alice's laboratory in a coherent state and perform a measurement on it. And meanwhile, our other friend Divya is going to keep Chidi's laboratory in a coherent state and perform a measurement on it. So 4 measurements are made there. We have 4 variables, A, B, C, and D, which are obtained in the course of that experiment. Now, the important move here, which allows us to make this into a first-person paradox, is to say, well, presumably Bob could choose either to perform the measurement and get the value of B, or he could just give up on the experiment, go into Alice's lab and ask her what she saw. And in that case, presumably he would learn the value of A instead. So it's natural, therefore, to say that Bob has the option to learn either A or B on any run of the experiment. And meanwhile, Divya has the option to learn either C or D on any run of the experiment. And then afterwards, of course, Bob and Divya can talk to each other and compare their results. So in conclusion, Bob can, on any run of the experiment, Bob can learn the values of any one of these pairs here. He could learn BD, BC, AD, or AC. So if we expect that quantum mechanics is universally correct in a first-person sense, whatever Bob sees must be consistent with the predictions of quantum mechanics. Moreover, if we don't allow retrocausality and we don't allow superdeterminism, then presumably the probability distribution for the results obtained by Alice and Chidi can't depend on the choices made later by Bob and Divya about whether to find out B or A or whether to find out C or D. So we conclude that the distribution over the 4 outcomes A, B, C, and D is going to have to reproduce the pairwise predictions of quantum mechanics for all 4 of those pairs all of the time. And the punchline is that this can't be done. If we assume locality, no retrocausality, and no superdeterminism, there is no distribution over those 4 variables, which will reproduce the pairwise predictions for all 4 of those pairs all of the time. Okay, so what are we going to do about this? Obviously, one way to resolve it is just to allow retrocausality or non-locality. That solves the problem in a fairly straightforward way. But suppose we want more specifically relational solution that's taking into account some of these relational ideas. A lot of discussions around this paradox have involved the suggestion that we should deny an assumption that's called absoluteness of observed events, which says that an observed outcome is a real single event, not relative to anything. We deny absoluteness of observed events. We can just deny that there exists any probability distribution over A, B, C, and D, so it doesn't matter that we can't make that distribution consistent with quantum mechanics. So one way, of course, to deny absoluteness of observed events is just to adopt the Everett interpretation. The alternative seems to be to adopt some kind of fact-based relational approach where we say the fact that some observation has been made is itself relative to someone, and therefore there are no absolute facts about the relations between what's been seen by these different observers, and so there's no well-defined probability distribution over them. So as I've already discussed, the fact-based relational approaches seem to lead to some quite severe epistemic problems. For me, that's reason enough to say that's not a viable approach and we shouldn't do that. Even if you don't believe that, I hope you can at least see that this is quite a radical step. This is probably something we should avoid doing unless we really have to, and so we should potentially be thinking about alternatives. So I think there is an alternative which is sort of influenced by these ideas about symmetries and their role in deciding what should be relativized. So for concreteness, I'm going to suppose here that the measurement that's being performed is a spin measurement. So concretely, what Alice is doing is she's taking the particle that she has in her laboratory, and she's comparing the direction of its spin to an axis that she has in her laboratory. So I'm going to suggest, therefore, that what happens here is that when Alice does her measurement, it is a well-defined absolute fact of the matter about what she saw, in the sense that she either found the spin to be parallel to her axis, or she found it to be anti-parallel to her axis. But there is, at that time, no fact of the matter about the orientation of Alice's axis relative to Bob's axis. The reason that is plausible, I think, is because in order for Bob to perform the measurement to obtain the value of B, he has to isolate Alice very effectively from her surroundings. I think it's therefore possible to suggest that Alice could therefore lose her alignment with the external reference frame. So although, of course, Alice would start out with a shared orientation reference frame with Bob, once she's been isolated from the environment, and perhaps when she measures the particle, at that point, plausibly, she can lose that alignment, and at that point, there's no shared reference frame between Alice and Bob. So at that point, we have a well-defined fact about what Alice has seen, but we don't have a well-defined fact about the direction of that spin relative to Bob's external reference frame. That allows us to disambiguate a little bit the meaning of these variables that are used in the derivation of that paradox. So we have those four variables, A, B, C, and D. What exactly does the variable A refer to? Well, A could refer to what Alice has actually seen in her laboratory. So it could be what I'll call AI, which specifies either Alice saw down relative to her axis, or Alice saw up relative to her axis. That's a variable describing the observation that she has made internal to her laboratory. Alternatively, A could be the variable AE, defined within Bob's reference frame, which describes the direction of the spin relative to his reference frame. That combines the facts about what Alice saw in her observation with facts about what direction her axis is found to point in later when Bob shifts the direction. So in particular, if Alice sees the results up relative to her axis, and if that axis is then found to be aligned with Bob's axis, AE is going to be up. Whereas if Alice sees the result up relative to her axis, but then the axis is subsequently found to point down relative to Bob's axis, AE is going to be down. So finally, I'm going to suppose here that Alice's axis in this situation comes to have a well-defined orientation relative to Bob's axis, only in the case where Bob actually checks. So he goes and he talks to Alice and asks her her result and finds out the value of A rather than measuring to find out B. So the thought here is that the variable AE is only going to exist on runs when Bob does not find out the value of B and instead finds out the value of A. What then does the idea of absoluteness of observed events require in this situation? Well, because the point here is that things which have been observed should be absolute, seems to me that absoluteness of observed events should be understood as requiring a well-defined probability distribution across AI, B, CI, and D. That's what is relevant in terms of observation. That's what's relevant in terms of the epistemic concerns I talked about previously. But the distribution across A, I, B, C, I, and D can't be compared to any quantum predictions. because quantum mechanics only makes predictions for spins measured relative to a common space-time reference frame. And here, AI is defined in such a way that it doesn't share a reference frame with B and with C. We can't make any comparisons with whatever quantum mechanics predicts here. And we can, of course, compare A, E, B, C, E, and D to the predictions of quantum mechanics, because those are all defined relative to the same external reference frame. But there is not necessarily any well-defined probability distribution across those four variables, because by construction, AE comes to exist only on runs when Bob does not obtain the value B. So the thought here is that by making that distinction between AI and AE, we can have a situation where no quantum predictions are violated, but nonetheless, we get to keep absoluteness of observed events, in the sense that there is always a well-defined fact of the matter about what Alice saw, and if Bob asks her, he will find out that fact. So we can sort of motivate that description by thinking about the relevant symmetries of the situation. So in particular, the thought here is that to take account of the fact that when we have symmetries that apply to the whole theory, those symmetries are not going to produce meaningful change if we apply them to subsystems, and we're looking only from the point of view of that subsystem, but we can see a meaningful change if we are looking from the point of view of an external subsystem. So in particular, a variable of the subsystem which is changed by the transformations belonging to the symmetry group is not meaningful when we consider that subsystem in isolation, but can still be meaningful when compared to an external reference frame. So in this case, because I conveniently chose spin as my thing we're going to measure, we can be dealing with the rotation symmetry. The theory is presumably subject to a rotation symmetry, so rotations of Alice and her laboratory in totality isn't going to change the internal state of Alice and her laboratory. And presumably won't change anything from Alice's point of view. Everything will look the same for Alice inside her laboratory. We rotate the whole laboratory relative to the external reference frame. So in particular, a fact like Alice has seen the spin pointing parallel to her axis, presumably lives in the invariant subspace with respect to the rotation group. Rotating the whole lab is not going to change that fact. But of course, rotations of Alice's laboratory are meaningful with respect to Bob's laboratory. We can imagine a superposition like the one that I've shown here. So here, P and P prime represent states of Alice which are internally the same, but which are different relative to Bob. So I'm going to suppose they represent states where Alice has observed the particle to be parallel to her own axis, but they have different total orientation relative to Bob. So these two terms in the superposition are different from Bob's point of view. They have different total orientation, but they're the same from Alice's point of view. They correspond to the same internal state of the laboratory, and they presumably would correspond to the same conscious states for her. So that suggests perhaps a different way of describing what happens in this Wigner's-Friend interaction. For the standard description of that measurement, it supposes that we start out with the superposed state, and then after the measurement, Alice is in a superposition of seeing up and seeing down. But perhaps we can suppose that instead what happens is that we get the state shown here. That is, in some way, probabilistically, Alice either sees up or down in that measurement. After the measurement has taken place, she's in a well-defined state of seeing parallel or seeing anti-parallel, but the overall state relative to Bob is still a superposition in the orientation variable, because we have two different possible total orientations of Alice relative to the external frame. So in this case, there is a well-defined fact about what Alice saw, and Bob can measure the invariant subspace and find out that fact, so he can learn the actual result of her measurement. But if he performs quantum experiments on the orientation variable, he's going to see quantum interference and reproduce the usual quantum predictions. We still get a sort of standard unitary description in terms of that orientation variable. We just have to be careful about the difference between Alice's orientation relative to Bob and the internal facts about Alice that aren't changed by that rotation. So that's just a sort of a brief sketch of what it might look like to apply this idea about symmetry to the Wigner's-Friend case. But I think hopefully we can sort of see that there's some interesting ground to be covered in terms of taking seriously this idea that the variables which should be relativized are the variables associated with symmetries. As I say, that is exactly how it is already done in GR and in the quantum reference frame formalism. Symmetries are very central to the quantum reference frame formalism. For some reason, that hasn't really carried over into the way that people think about relational quantum mechanics and various relational interpretations. But I think there's some really interesting ground to be covered here in terms of taking the idea seriously and thinking about what it might mean for the interpretation of quantum mechanics. In particular, if you look at the story I just told, it sort of seemed like what happened was that we're sort of denying the principle of universal superposition. It seemed as though there's some kind of idea that the internal variables of Alice's laboratory can't be superposed in the same way as the orientation variables. That would need to be worked out in more detail, but I think that's potentially an interesting thing to think about in terms of the future development of relational approaches. Great, so to sum up, there are good reasons to think that at least some quantum descriptions are necessarily relativized to something. There are a large number of choices to make about how to implement that relativization. We should think carefully about all of these choice points. We should be wary of jumping straight to established positions or to the most radical approach. For what it's worth, my preferred answer to those questions is the emergentist approach, inherent approach, dynamical approach, and appealing to symmetries of the theory to decide what specifically should be relativized. So I've plotted a couple of those distinctions on this table. I can only do two-dimensional tables, so we only have some of the distinctions. But here we have effective versus inherent and fact-based versus dynamical. You can sort of see how some of the existing views fall into those categories. In particular, as I've just said, my preferred box here is the inherent dynamical box. As you see, there's not all that much in that box at the moment. I take that as an invitation to develop this view and these views a little bit further. I think there's some interesting possibilities to be explored in that box that perhaps haven't been pursued as far as they could be. And more generally, I think there are a lot of interesting ideas about relational approaches beyond the sort of standard well-known approaches that we should be exploring to sort of see what the full potential of this approach is. So that's it for me. Thank you very much for listening, and I appreciate very much.
Thank you very much.
Thank you. Very interesting. So, so in general relativity, you talked about that as a sort of motivation for this relational program. Although in general relativity, the variables, if you like, are well determined. They're properties which are invariant and general coordinate transformations or homomorphisms, and everyone agrees what they are. They're not relative to observers. Those are just facts about the world.
Oh yes, but I mean, some of those properties are relational observables. There's certainly a layer of underlying absolute facts, which is what I think we should do with quantum mechanics as well. But certain kinds of properties that we would normally think of as being intrinsic turn out to be relational properties.
But any sort of thing we might write down in a lab book coming from general relativity would be one of these sort of absolute facts, which are I think properties which are invariant under diffeomorphisms.
Well, anything we'd write down in a lab book is usually going to be a partial observable. So a partial observable is like half of a relational observable. So partial observables themselves are not really invariant. That's the relational observable.
As an example, we might have, well, I mean, even things we might not write down, but we might have like two fluid particles intersect here, another two fluid particles intersect there. So those are both absolute things. And then also there's the extremal distance between those intersection points. That might be a more non-local thing, but it's also an absolute fact. It's not. And then that kind of approach. So one approach is the thing that I've been doing, which is to take so quantum coordinate system or quantum diffeomorphisms, and you can take that sort of that approach where you now sort of get a similar sort of thing in a kind of quantum context.
Right.
And I'm not sure if that fits into the thing one of the things you were describing, or because it seems to me this is a way of just establishing facts about the world that are not relative to a particular observer or particular person. Do you not agree?
Well, I mean, I think a lot of these facts are relational in the general sense, in that they describe relations between things. And I totally agree that those relations are not themselves relativized to anything else. And I think that's the right way to think about quantum mechanics as well. That quantum states might be relativized to things, but then at that point we stop. We don't keep relativizing forever. So the thought is that I think we should try to have a closer match between the type of relativization that we're having in GR and the type that is relevant to relational interpretations of quantum mechanics.
Okay.
Thanks. I'm worried that the resolution of the Bong et al. Paradox relies on the fact that we happened to use spin as our two-state system. I mean, in my system, there's something that was not symmetry related. So it's like if up reflects a cavity without a photon in, and down a cavity with a photon in, or up is the ground state and down is the first excited state of some atom, then it looks as if we don't need the reference frame to measure it. But presumably the paradox doesn't rely on spin algebra; it just relies on qubit structure.
Yeah. So I mean, influenced here by the quantum reference frame formalism, in which everything that you would consider to have all the superpositions which are considered associated with a symmetry group. And so there's some kind of claim being made here that like all meaningful superpositions in some sense can ultimately be associated with some symmetry like that. And I think there's a substantive question to establish whether that's true. I can believe it might be. I can believe that there would be a sense in which all of the things that we can experimentally produce now, that all the superpositions we know about, in fact, can be traced back to some symmetry group. For sure, I think that's a substantive question to decide whether that's really the case.
Yeah, I mean, just naively, if it is the case, it's only the case through some big reconstruction. Again, I could just imagine a cavity. I've got a cavity here with an arrow drawn on it, and another cavity here with a circle drawn on it, and I have a photon in one cavity or the other cavity, and at least in the normal sense of symmetry, there's no sense in which those are symmetry related.
Yeah, no, I agree. I agree that there's a lot of cases which are less obvious. With that said, in the reference frame formalism, a lot of things, when one starts to look at the way in which reference frames are used, a lot of things that seem like things like subsystem decompositions, for example, turn out to be relative to a choice of reference frame in quite non-obvious ways. So, I think a lot more work would be needed to establish this. This could work for any kind of superposition. But I think it's at least possible that it could be made. Okay, thanks.
My one actually relates to what David was. Go ahead, David. Yes, thank you. So I was going to make a similar point, I think, to what David was saying. Leading up to it, I was also going to, the version of the extended Wigner scenario you described. I think it had, I'm forgetting it in the names which was which. Is Alice doing interference on somebody?
Alice was in the laboratory. Bob was outside.
Bob is outside doing interference on Alice. And Bob is doing that every time. He doesn't have a choice of settings here, as I understand it, in this version of the...
Well, yes and no. I mean, and the thought was that he does do the same thing every time, but that he could do the other thing, and that's why there has to be a well-defined distribution from the first-person point of view. That's my understanding of the motivation there.
So, okay, perhaps I need to read this version because I didn't see how locality and superdeterminism and no retrocausality come into it. Well, because at least in the version of this where Bob just does the same thing every time, no one has any settings or choices, and it's just a mathematical fact that there is no joint distribution over the four that reduces to all the pairs.
There's sort of a branching path here. One option is to not give anybody any choices. In that case, you can derive a paradox without appeal to retrocausality and superdeterminism, but that will only work if you're assuming that quantum mechanics is valid across any space-like slice, even if nobody compares those results. Other alternative is to give someone a choice. Then you can do it from a first-person point of view, but then, of course, you do have to appeal to things like...
that's the distinction.
Those are those two options, basically.
I like the version where you don't even need to assume
any
of those things, because it just shows they're not going to help you.
Well, no, but from a relational point of view, that version doesn't really make sense, because the quantum state that predicts outcomes across a full space-like hypersurface, when nobody can compare those outcomes, can't be relative to anyone. There's no observer to whom that quantum state can be ascribed. So I think moving to a relational approach makes that kind of paradox seem less relevant.
Oh, I see. Okay. And then on the thing David was saying, yes. So you made it look all plausible by having spin be the thing.
Very conveniently too.
We kind of understand quite well about what it means to have a reference frame for a direction in space, and then two people might not share one. But you can sort of run the argument for any sort of observable. I was chatting with Eric the other day. You can make it quite extreme, and you're going to have to, I think, move to a quite extreme form of relationalism. It's not just about symmetries and spatial directions and things. It's going to have to be that, Eric was talking about writing down a poem about a cat as sort of one of the outcomes. This is something Alice does in her lab versus something else completely different happening. And it's going to have to be that there's no difference between those things except relative to some frame that Bob does not have access to.
In my setup, I was assuming that Alice only gets one result. So Alice always gets either the up result or the down result. So if we then asked Alice to write a poem where she sees the up result, either she does or she doesn't. It's not both. So I was denying the superposed that the two results can be superposed.
Well, but then I think the paradox trips you up.
How so?
And I think the only way relationalism can, for the simple mathematical fact that there's no joint distribution over four things.
Right, but there doesn't have to be if you make a distinction between what Alice has seen and the value of that thing relative to Bob's reference.
Perhaps I'll
got some other questions. Sorry, but I came out of the last iteration of this debate.
Just a quick,
Anthony.
quick question. Superb talk. Thank you so much. It's just a question that a couple of times I've put to Carlo Rovelli, and very well, great friend. And I think maybe you've given your answer, maybe implicitly, but look, like this, there is a super advanced alien, super technologically advanced alien, forms an interference experiment on the whole Earth.
Yeah.
And maybe there's some quantum event that determined whether I came to this conference or not.
Yeah.
And then relative to the alien, it is a fact that this conversation never took place.
Yeah.
This conference never took place. Perhaps we were never even born.
Yeah.
And I've asked Carlo, look, are you comfortable with that? That according to a super advanced intelligent alien, it is a fact for them that you were never born. Carlo didn't seem to have a problem with this. To me, it seems just, there's this primordial fact of, well, I know I'm here. It is a sort of starting point, some would say, for philosophical certainty. What would be your opinion about this?
Yeah, so I mean, I think Carlo is mostly attracted towards what I call the fact-based relational approach and towards the infinite regressive relativization. So for him, there's no absolute facts. I do not like the infinite regressive relativization. I don't think the fact-based approach is the right way to go. So I do think there does need, in some sense, be an underlying layer of absolute fact about relations or something. So specifically, what is contained in that layer of absolute facts is going to depend on the different formulations you could arrive at, and they're going to say different things about what the absolute facts are. So some formulations might say that indeed what you've described is still relative. Other formulations might say, no, this is an absolute fact. What I think is important for me is that there should be some layer of absolute facts, and that layer of facts should be in particular capable of supporting the kinds of purposes that we do in science to arrive at our theories. So I don't have a specific way of circumscribing exactly what those absolute facts should be right now, but I do think that there need to be some, and they need to sort of contain certain important facts about scientific methodology.
Thank you. Next time I see Carlo, I'll quote you on that. Thank you so much. Thank you.
Yeah, thanks, Emily. I think I have a really much better understanding of RQM now, so I appreciate that. But my question is really straightforward. I mean, is there another position I could hold on your grid here where I deny a universal wave function, but the reason that the wave function is inherently relative is not because it's inherently relative, but because the system it describes is an open system?
I guess I can see that, although I would argue if there never are any absolute states anywhere in the universe as a matter of fact, I'm not sure what meaning it would have to say that there could have been such things. If the universe as a whole is just an open system and that's why there's no absolute quantum state, then that sort of seems like an argument for the claim that in fact the quantum states are inherently relational. Okay.
As somebody who's been continuing to develop a relational interpretation, I thought I would say a few things about how it relates to what you said. First of all, there are two things that might be said to be relational: the quantum state and the outcome of a measurement. And for a long time, I thought that the first was relational, but the second was not. I finally became convinced that both are relational, but they're relative to different things. And neither of them is relational relative to an observer, whatever an observer is. And neither of them is relative to a physical system either, though they're both the wrong relata. And the right relata is something physical. It's nothing has nothing to do with us as observers, if we are or whatever. It has to do with something physically characterized, but not characterizable quantum mechanically. I call it an agent situation.
Yeah.
Okay. Now, given all that, I'm inclined to go ahead willy-nilly and solve these severe epistemic problems that you point out for a fact-based approach towards a relational view. And I think I've made some progress, but the progress involves denying that inherent relationality, which is invariant across actual agent situations, is thereby shown to be not really relational. I think it is relational. It's invariantly relational, but it's not because it's invariantly relational, thereby shown not to be relational at all.
I was claiming that that would mean it's not relational. I was claiming that that means there is an underlying absolute fact of some kind. So it's not the case that everything is relative.
No, I want to get rid of absolute underlying facts here.
I don't think you have if you've got something that's invariant across everything.
There are problems, but they can be solved. It's worth solving them because that's the right view you arrive at having solved them.
Well, I think if it's invariant across all agent situations, it is in that sense absolute. It's not related.
I don't like to use the word absolute. I say it's objective.
Okay, well, perhaps we
it's
agree.
Eminently
Using different words
objective,
then.
but it's not absolute.
Well, perhaps we're just using different words then to say the same thing.
The words actually matter here.
Well.
Okay, well, I think that was absolutely objectively brilliant, Paul. Thank you very much. Quick turnover, and John Barrett's about to give us the next talk. There's a fresh glass of water for you there, John. There's a fresh glass of water for you there. Great. I'm very pleased to welcome John Barrett, local hero, man who took the B in PDR. And he's going to talk about quantum causal models. Over to you, John. We're starting 5 minutes late, so I'm assuming I will give you a hand after 40 minutes. So we're starting at 10:02 rather than 42.
All right, thanks. Well, thanks to everybody for having me here. Thanks for the introduction, James. I'm going to talk about causality in quantum theory. I'm going to, well, say some things that lead up to quantum causal models. In a way, I'm not then going to sort of give a talk that's all about quantum causal models. At some point, I'm going to sort of veer off and say some things about, well, in the direction of interpretation of quantum theory. And I don't want to go as far as saying that I'm going to describe a new interpretation, but some ideas that, you know, I hope might be leading in that direction. So there's a much more important talk coming after mine by Nick Ormrod, which is also about those ideas. Hopefully some of what I say will be useful in kind of setting up some, you know, some theory and background and things. That will help with that. That's as well as the much more important talk
that we just had before, from Emily and all the other ones before that. All right. Now, does this change slides or is it just a pointer? Do I have to do that? Okay. No, don't worry. I'll just use the button. Causal models. There's a large literature on classical causal models, dating back, I guess, to the 90s. These days, there's an increasing interest in this literature from various communities. In my department, lots of sort of machine learning and AI type people do talk about this nowadays. Broad array of applications, whether it's automated medical diagnosis or whatever. Now, within the quantum communities, especially the sort of quantum information and foundations community, there's also increasing interest in this, and causality is quite the hot topic, with people sort of developing various sorts of quantum generalizations of these ideas. A lot of people have a sort of broadly operational, approach when they're doing foundations of quantum, and that means they've adopted sort of broadly operational approaches here. So just having, sources and allowing entangled states and looking at measurement outcomes and correlations and things like that. Bell's theorem being the kind of starting point. But generalizing in lots of ways as suggested by this classical work. However, I'm not going to give you a sort of survey or overview of all of that bit of the literature. Instead, I'm going to be hawking my own wares, I guess, and sort of talking about the approach I've been following. Because I think the sort of operational stuff, there's lots of good and interesting results and everything, but I think it misses some of the most interesting parts. Okay. And in particular, some of the most interesting parts for foundations. So even, the classical literature, one of the early people who developed this was Judea Pearl. He certainly had some stuff to say about the foundations here, as well as just doing statistics. So some foundational questions that are raised or perhaps have new light shed on them by this work. If A is a cause of B, what sort of thing are A and B? What does it mean to say that A is a direct cause of B? Causal concepts involve an essential way interventions by agents, or causal relations directed in time. What in the overall picture is ontic, that is factual and independent of the agent? What is epistemic relative to an agent's knowledge or beliefs? Okay. As with Matt Leifer, I'm not going to read that out, but you are. The talk's sort of in 4 bits. I might have to go rather fast through number 3 if time is pressing. I'm assuming finite dimensional systems throughout because, well, I don't know. I'm no good at maths, so it's all I know how to do really. So the first part is with some of this audience, I may be sort of preaching to the converted. I'm not sure. It's a sort of broadside against some of the community who take the more operational approaches, kind of talk about causal influence and signaling in one breath, and there's always agents involved and so on. I want to make a certain point, which we can is important actually in the classical literature on causal modeling. So this is completely classical, first of all. I'm just considering a scenario where I have sort of 3 quantities of interest. They're called X, lambda, and Z. I wonder why they're not on the actual circuit picture there. Anyway, Z is coming out at the top of F. X and lambda are going into it. Let's suppose these quantities of interest are just 2 valued, so they're bits. And they're related by a function, so some law or rule is governing them that just ensures that they satisfy this functional relationship. It can be emergent, it doesn't have to be a sort of fundamental law or anything. And the nature of this function is that Z is X plus lambda mod
2, or in other words, Z is the parity of X and lambda. Okay, now, yes, I see, Chris warned me about this yesterday. Maybe I should have checked, but certain symbols are not appearing on the PDF here. I'm not sure why that is, because they were on mine. Huh? Because you're running in PowerPoint. Is it? Is there an easy fix it'll take 30 seconds, or shall I just sort of proceed? Huh? Literally just open it in another viewer. Where is the file to open now? It looks like this. Can I just open with and then put something else? Let's try this. Sorry, I should have checked over lunchtime or something. Rotter. Oh, it's all right, I can find it again. Brilliant. That looks much better. So you can see just what I meant. Oh, for goodness sake. Okay, I'll say no, shall I? Very good, thanks very much. Right. Suppose that from some person's point of view, lambda is hidden. It doesn't need to be fundamentally hidden in any way. It might just be a bit hard to measure or something, or maybe they just didn't bother looking at it. So from their point of view, let's suppose they just assign probabilities half each to lambda being 0 and 1. Now we look at the marginal channel from X to Z. And having marginalized over lambda, we see that Z is just a random bit here. For each possible value of X, Z is random with probabilities independent of X. So there's a channel from X to Z here, and that channel is just one where, you know, the X, think of it as thrown in the bin, if you like, and Z just takes a random value. So certainly from the point of view of that agent who doesn't know lambda, there's no signaling from X to Z. But it would be quite wrong to say there's no causal influence from X to Z, because there is, you know, Z depends on X through this function. It's the parity of X and lambda. So independently of any agent here, it's just a fact that there's causal influence from X to Z. And this is an instance of what's called fine-tuning. Because of fine-tuning, there's no signal that you can send from X to Z. It's fine-tuning because it's that specific distribution on lambda that does this. Any other distribution, and we would see a signal from X to Z. Okay, so this is supposed to establish that, you know, causal influence should not be defined as signaling. It's very similar in the quantum case. This is a similar example. They're all qubits now. And instead of a function, I have a quantum C0 gate. For lambda, let's imagine that it's prepared in the following manner. Someone tosses a coin. If they get heads, they prepare the 0 state. Get tails, prepare the 1 state. Now, to a particular agent who's kind of knows all this is happening, but is unaware of the coin toss, they'll just assign a density matrix to lambda, which is a maximally mixed state ion 2. And from that agent's perspective, again, there's no signaling from A to C. At the output C, there is just a maximally mixed state, regardless of what is put in at A. It's fine-tuning again, because for other states of lambda, this wouldn't be the case. Again, there's clearly causal influence from A to C. Indeed, from another agent's perspective who knows the coin toss, a signal can be sent from A to C. So again, causal influence not the same as signaling, should not be defined by signaling. Signaling is an epistemic notion. Whether Alice can signal to Bob depends on what they both know. Or even in more general examples, what Alice knows about what Bob knows, and so on. Okay. So if signaling is an epistemic notion, what's causal influence, then I've asserted that there is some in a couple of examples. But what's a good notion of causal influence then that is distinct from just signaling through a general channel? Well, I'm going to argue as follows. Fine-tuned, unobserved systems can result in an absence of apparent signaling. But causal influence can be defined once all relevant systems are included in the description. So once lambda is in that description as well in the examples, you can sort of see that there's causal influence. So this means we're now dealing with a closed system, and at least in standard quantum theory, closed systems evolve unitarily. So we're going to define causal influence in terms of unitaries. And part two is how we do that. What's quite nice is on thinking about it, various possible definitions, present themselves for what it might mean for a given input to a multipartite unitary having causal influence on a particular output. But then it turns out that all those different notions are equivalent mathematically. So that I think is encouraging. It tells us that we've sort of hit on the right notion. Mathematically, seeing they're equivalent, it doesn't matter which one you choose for a definition. Conceptually, there may be a reason to sort of prefer one of them and make that the definition and have the others as derived statements. But I'm not going to sort of take a strong position on that. A bit of notation here that's going to be useful for us. Suppose we have a quantum channel with input A and output B corresponding to a CP map E. I'm going to make use of Choi-Jamalkowski operators for representing channels. So that's how one of those is defined, like this. So I write it as rho of B given A when it's a channel from A to B. That's an operator on a tensor product of two Hilbert spaces, but it's one way of representing the channel because there's this isomorphism between them. That's how it's actually defined. Defined this way, it's a positive operator. Trace out B, we're left with identity on A. Okay, now here's a definition. We're actually defining does not influence. So for a generic bipartite unitary U, it's got inputs A, B, and outputs C, D. Suppose that for all possible input states rho B, it turns out that the marginal at the D output is independent of which state we prepared the A input. Equivalently, in maths, that statement corresponds to that condition there. That if I start with a Choi-Jamalkowski operator for the whole unitary channel and trace out C, because let's just say we're not interested in it for a moment, if when you do that, what you're left with is just a channel from B to D, sort of tensored with the identity on A, that's equivalent to this statement here. And we're going to say in that case, A does not influence D. So it sort of means that you can never send a signal from A to D. And that holds no matter what you prepare at B. So for any choice of preparation at B, there's no signal from A to D. That means A does not influence D. Yeah, a bit of notation. When A does influence D, let's draw an arrow, a sort of double arrow like that. Now, there's a theorem that's going to matter now for a lot of what we carry on to do. I'm always trying to think of a name for it, and I sort of never can. So it's just called the big main super important theorem for any discussion of quantum causality. Or the boom, yeah. I feel I wanted to rearrange the words a bit and have it spell something rude, but I can't. It sort of says bumsit fadop at the moment. We'll call it that. It's a theorem about these Choi-Jamalkowski operators. Suppose I have some unitary with K inputs and N outputs. So it seems it's unitary, of course, the total dimension of the input has to match the total dimension of the output. But otherwise, K and N might be anything here. Suppose for a particular output, BI, let's define the subset of the inputs that influence that particular output, have causal influence on it according to the definition we had, and denote those PA subscript I, PA for parents. So I'm thinking of them as the parents of the I, that's the subset of the inputs that do influence it. Okay. Well then, if we write down the Choi-Jamalkowski operator for this unitary, turns out to be a product of terms, one term for each output. So a row term for B1, a row term for B2, and so on, where all of those commute. And each of those terms is of the form of a Choi-Jamalkowski type of operator for a channel into that particular output, but just coming from its parents. Okay, there's a convention here, which I always do. If I look to be taking a product of operators that seem to act on different Hilbert spaces, it means you pad with identities to make it well defined. Okay, so why is this theorem important? There are two immediate consequences from it. One I'm calling causal atomicity. Suppose that AI does not influence an output Bj and not an output Bk either. Well then, if we group Bj and Bk together and talk about the composite thing, imagine if you like an agent at the output doing kind of possibly joint measurements on J and K, then it'll follow that AI did not influence the composite either. This is true for unitary channels. I've just said it follows from that theorem. It's trivially true for classical functions. It's not true in general if we were discussing something else like signaling through a general CP map or a classical stochastic map, because you can signal to a pair, like write a signal into their parity or something without signaling to either one individually. But this causal atomicity, it does hold the causal influence through unitaries. And it has a certain kind of nice consequence, which is the causal structure of a unitary can be completely specified by these parental sets, or equivalently by just drawing arrows from inputs to outputs. For each input, I just draw arrows to those outputs that it does influence. And I can do this simply. If it weren't for this causal atomicity, I'd have to consider all the arbitrary subsets of inputs and outputs and whether they influence each other, but we don't have to do that. Everything to be said about the causal structure of this unitary can be just drawn with one kind of simple bunch of arrows like that. Now, another consequence of some of this is I'm calling causal reversibility. Suppose I have a unitary with a causal structure a bit like that. I've just argued you can draw it with arrows. To get the causal structure of the inverse of that unitary, you just flip the arrows. Okay? So yeah, much as it says, now we're talking about influence from B's to A's. I just flip those arrows, that's the causal structure of U minus 1. And in case you're thinking that this is somehow obvious, it's not true for classical reversible functions. And it's stronger than the mere claim that unitaries are reversible transformations in the familiar sense. I think it's probably true for classical sort of symplectic maps on a phase space. But yeah, not for just for sort of generic classical reversible functions. The classical C0 is actually a counterexample. Some of this work, we had a paper with, I got a rather sort of grumpy referee report. The one Nick's going to talk about. It said at one point, in reference to this, I was present, the referee said, at a conference where one of the authors spoke about this. So it would have been me. And this point was discussed ad nauseum. I would ask, please don't ask too many questions about this aspect. I'd hate if the referee is in the room for actual vomiting to happen, just because of something that I said. All right, now we can build on these ideas a bit and talk about causal influence, not just from inputs to outputs of a given unitary, but at different stages of a unitary process. So here we have what is supposed to be a sort of fairly generic picture. It's got some stuff coming into it, just labeled with lambdas at the bottom, at the beginning, from the past, something. and stuff going off at the top labeled with μ's. At these intermediate times, we have unitary evolution, U1, 2, 3, 4. I've drawn this to be general, so I've drawn it so that U1 stretches across all the systems, because it might. But of course, in a particular circuit, we may have that U1 only acts on a couple of these, and U2 on a couple of the others, and so on. Kind of most generally, you can draw it like this. Now, here's how I'm going to talk about causal influence sort of inside a process like this as the process goes on. I'm going to identify some of the wires as points that I'm particularly interested in. So it's not that anything special is happening there, other than just there's a system and the unitaries I've already drawn are happening. I've just decided to be interested in a particular system at a particular moment. And those places I've broken the wire in my picture, and I've given them labels. You can see A, B, C, D. Those breaks, I'm going to call them quantum nodes. It corresponds to a locus within the overall process. Now, often people, when they're doing this sort of formalism, they talk about an agent saying that they will intervene at that node. And that's one way, I suppose, an agent Alice could decide to intervene and do something extra at that location A there. But I'm not emphasizing that part because I don't want the agents to be, any kind of important part of this story. So, it's not important that I discuss an agent doing something there. It's just a locus within the circuit that we're interested in. When I make that cut in the wire, mathematically, it's associated with two Hilbert spaces. I'll label them HA in and HA out for the node A. If someone were intervening there, doing something extra, it would be a map from HA in into HA out, for example. Or you could think of HA in as associated with the bottom little dangly wire bit just below A, and the other one with the top bit. Now, in the literature where people do kind of study this, the whole thing is what people call a supermap or a quantum comb. In this particular case, a unitary one. So one way of representing it is with a positive operator that's defined on all of those Hilbert spaces. Now, I want to talk about causal structure. So for this, I'm going to stretch the wires, and this doesn't correspond to anything. In reality, it's just something, I'm doing something to the picture. Okay. It's just, okay, I've decided I want to draw it this way, so I have. You'll see that for each node, like A there, the wire which is carrying on, going up, which corresponds to a Hilbert space, A out, HA out. That wire is pulled down here, so it's ended up at the bottom. Whereas the other thing corresponding to the Hilbert space, HA in, that's been stretched and pulled right up to the top. That's why A in is right up there now. And so we do this with all of them. So we've got all the outs at the bottom and all the ins at the top. And the reason I did that is because now we can say this, that whole picture there, which has got these Hilbert spaces at the bottom, the lambdas and also these A, B, C, D out, and at the top, the mu's and A, B, C, D in, corresponds to some big unitary transformation V, just mathematically, I mean, that is a transformation from those output spaces and the lambdas into the input spaces and the mu's there. And now we can talk about causal influence between these nodes, because for a given node X, where X might be A, B, C, D in this example, or one of the lambdas, it's a direct cause of another node Y, where again, Y is A, B, C, D, or perhaps one of the mu's, if and only if X out causally influences Y in through that unitary V. And we've already defined what that means. Okay. It follows from causal atomicity that the causal relations can now be represented just by drawing arrows. So they correspond, in fact, to a directed acyclic graph. much as the way we represent them in the traditional classical literature on causal models. So there's an example, it might have turned out like this in this case. Where those arrows are, it depends what these unitaries are. You can't just read it from a picture like that. It depends what the unitaries actually are. So that's what it might have looked like. Yeah, from the causal symmetry, you can consider the inverse process as well, and it will have a causal structure, and you'll get it just by flipping those arrows, which is kind of neat. Okay, and now some conclusions. That sort of concludes the first half of the talk, although I guess the second half will be shorter. Relata of causal relations in this approach are nodes. So these are answers to some of those foundations questions we started off with. And these nodes are loci within an overall unitary process. A compelling account exists of what it means to say that A is a direct cause of B. Nothing in the account of causal relations here involves an essential appeal to agency. The causal relations are time symmetric. Asymmetry does come in when we consider agents who are reasoning about the ontology, because they'll bring in asymmetry when their epistemic situation with respect to the past is different from their situation with respect to the future. I mean, it's not true that we know the past and we don't know the future. We predict many things about the future, but we know it pretty well in some ways, and there's lots we don't know about the past, but still, there's a difference. So agents bring in asymmetry. All right, now, I think I do want to get to the sort of interpretationally bit. So I'll make sure not to spend too long on this part. I've written Uber theorem. That's what I used to call it. That should say whatever it was. The commutation of the operators in that thing induces tensor factor and direct sum decompositions of Hilbert spaces in interesting and intricate ways. So, bipartite unitary here. Suppose A1 does not influence B2 and A2 not B1. It's immediate from that thing, the theorem that I don't know. Big main and super important theorem for any discussion of quantum causality. It's immediate that in this case that U can be written as V tensor W, which is kind of neat because when you draw it that way, it's explicit from the picture that A1 does not influence B2 and A2 not B1. Okay, now let's have a slightly more involved example. This is a tripartite unitary. We'll just impose these things. Suppose A1 does not influence B3 and A3 not B1. Sometimes in conversation, I call this the Reichenbach example because it means that A2 is a complete common cause for B1 and B3. It's the only thing that has causal influence on both of them. And then you get a sort of quantum statement. That is a kind of quantum statement of classical Reichenbach's principle, as Eric talked about, for instance. We might ask the same question. Can you make that causal structure evident by decomposing U into a circuit? It would have to look like this, for it to have a sort of the topology, I mean, where to make it that A1 has no path up to B3 and A3 up to B1. The answer is no, not in general, the counter examples. But you can do this instead. If we introduce a new type of circuit notation that's a bit of a generalization from the usual one, then you can do it. I do it with these little indices, I there, you see, VI and WI and on the wires. In a circuit, normally, if I have parallel wires, that means a tensor product of Hilbert spaces, like here, HA1 tensor HA2. And when I have parallel wires with eyes on them, it means something like this. There's a Hilbert space that decomposes into subspaces and is a direct sum of those subspaces. And then inside each subspace, you have a factorization into two terms. But the whole thing doesn't factorize into two factors. Yeah, it's sort of inside each of these subspaces that it's a direct sum of. So that's what's happening here. And then this VI is a unitary on the A1, A2 Hilbert spaces, but such that it's always the identity on this bit. Kind of inside each subspace, it's only non-trivial on the left part, which is why the box only covers this wire. And with that little generalization, we have a theorem, any unitary with that causal influence constraint can be written as a little thing like that. And this generalizes quite a lot. Did a paper with my student at the time, Robin Lawrence, about that. We sort of covered all kinds of cases. There's an example of one. So 4 inputs, 4 outputs, like the red one, B2. What this picture here is saying that it's influenced by A1 and A3, but not any of the others, whereas the blue one, B1, is influenced by A1, A2, A3, but not A4. A theorem says any such unitary can be decomposed into a picture like that. And the point about that picture is that the causal relations follow from the paths. Now, I'm going to move to the foundations-y bit. Well, by the way, it seems now that there are also counterexamples, unitaries, where you can't quite do this thing with 4 inputs and 4 outputs. So I'm not actually claiming you can always do it for every unitary, but there may be kind of slightly weaker things, which are still interesting to look at. Anyway, let's get on with the interpretation bit. Let's roll with a certain idea. I mean, I'm not going to say enough to convince anyone who doesn't believe me, but I'm just sort of asking, let's roll with it. But the causal structure is ontic, so out there, independent of agents. It could be that the unitaries are ontic. It could be something weaker than that, where the causal structure of a unitary is ontic, but there's no matter of fact about whether it's this unitary with that exact causal structure or a different one, whatever. Suppose in any quantum experiment in which we would normally say that a measurement device has a pointer, and the pointer goes left or right, the device can be modeled entirely as a quantum system. There's no special realm of classical systems, anything like that. Suppose we describe the entire experiment as a unitary process. Now, in an individual trial, facts happen. The pointer went left, let's say. So what do these correspond to? They're not. If I've just drawn a unitary circuit, well, fine. That's kind of what's happening every time. But where does this fact come from about a pointer going left? Now, I was rather intrigued, you see, when I started investigating these unitary transformations and their causal structure, because any interpretation of QM pretty much faces some version of a preferred basis problem. Like, I mean, people call it that, certainly with regard to the Everett interpretation. Why is it a world with a live cat and a dead cat, as opposed to, right of superposition a different way, and you've got some world with a weird cat superposition and another world with a different weird cat superposition? Well, people like David and Simon have written, I think compellingly about that. So I'm not saying the Everettian can't address the problem. I'm just saying that David and Simon did need to do that work and write that stuff. So it needs to be talked about. In the de Broglie-Bohm theory, you can ask why position, and it's pretty much by fiat, isn't it? That's what the theory says. There were modal interpretations for a while where people sort of, I think they tried to use the Schmidt decomposition and then sort of pick out a preferred basis that way. I got interested here because this I is labeling orthogonal subspaces of the Hilbert space. And it's just picked out by the unitary transformations, which we are supposing are ontic. So the sort of ontically preferred decomposition of this Hilbert space here. The speculation started to become, well, what if that could be that's something we could sort of build an interpretation on. So the facts that obtain are something like that I thing taking a particular value on each trial. And so this is where we've got to, and Nick may talk more about this. Let's go back to that whole process, the unitary process I drew. And you remember I stretched the wires and then said that once I'd stretched the wires, it was kind of equivalent just to a big V going from these Hilbert spaces the output ones and the lambdas to those others, the input ones and the mu's. It turns out you can quite naturally pick out a preferred decomposition on each of these output Hilbert spaces. It kind of works. I'll say it briefly, and I suppose people can look at the paper or something or for details, but if you think of the algebra of operators on A out there, you can sort of roll it forward through V and then start to compare it with other algebras up there. And you can, in particular, take the intersection of it with the algebra of operators on the unlabeled things at the top. So those are the systems that just kind of went off at the end of the diagram off to infinity. So those are matrices within this algebra that commute with everything on A and B and C and D in. And then having got that, you can take the center of it, which then looks like a decomposition. The intersection of two algebras is an algebra. And so we get this algebra on A out, in general, a subalgebra of all matrices there. And being an algebra, it will have this structure of sort of looking like block diagonal matrices with A out being divided into subspaces. So applying that procedure, you uniquely pick out this decomposition. An intuitive thing to say might be that sort of anyone measuring at B in, C and D in won't be able to detect phases between these subspaces here. That's a sort of consequence of how we're picking it out. We'll do that on all of these spaces, so we get a decomposition on each of them. And because we have this time symmetry, and I don't want to introduce an asymmetry right now by hand for no reason, let's put them on the others as well. We can do exactly the same thing on those ins by sort of feeding them back and looking for subalgebras that commute with everything on the outs. Same rule, just the other way around. And then redrawing the diagram with the wires unstretched. That means it looks like this now with preferred decompositions associated with the ins and outs for each of these nodes. And what kind of nice is that when you take all those projective decompositions, they form what's called a decoherent history set. So yeah, people of a certain age will remember lots of talk about decoherent history sets, sort of from the 90s and maybe early 2000s. It means that there's a very easy way of assigning probabilities to these things. So a history means pick out just one projector from the projective decomposition for each of the decompositions. So it might mean, pick out P1 here and Q3 there, and on the B node P4 and Q2, and just pick out one from each. That's a history, and we can very easily assign probabilities to histories. With the rule that's just a trace rule, and everything works because it's a decoherent history set. Good. So just last, how much time is left actually? Because I can be fast or slow now. Perfect. Perfect. A question immediately is, okay, we can sometimes then find these preferred decompositions and define these decoherent history sets. But are there can we do it in a way that's useful? I mean, what about actual scenarios, like lab scenarios where we do stuff and we think there's an outcome? We need to have enough of these sort of histories to actually say that it corresponds to something interesting. And so it was encouraging that we started to look at a few different scenarios, like simple prepare and measure in a laboratory, for instance. Let's say a qubit gets prepared in a spin up or down Z, and then some unitary is applied to it, and then it's measured, just again in the Z basis. Well, you can model that whole thing. You have to include the preparation device explicitly in the picture, because this whole analysis, everything's quantum, everything's unitary, it all has to be in there. So there's other systems involved here. There's a couple here that are serving as a sort of preparation device. This one in the middle is the qubit being prepared. But we don't just say prepare a qubit. Again, we're trying not to be operational here. So that in fact, there's unitary interactions between that qubit and sort of preparation device stuff. I said a unitary was applied to it. That's just U in the middle. And then again, the measurement of Z at the end. You have to have the measuring device in the picture. Everything's unitaries. And so it might look something like that. And then you make cuts in the manner I described. Do that thing where we pick out preferred decompositions. And it turns out like this. Where I've written a Z, that means the preferred decomposition is, the Z basis. And where I've written X, it's the X basis. And sometimes it can be trivial. Your preferred decomposition is just the identity. So that's what it is where I haven't written any label. And yeah, I mean, you can, the usual stuff we say about comparing and measuring and getting this with these probabilities kind of follows from the distribution you get over all of these X's and Z's. So now, yeah, it was quite handy in a way that I'm immediately following Emily, because almost as if somebody found it. Well done. Excellent planning. Just for that. Because now I'm going to say a thing or two about relationalism, which is kind of where I see this thing as heading, actually. Because so far I've been pulling the wool over your eyes a little bit. We can ask, have we succeeded in identifying a unique, I was calling it decoherent history set a minute ago. Let's say decoherent history set, such that one element, i.e. one history, could then just be probabilistically, selected and regarded as the history of the universe, a one world universe. And the answer is no, unfortunately. That would have been too easy, perhaps. Because we could have started with the same unitary circuit and made a different choice of which wires to break and which to leave closed. And I said, there's not meant to be anything kind of special about those ones. It's just me being interested in them. So I could have been interested in some different places in that circuit. I could have done the whole thing again. I'd have got a different set of histories that might have been incompatible with the first set. This is the problem. And there are even examples where you can prove a sort of contextuality type thing. Two of these sets involve, let's say they share a node and even pick out the same projectors on that node. And then you argue that, do a proof that it has to be a different projector. On a given file, you can't even enforce the rule that it's the same projector you always get in the two different incompatible history sets. So, yeah, what do we do? Bit of terminology. I think we started saying bubble for this as well at some point, following a word Eric introduced in discussions of Wigner friends and things. Let the circuit along with that choice of which wires to break be called a frame. The suggestion then is that quantities are relative to a frame. So these projectors that are picked out and are then taking a value probabilistically represent relations between a node and the rest of the frame. And I'm wondering if this could be one way of sort of taking works which I find, provocative, like, Carlo Rovelli's papers on relational quantum mechanics and things, but trying to put some mathematical precision on some questions about, what's relative. When do things actually take definite values? When does the measurement happen so that even relationally a thing has a value relative to a thing? And then what relative to what? Answer that question. We do have some answers to that thing here. I should say though, I mean, there's other stuff you could do if you really wanted. You could do sort of start to explore mad things. Maybe the cuts are ontic and fundamental, and like have them random or something. Nature is a big circuit like that with a random. Each wire has a probability p to be cut, and that way, well, you would get a unique kind of history set picked out and one be the path. But right, yeah, I'm just saying that you could start with this formalism and go in a few different directions. And so this kind of relationalism thing is just, yeah, perhaps the direction I'm most interested in. And then I did have this slide for discussion. A lot of this has already been discussed by Emily. So consider a sentence like that, relative to frame F, history H obtains. And on a particular trial, is that sentence then true or false? Absolutely. Or is it true or false in turn relative to something else? I think Emily was suggesting a similar thing. For me, if it's relations all the way down, I think this is an infinite regress. I think you have to stop and say that something's absolute at some point. So let's say absolutely. Yeah, but there's something still missing that would have to be there, I think, to start to have a convincing interpretation, which is, given two such statements, relative to frame F, history H obtains, we might, do all the analysis, work out probabilities, suppose that H obtains on that run. And P prime on the very same trial, let's suppose that relative to F prime, history H prime obtains. There should be some logical relation between these statements, I feel, because if none, we're kind of stuck with a position where specifying the ontology of a particular trial just involves a kind of massive list of such statements, one for every conceivable frame. And I don't think that would be the right way to go. But yeah, a way forward I'm interested in now is can we sort of take inspiration from the literature on quantum reference frames, things like this, see if we can put that into this work somehow. The reference frames could be large or small systems, but they have to be in the diagram along with everything else, not just externally. So on this approach, it's not enough for something just to be kind of sitting there somewhere out there to be a reference frame. It actually has to be interacting with the system in some way in order to serve as a reference frame for that system. And in particular, yes, your diagram has to include anything that you are hoping might act as a reference frame. And then, so we're going to look at the literature on quantum reference frames for this, and somehow understanding these projectors as relations between things in the circuit is the idea. I'm going to stop talking just there, I think, yes, and just ask if there's any questions.
Well, this is just for clarification. You right at the beginning, you had a sentence on the notion of causality in relation to agents' interventions. And I know this word intervention is something that Pearl uses a lot, and I never really fully understood what it means, what an intervention is. Towards the end of your talk, you said that cutting a wire could lead to some inconsistent state. So if an agent intervened, maybe counterfactually intervened, cutting a wire where in reality the wire hadn't been cut, does that mean the intervention sort of changed the basic ontology of the world you're considering? What are the implications of this for interventions, I suppose, is my question.
So, except for a speculative idea about cuts appearing in the ontology probabilistically, but forget that. Except for that, the cuts don't correspond to anything. I mean, all that happens here is that system just keeps evolving like it always does. And me having drawn a cut in the picture is just so that I can give it a label and start to talk about whether it causally influences other things, other bits of the picture. Now, certainly, we can imagine an agent choosing to intervene at that point. They may just insert their own extra little unitary transformation there between U1 and U2, for instance, on that system. But I didn't need to talk about that because it wasn't part of any of the analysis I was doing. People who, from studying processes for other reasons, doing operational things, often talk about agents intervening there. Or doing a measurement would be another thing an agent could do there if they wanted. But again, for me, there's no agent, there's just the system doing its thing. I mean, to answer your question literally, I think you asked if someone does an intervention, is that different ontology? Well, yes, very much so. There's a hulking great agent there. Sort of measuring the system, that is different ontically from there being no agent there. But if I wanted to analyze the case where an agent was there doing something like an intervention, I wouldn't just say that and use the word agent. The agent's a quantum system. They've got to be in the picture as well. So I would draw a bigger circuit where some of the systems are now, that is the agent or bits of the agent or something. But the agent, they measure actually means there's unitaries happening, but interaction between the agent wires and that one.
But what was the point you made right at the very end of the talk about doing something to the wiring, made some compatible list of projector something incompatible?
The idea of the analysis was, once I've got a picture like this that I've already made some cuts in, I get a preferred projective decomposition on each of the on the incoming and outgoing wires for each of these nodes. So actually two projective decompositions in each place. And they had a nice feature, which is they made a decoherent history set, and it was easy to give probabilities to them. The point I was making there is that I suppose I'm talking about the same experiment now, the same set of events, but I just draw my picture differently. I don't decide to put cuts where A and B are there. I put one here instead, and another one up there instead. I can redo my analysis, and I'll pick out projective decompositions on those places. But what I have now is a new history set, which may be incompatible with the one I got from this picture.
Yeah, I was puzzled about this thing too. So it seems to me that it's clear from what you said now. It seems to me this is not relativity or relativism. This is just a non-uniqueness of which history to assign. Because if I understand correctly, cutting these wires does not correspond to doing anything.
That's right.
Yeah. Then, well, how could the way I describe the system or the whole evolution here be relative to the various ways in which I could do nothing?
Well, no. You you have to. You have to you have to decide what you're going to talk about. You have to label a system. You labeling a system and calling it system S is not doing anything to the system, is it? Some systems you won't decide to label because you're not labeling everything in the universe. So to say anything, you have to say this is S, this is system T, and now start to say some stuff about them. That's what's happening here. I've decided to say stuff about A, B, C, and D.
Yeah.
Certain systems I haven't labeled because I'm not labeling everything in the universe. And we found some things follow. You can talk about causal influence, for example.
Sure.
By the way, even if people don't buy the interpretational bit, I could have veered in a different direction, done all of this, and then you get quite a nice account of quantum causal models, which will have practical use and consequences, just as the classical literature does.
But wouldn't then be right to say, well, we got a variety of ways in which I could label systems or choose not to label them. and therefore I have a variety of different representations or consistent history, decoherent histories, and they're all equivalent. It, we just have a choice between all of those, rather than to say that it introduces a sort of relativism.
It's, I mean, you do want to recover, experiments having outcomes though. And it's tricky when, suppose that I get a particular projector I get this projective decomposition on, let's say, my A node here. And the idea is that one of those projectors actually happens when this trial takes place.
Yeah, but I didn't think that, or I didn't expect that your analysis of these unitary matrices is going to lead to a solution of the measurement problem.
That's that's the idea.
That is the
when I
idea.
said aiming towards an interpretation of quantum theory, that's exactly what I meant, yes.
Just by considering unitaries.
Pretty much, and understanding relationalism appropriately. You may notice that the quantum state is pretty much absent in this story. It will come back but it has more of an epistemic significance, you see, which I actually kind of see as a strength of the story. It will come back if a scientist, let's call her Alice, is wanting to make predictions. Think of this analysis. The scientist already knows some things, some facts about the lab, the past, whatever. So they know the values of some of these P's, some of these projectors, going back in a massive sort of diagram way back. So the agent is actually wanting to predict kind of future things. And it's not that time has a special direction here, but agents themselves are kind of directed. So the agent is typically wanting to make predictions about, let's say, what projectors are going to be realized on some node D, conditioned on certain projectors having already been realized on other nodes. And in order to do that calculation, they'll be writing down a quantum state.
Yeah, just a quick question. You had consistent histories and then you had decoherent histories, and I just wondered if there's a difference. And does it involve the vanishing of both the real and the imaginary parts that normally involved?
What actually happened was I gave this talk, once before because you were there, and I called them consistent histories throughout. And at the end, you told me I should have said decoherent. And then I changed it for this talk, hoping that was right, except one instance forgot to change, so it still said consistent.
Okay, well, if I said decoherent,
I'll be honest, I can't remember the difference.
I think you mean vanishing of both the imaginary and the real.
Well, yeah, actually, I do mean that. They satisfy a condition that's even a bit stronger than that one, but yeah, it's both of those parts.
Very quick question, Tony, if you can make it reasonably quick. And then we better have a coffee break.
Yeah, sorry, here's a quick one. So when you were defining the causal influences, I think you had it that A doesn't influence B if the reduced density operator out at B doesn't depend on the reduced density operator in at A. Is that right?
Might have been.
Right near the start.
Can you say it again?
That when you define the causal influence, that A doesn't influence B, you were saying, I think maybe the previous slide, that it just depended on the reduced density operators in and out.
So the previous slide, that's just Choi Gamilkowski. There was some chat about fine tuning and signaling.
Anyway, maybe I'll.
This was the definition of no influence through a unitary.
But I guess it seems to depend just on the reduced density operators of individual sites. I guess I wanted to know if it depended on how those sites were entangled with other sites. So you allow us to put in entangled inputs. And
so this whether A influences D or not depends only on the unitary. It's just a property of U. It doesn't depend on the state of anything.
But I guess that this sentence, just on the field diagram, the marginal row D is independent of row A. If the marginal row D was changed by how A was entangled with B, but not its reduced density operator, would that?
Are you thinking of A being entangled with
B
or something?
But you put in a state in which those two are entangled.
Yeah.
And if the output D depended on how they're entangled, but not on the reduced density operator A, maybe in some way then A is influencing D.
I think it can't.
Okay.
You can consider an entangled input on AB and then think of doing a transformation on A alone, and an equivalent definition is that the output at D is independent of anything you do at A.
Okay.
And that the statement is if that holds true for all possible joint inputs on A and B.
Okay.
Including entangled ones. So you can define it that way, but it's equivalent to
thanks
to this. There's a nice algebraic one that's equivalent as well. Just the algebra to A, if you sort of roll it forwards through the unitary, and if it commutes with the algebra at D, that's equivalent to this as well.
Great,
okay.
Okay. Welcome to the final session of this really wonderful conference. I'm Kareem Tebo from the University of Bristol. I'm going to be sharing the session. And the first speaker, who's going to continue some of the themes from the last session, I believe, is Nicole Morod from the Perimeter Institute. Over to you, Nick.
Well, thank you very much. And thank you to Chris and everybody involved organizing this conference. And also for the excellent scheduling, because John has set me up very nicely for this talk. I'm going to be delving further into the implications, the interpretational implications of quantum causal modeling, and elaborating on their connections with decoherence. So, throughout the first century AQ, where by AQ I mean after quantum. Throughout the first century AQ, the way that we think about quantum physics and its foundations has really been conditioned by what I would call the state first view of physics. Now, on the state first view, physics aims to describe reality, or at least our knowledge of it. And the way that it makes those descriptions is by specifying states. Oh, dear. The way it makes those descriptions is by specifying states. And dynamics, on the other hand, are rules for transforming or constraining descriptions, hence transforming or constraining states. So on the state first view, dynamics do matter only because of their implications for states. States, on the other hand, don't have to justify their own existence. They already are the core subject matter of physics. So it's not that I think that most or all physicists actively endorse the state first view. And in fact, I find that when you explicitly articulate it, it is often met with skepticism. And that's all very good. But at the same time, I do believe that historically physicists, for whatever reason, have found it much more difficult to pin down a dynamics first alternative to the state first view. And that's not all that surprising, because in order to pin down a dynamics first alternative, you have to answer a tricky question, which is what could the dynamics be if they are not rules governing states? We seem to have a difficult time answering this question because doing so flies in the face of a number of more state-first intuitions that we have about reality. This is where quantum theory is going to give us a great gift. Because as you've already begun to see in John's talk, and as I'm going to elaborate on further, buried inside the mathematical structures of quantum theory, there are clues for what a dynamics first view of physics might look like. And once those clues are spotted, it's actually surprisingly easy to reformulate quantum theory from a dynamics first perspective. And in doing so, arrive at a mathematical formalism that helps provide a clear answer to this question on the screen. Okay, so it'll be easy to reformulate the theory once we see those clues, but seeing those clues is like trying to see the special effects in a 3D movie, right? It's easy to do so as long as you're wearing the right glasses. Well, these are the glasses that we need to put on. And it's very convenient, again, the scheduling, because we've already seen each one of these lenses in isolation. In David's talk this morning, he talked about the way of decoherence, and John talked a lot about the concept of causation in quantum theory and what we can do with it. Well, I really believe that these two things are two sides of the same coin. I think the proper way to understand decoherence is through the lens of quantum causation, and in fact, vice versa. And together, coherence and causation provide you a perspective that makes very clear how to think about quantum theory in a more dynamics first way. Okay, so in a little bit more detail in this talk, I'm going to start by discussing coherence. And I'm going to begin by arguing that traditionally, the way that we think about decoherence has been held back by our state first tendencies, which have often served to obscure the very central role that's played by the unitary dynamics in decoherence. The remedy to that problem, I'm going to argue, is ideas from quantum causal modeling. Ultimately, we're going to arrive at a formalism for dealing with, for treating decoherence using causal influences that I call the causal decoherence formalism. And it's going to be equivalent to some of the techniques that John was just describing, although we're going to see it introduced in a different way. Now, the causal decoherence formalism is just that. It's a formalism, right? It is not itself an interpretation. It's a formalism for studying decoherence from a causal perspective. But nevertheless, there is an obvious way of taking this formalism literally and arriving at some kind of interpretation of quantum theory. And I'm going to call that causal quantum theory. Okay. So unlike John, I am going to be talking about causal quantum theory as an interpretation. Now, the reason for that is not that I think that that I disagree with John that there are still problems faced by this interpretation, or that I disagree that we should ultimately be looking for a more satisfactory successor theory. But what I want to emphasize by calling it an interpretation is that it is a precise mathematical formalism which describes a way that the world could possibly be. And in doing so, it reproduces the predictions of quantum mechanics, at least in the finite dimensional case. And thus, whether or not we find it an attractive or unattractive interpretation, whether we find it plausible or implausible, it is a kind of interpretation. And I think it's a very valuable one, insofar as it's going to allow us to bust a number of myths that have developed over the first century AQ and equip us with some new lessons that we can bring in to the second century. All right. So I'm going to begin by talking about decoherence. And I think it helps to start with a story about decoherence that I'm sure pretty much all of you will already recognize. Although it's a very well-known story, I think it's worth retelling it, because it highlights some tensions, I think, in the way that decoherence has often been traditionally conceived. So in this story, you begin with a quantum system in an even superposition of states, and you want to measure this system in that 0-1 basis. Well, if it's true what they say, that all time evolution is unitary, then that interaction itself is just another unitary interaction. So we can see what happens when we try to model it like one. For simplicity, I'm going to assume that the apparatus is just another qubit, and then a reasonable choice of Hamiltonian turns out to be the one on the screen defined in terms of Pauli operators. Now, if we run that Hamiltonian, we end up with a post-measurement state of the system and the apparatus, psi. Now, if you look at the top expression for psi, you might think it looks encouraging, because it tells us that that 0-1 basis has indeed become correlated with the apparatus. Yeah, good. And you might think that this correlation between the 0-1 basis for the system and the apparatus allows us to argue that we really have measured that basis as we wanted to. And actually, if that argument goes through, then we're really in big trouble, because we could apply the exact same argument to this bottom expression, and then we'd be concluding that it was actually the plus-minus basis that we measured. And we know, of course, that we can't measure these frequencies without noise at the same time. So there's the problem. The state psi is just too symmetric to single out any unique basis as preferred, and thus it cannot support the conclusion that we have measured any unique basis to the exclusion of all others. Preferred basis problem. Unfortunately, the story doesn't end there. It goes on to say that actually all we need to do to get a solution here is to take account of a very obvious fact, that any apparatus is inevitably going to interact with its surrounding environment. So we'll do that, and for comic simplicity, I'm going to assume that the environment too is just another qubit. Then it turns out that this again is a reasonable choice of Hamiltonian, and we can run it and get a new post-measurement state initially of all three systems, and then we trace out the environment to obtain a new state for the system and the apparatus. And this state is good news because unlike the state psi, it does pick out a preferred basis. You can see from that expression that the 0-1 basis for the system is still perfectly correlated, but then the absence of off-diagonal terms in the density matrix, that tells us that the 0-1 basis is the only one that remains perfectly correlated with the apparatus. And that is supposed to be our preferred basis solution. Okay. So as I said, this is a very famous story, not just within the context of people who work on decoherence, but actually it's permeated throughout the quantum foundation's consciousness more generally to a great extent. And yet, interestingly enough, this story was told in a landmark 1981 paper by Wojtek Zurek, which actually opened with an observation, which, although it's definitely known by people who work on decoherence, compared to the story that I just told a second ago, it's comparatively less famous. And this observation is about the role that the unitary dynamics play in decoherence. So, Zurek thinks it's important enough that he opens this paper by saying that the form of the interaction Hamiltonian between the apparatus and its environment is sufficient to determine which observable of the measured quantum system can be considered recorded by the apparatus. And the basis that contains this record, the pointer basis of the apparatus, consists of the eigenvectors of the operator and commutes with the apparatus environment interaction Hamiltonian. Now, to get a sense of what Zurek is saying here, we can apply it to our existing example. Well, the relevant interaction term for us is this minus ZA tensor XE, where those are Pauli operators. Now, we can ask which apparatus observables commute with the interaction term, and we find that it's precisely those observables that are diagonal with respect to the 0, 1 basis. Now, Zurek's observation, his insight, is precisely that this fact alone allows us to directly infer that the preferred pointer basis of the apparatus is the 0, 1 basis. It's a very powerful observation, right? If you want to know what the preferred basis is, then all you have to do is look at the structure of the Hamiltonian. You need not consult anything else, and in particular, you don't even have to look at the quantum state. So as powerful as it is, it's an observation which is also a little bit puzzling, because in that story about decoherence and preferred bases that we just went through, actually the emphasis really was on quantum states. Hamiltonians were there, but they were really in the background, helping us to calculate the evolution of states. And at the end of the day, we were encouraged to conceptualize the preferred basis in terms of quantum states, and in particular, in terms of the correlations that the state of the system and the apparatus defined, right? The preferred basis of the system was the unique system that remained perfectly correlated with the apparatus. So we might reasonably ask the question, given that the unitary dynamics alone determine the preferred basis, why does Zurek conceptualize the preferred basis in terms of states? Why do we need the quantum state as a kind of middleman? Why can't we just directly, not just formally define the preferred basis in terms of the Hamiltonian, but actually conceptualize it directly in terms of the dynamics? Okay, now I think this question has a clear answer, but I'm not going to tell you what I think that answer is just yet. Instead, I'm going to encourage you to keep this in the back of your mind as we go forward about a decade in the history of decoherence, and in particular, in Zurek's thinking. So about a decade later, in the early 90s, Zurek's work had exerted a pretty significant influence on the foundations of quantum theory, and yet Zurek still felt that the central concept of decoherence was often being misunderstood. And in particular, he felt that people often misunderstood the role that was played by diagonality, the suppression of off-diagonal terms in the density matrix. Now, we did see that for Zurek, diagonality is an important consequence of decoherence. But people, even today, they often think it's more than that, right? People often think that decoherence just is diagonality. And already in the early 90s, Zurek is adamant that that's a mistake. He says diagonality alone is only a symptom and not a cause of the effective classicality of the preferred states. And as all symptoms, it has to be used in caution with diagnosing its origin. Causes of diagonality may, on occasion, differ from those relevant for the dynamics of the process of decoherence. It's a clear argument. Diagonality is not sufficient for decoherence, so cannot possibly define decoherence. Fair enough. Now, Zurek also made a very similar type of argument against the use of the consistent histories formalism to define decoherence. He said that the satisfaction of conditions from that formalism, yes, tends to be a consequence of decoherence, but is not sufficient for decoherence, therefore cannot possibly define decoherence. Zurich is very keen that we don't take mere symptoms of decoherence to be supplying the definition. He wants us to understand the process itself. Okay, so Zurich made these criticisms of various colleagues' definitions of decoherence at a conference where many of those colleagues were present. And so it's not surprising that some of his colleagues challenged him as to what he thought would be a sensible definition of decoherence. In the discussion, he said this: I feel that the term decoherence is best reserved for the process which destroys quantum coherence when a system becomes correlated with other degrees of freedom. Now, in the first part of this quote, Zurich is calling decoherence a process, so he's emphasizing its dynamical character. And I think we could read that as an attempt of Zurich to do justice to his own 1981 insight that it's just the dynamics on their own that determine a preferred basis. But unfortunately, I think justice is ultimately not done to that insight by the quoted definition. And the reason is that after he calls decoherence a process, Zurich then gives us no way of defining exactly what that process is, except by appealing to its symptoms. So he appeals to two things: the destruction of quantum coherence, so that's diagonality, which we just saw for Zurich was a mere symptom of decoherence, not sufficient for it. And then the only other thing that it appeals to is the formation of correlations between that system and other degrees of freedom. Well, you can make a very Zurich-like argument that correlation formation 2 is another mere symptom of decoherence. Because it's true, that kind of correlation formation, it does tend to be the consequence of the interaction Hamiltonian having the form that for Zurich picks out a preferred basis. But it's not sufficient for the interaction Hamiltonian to have that form. It can happen for other reasons, such as initially fine-tuned states. And so in a very Zurich-like way, we can argue that correlation formation is another symptom. And so I think, unfortunately, Zurich here, every bit as much as the colleagues that he's criticizing for doing so, is defining decoherence merely in terms of its symptoms rather than getting to the core of the process of decoherence. Now, remember that question we asked a moment ago, right? Given that the unitary dynamics alone determine a preferred basis, why doesn't Zurich directly conceptualize preferred bases in terms of Hamiltonians? Here we're led to ask another similar question. Why does Zurich define the process of decoherence in terms of its state-level symptoms rather than directly in terms of the Hamiltonian responsible for them? Zurich knows better than anyone, because he pointed it out, that the preferred basis is there just in the dynamics alone. So why is he reaching for this idea of a process where quantum coherence is destroyed and you've got correlation formation, rather than directly appealing to those structural features of the Hamiltonian that Zurich himself places so much emphasis on? Good. Now, I think that actually both of these two questions have a clear answer, and they have the same answer. Although Zurich is well aware about the central role mathematically played by the dynamics in decoherence, he is nevertheless influenced by the state-first view. Remember, the state-first view of physics was that physics aims to describe reality or our knowledge of it, and always the way that it makes those descriptions is by specifying states. So states are the core subject matter of physics, and dynamics are just rules governing states. If that's how you think about physics, then always you have to cash out the conceptual implications of the dynamics in terms of their state-level features. Zurich is well aware that at the formal level, or the mathematical level, he could find preferred coherence just in terms of the Hamiltonian. But he doesn't want to do that because he's not content to give us mere formal conditions for coherence or preferred bases. He wants to give us conceptually motivated definitions. And so he is led by the state-first view to reach for the language of quantum states. So essentially what I'm saying here is that there's a kind of tension in Zurich's work between the mathematically primary role played by the dynamics and the conceptually primary role, which is nevertheless often afforded to quantum states. Now, if you're somebody who is wedded to the state-first view, then you might be content to just put up with that. You might not view this tension as a big deal. But if, on the other hand, you're somebody who is open to dynamics-first alternatives, if they can be articulated, then you might regard this tension as a reason, a motivation, to develop a dynamics first perspective on decoherence and perhaps ultimately on quantum theory generally. Well, that's what I'm going to try to do now, and making use of ideas from quantum causal modeling and especially from these papers. Okay, so the idea that I want to push here is that the missing conceptual ingredient that is necessary so that the dynamics cannot merely provide a formal condition for, but so that you can actually conceptualize decoherence in terms of the dynamics. That missing ingredient is causation. As John has just described to you in his talk, the approach to causation in these papers is that causation is a property of the unitary dynamics alone. And I'm going to be arguing that it's the really salient property that we need in order to define referred bases, decoherence, and so on, purely in terms of the unitary dynamics. Well, what we're going to find, as John has anticipated, is that once we develop that causal approach to decoherence, right, they act like these kind of 3D glasses. They make a dynamics first perspective jump out at us. Okay, so I want to develop a purely dynamical, purely causal definition of decoherence. And to do that, I want to begin by looking at a very simple case of a 2-input, 2-output unitary transformation. Our goal is to identify which observables on this input A are decohered as a result of its causal relationship with D. So what we want to do is really put this causal relationship under the microscope. Now, in John's talk, when he was discussing causal influences, that was always in the context of causal influences between entire systems. So on that definition, it's just a yes-no fact of the matter about whether or not A influences D. But as I'm going to describe, you can also define causal relations at a more fine-grained level, and they turn out to be very useful for understanding decoherence. Okay. At the mathematical level, causation in quantum theory is really all about operator algebras and non-commutation relations between them. So it's going to be very important for us to think about these systems in terms of their operator algebras. So we're defining the system A just as the kind of algebra of operators that act locally on this wire of the input space of U. And D, we're thinking of in a similar way, except that we're rolling that algebra of operators back through the unitary. So now that A is defined on this input space, which is good because now that the A and D operators are defined on the same Hilbert space, we can compare them and we can ask whether they can meet with each other. Now, in order to really understand the nature of this causal arrow from A to D, we're going to have to make use of not just one, but two key causal concepts. And I call these concepts influence and accessibility. All right, so in both cases, it's a relation between an individual operator on A and the full system D. I'll describe what these are mathematically, and then I'll show you how you can interpret them operationally too. So mathematically, an operator in A influences D if and only if it doesn't commute with at least one operator on D, right? That D prime denotes the commutant of D. So what this is saying is that influence is about MA not commuting with at least one of those D operators. Good. Now for accessibility, we're saying that MA is accessible to D if and only if this whole condition holds. So for all operators in A, MA and that other operator don't commute, then that other operator has to not commute with D. Or bearing in mind the first definition, we could say, then this operator has to influence D. Okay, so there's some mathematical conditions, but what do these actually mean conceptually? What do they mean operationally? Well, it helps to assume, and it turns out that it's harmless to assume, that MA is a Hermitian operator. If it's a Hermitian operator, then it can be regarded either as an observable or a generator of unitary transformations. And a nice way of intuitively understanding each role that it plays is by writing the operator in its spectral decomposition. So as an observable, you know, in quantum information theory, we would say that the information encoded by the observable is really this projective valued measurement defined by its spectrum. But as a generator, what it does is it generates unitary transformations that do nothing except for change the sort of these degrees of freedom that are conjugate to that PVM, right? So it's really playing dual roles as a generator or as an observable. This, of course, is very basic quantum mechanics, but it helps to really bear that generator-observable duality in the front of your mind as you're understanding causal relationships, right? These quantum operators, they're not just observables, they're observables and generators. So if we want to understand influence at the operational level, I find it helpful to think about MA as a generator. If MA is a generator, then influence simply means that the generator can be used to send signals to D. Right? So more precisely, imagine an agent Alice gets to implement the generator down here before U gets applied, and Debbie gets to perform whatever measurement she likes up here after the unitary is applied. Influence is equivalent to Alice being able to signal to Debbie for at least one initial state of AB. So again, influence is signaling from a generator. Okay, for accessibility, I like to think about MA as an observable. So if MA is an observable, then what does this condition mean? Well, let's think about these GAs as generators. And then we think about the Heisenberg equation. What this non-commutation relation tells you is precisely that this generator actually changes the observable. And this is influence, so we now know that this condition means that the generator sends signals to D through the unitary. So altogether, this condition is saying that any generator that changes the observable has to signal to D. We're saying that D notices whenever we make a change to that observable, and that is the sense in which D has access to the observable. Okay, good. So it's nice to have operational interpretations of these notions. It helps with our intuitions. Bear in mind, though, just as with John's talk, it's not going to be crucial to the story that there actually is any Alice or any Debbie. At the end of the day, things that are defined by the unitary dynamics, which we might well think is just an objective, agent-independent thing that happens. Okay, so what's the point of looking at influence and accessibility? Well, remember, our goal here is to find decoherence of observables on A by putting under the microscope A's causal relationship with D. It turns out that these concepts help us do that. So in particular, the concepts of influence and accessibility, we can use them to define a partitioning of A into two independent subsystems, right? And that partitioning will help us understand the causal influence. So at the mathematical level, the complete set of non-influencing operators forms a subalgebra of A that I call A and I. The complete set of accessible operators also forms an algebra that I call A at. And it turns out it's not too difficult to see that each of these algebras is the commutant of the other, where I'm taking commutants within A, so that's why I'm always intersecting with A here. Good. So we're dividing an algebra into two subalgebras where each is the commutant of the other. In quantum theory, it represents a division of a system into two independent subsystems. And it's a partitioning that's induced by the causal relationship with D. It's very important, though, to bear in mind that when we're partitioning the algebra A, we're not partitioning it into two disjoint subsets, right? We're partitioning it into commutants. So in particular, there can be non-trivial operators contained in the overlap of these two algebras. At the operational level, it's easy to see why. It's perfectly possible for D to have access to a given observable even if it doesn't receive signals from the corresponding generator. And when that happens, D has access to the information encoded by this PVM, but not to the conjugate phase degrees of freedom. What does that sound like? We're going to be defining decoherence as the conjunction of non-influence and accessibility. And what that really means is that we're going to define a decoherent subalgebra of operators on A as the intersection of our two algebras. Well, what do we immediately notice about this definition of algebra? It's the intersection of two algebras that commute with each other. So it is a commutative algebra. That's good. That means that it always picks out a sort of preferred classical degree of freedom. For simplicity, in the finite dimensional case, it always picks out a unique division of the Hilbert space into orthogonal subspaces. So in particular, the decoherent operators are precisely the linear combinations of the projectors onto these subspaces. Good. So that's the end of our general analysis of decoherence for this simple case of a two-input, two-output unitary. Now, maybe bringing this sort of abstract analysis back down to earth a bit, we can revisit that preferred basis example that we started off with. So we had this Hamiltonian coupling the system and the apparatus at the beginning of that story we told before. And it generates unitaries of this coherent control form that you see here on the screen. This thing is a two-input, two-output unitary, so we can apply all of our analysis. And in particular, we can look at the causal relation between the system and the apparatus and use that to pick out these preferred algebras on the system. Okay, so what algebras do we get? Well, to begin with, we can ask, what is the algebra of non-influencing operators, right? The generators that don't send signals. And that turns out to be this one, right? Operators diagonal with respect to the 0, 1 basis. So what this tells us is that the apparatus doesn't learn anything via this unitary about the relative phases between the 0, 1 basis states on the system. Good. We can then obtain the accessible algebra just by taking the commutant of this algebra within the total algebra on S. And this algebra is actually self-commutant, so we just get the same thing again. And that's really a relief, right? Because the point of this Hamiltonian was to measure the 0, 1 basis. So it would have been awkward if anything else had been the accessible algebra. We want the observables that are diagonal with respect to the 0, 1 basis. Okay. The decoherent algebra is the intersection of these two algebras. And operationally, remember, it's the observables that are access to the apparatus but don't send signals to the apparatus. Well, of course, in this case, it's just the same algebra again. And so these are the decoherent observables. This allows us to argue that the 0, 1 basis for the system is selected as preferred by our causal notion of decoherence, matching Zurich's own conclusion the way that we told the story before. It's worth emphasizing, though, that here we've got this preferred basis without bringing the environment into the picture. How is that possible? Well, from the beginning, we never assumed that if there was a preferred basis, we would have to be able to read it off of post-measurement state. To the contrary, we looked for a preferred basis in the dynamics, and we found it without bringing in the environment. All right, so that's a good start, but you could accurately object that this is not yet a completely dynamics-first solution to the preferred basis problem. Why not? Well, yes, I've given you a definition of decoherence just in terms of causation and thus just in terms of the unitary dynamics, and we found a preferred basis according to that notion of decoherence. But nevertheless, I've not told you how to think about those unitary dynamics as anything other than rules governing quantum states. I'm still yet to answer this key question for any advocate of the dynamics first view of physics. What could dynamics be if not rules governing states? Well, ultimately, we only have to leverage our analysis a little bit further in order to get an answer to this question. So the key thing is that we need to extend our analysis of decoherence beyond these simple two-input, two-output unitary transformations and towards arbitrary circuits of unitary transformations. So I'm going to show you how to do that. I'm going to use this particular circuit as an example, but at no stage in the analysis am I going to assume any special features of this circuit. So this method will generalize. Now, it's a four-step method. It's going to be equivalent to the method that John described for extracting preferred bases. But here, we're going to see a way of doing it that doesn't require you to make these cuts in the wires, and a way of doing it that sort of more directly connects, I think, to this notion of decoherence. Step one is identify a set of systems that you want to study decoherence relative to. So here I've picked 3 systems. I've called them P, S, and A. And note that by a system here, say by the system P, I really only mean the wire going into U. I don't also mean the wire coming out of U. So it's a sort of time localized notion of a system rather than a system that persists over time. Okay. So step 2 is after you've identified these systems, define not just 1, but 2 non-influencing algebras for each system. So I'll write down the particular definitions you end up getting here. And you should be able to see the pattern. So in every case, we've got a down no influencing algebra and an up no influencing algebra. And the up no influencing algebra is defined in terms of what comes above in the circuit, and the down algebra is defined in terms of what comes below in the circuit. If there's nothing below a system, say P in the circuit, then it's going to be defined in terms of the empty set. If there's multiple things above, then we'll take the algebra that's generated by everything above. Okay. So we can always do this and get our 2 non-influencing algebras. Remember, John already gave the justification for sort of applying this analysis in 2 directions of time, right? It's just that we're dealing here with a unitary circuit, which is time symmetric, and a notion of causation, which is time symmetric. It would be odd if we suddenly decided to carry out our analysis in a way that assumed a preferred direction of time. Step 3 is after getting these non-influencing algebras, you can take commutants to get accessible algebras, intersections to get decoherent algebras, and at the end of the day, you're going to arrive at preferred decompositions of the Hilbert space. Okay. Step 4 is the exciting one, because it's the one that invokes the sort of key theorem, the key result that makes all of this analysis possible. It's the result that John already introduced in a different way, which says that these preferred decompositions will always define a consistent history set. So not just for this particular circuit, not just for this set of systems, starting from any unitary circuit and any set of systems, you will always get a consistent history set. And in particular, it's a consistent history set whose probabilities are described by this simple expression where you're just lining up projectors and tracing them through and dividing through by the dimension of the Hilbert space. Okay. So that completes what I call the causal decoherence formalism. A way of arriving, in this case, not just a preferred decomposition of some system's Hilbert space, but actually a whole history set just by looking at decoherence, where decoherence is defined just in terms of the causal structure defined by the unitary circuit. Now, the question is, how can we leverage this in order to come with a more completely dynamics first solution to that preferred basis problem? Well, now you're going to see my agenda in labeling these systems P, S, and A. What I had in mind all along was that S is the system, A is the apparatus. P is going to be a preparation device that you use to prepare your system in an initial state. So we're going to see how this works. I'm assuming a little bit more about the form of these boxes in the unitary circuit. So we've got coherent control unitaries, the kind that were generated by the Hamiltonians that we've been looking at so far. And when you apply that analysis of decoherence to this sort of example, it's actually what you get on A and Q. It's going to depend on what the definitions of the V's and the U's are. But in most cases, you get sort of nothing interesting popping up on the apparatus and the preparation. You do get 2 interesting things popping up on the system. Okay. You've got your sort of up event, which you can think of as the measurement outcome, and you've got this down event, which I'm going to argue you can think of as the preparation of the state. So how does that work? Well, remember, there's always a probability rule, so we can compute those probabilities, and we obtain a conditional probability for one of these events given one of these events. And we find in particular that reduced conventional textbook quantum expression for what situation? Well, the situation where you're calculating the probability of a measurement outcome K after preparing the system in the state psi. That's important because that is what justifies us in regarding this unitary box over here as state preparation, right? This thing that is leading to the emergence of these psi events which appear in this expression. We have internalized state preparation into the circuit, and thus there is no need for an input state to the entire circuit. And I want to dwell on this because this really matters. The way that we are used to thinking about circuits is state first. What is the circuit? Well, it's a rule that tells you how a state that I put in the bottom of the circuit is going to evolve as it moves up to the top. Well, we don't need to think about this circuit in that way because the state has been internalized into the circuit itself. At no point in our analysis do we need to insert an input state. Good. Now, I'll probably race through this because John sort of already had a model that looked a bit like this one. The point of this slide really is to convince you that there's no problem with incorporating measurement devices, even observers, into the picture. So on the previous slide, I only had events happening associated with the system, the quantum system that we were measuring. But when we extend the circuit to take into account the interaction between the apparatus and the environment, we find more events popping up, and we turn out to be justified in regarding this event as a ready state of the apparatus and this event as a record. Because our probability rule implies this, which we can read as saying, given that the apparatus is in its ready state, the record is perfectly correlated with the outcome. Okay. So if you're with me so far, then now that you've got used to wearing these new glasses, you might be able to see the possibility of a dynamics first approach to quantum theory popping out at you. And I'm calling that causal quantum theory. So, making this explicit. Something that John and I proved in our paper is that at least in the finite dimensional case, all quantum predictions are reproduced in this formalism. We haven't done the infinite dimensional case, although this is something I'm currently working on, and there don't appear to be any problems so far. But what it means is that at least in the infinite dimensional case, it is possible to regard the causal decoherence formalism as supplying us with a realist interpretation of quantum theory. So what I mean by that is a mathematical formalism which makes clear a way that the world could possibly be, and in doing so reproduces quantum predictions. So explicitly, causal quantum theory says that reality is described by a unitary circuit and the histories that emerge from it via causal decoherence. Relative to any set of systems, exactly one history from the preferred consistent set will happen. The probability for a given history to happen is given by this probability rule. Maybe I should just emphasize exactly what kind of role the history sets are playing in this interpretation. So two things are true at once here. On the one hand, there's no unique history set because there's a different history set relative to any set of systems. At the same time, relative to any set of systems, this interpretation is asserting that only one history is going to happen. We're not doing the Everettian thing of saying that all of the histories happen. Only one is going to happen, and that is what the probabilities are for, right? It's a stochastic theory, and the probabilities are for the chancy event of a given history being selected from a history set. Okay. Now, I promised you that causal quantum theory was going to provide you with an answer, a well-formalized answer to this question of what could dynamics be without rules governing states. Well, in some sense, I've already answered this question by showing you how the causal decoherence formalism works. But to make it explicit and to give it a cute metaphor, EQT dynamics is the mother of histories, right? Because the circuit is not something that you put a state into and then governs how the state evolves. The circuit's just there, kind of like how we might have once thought that the state was just there, right? Or the initial state of the universe. Here, the circuit is just there, but it gives birth to these histories. So it's a view of dynamics which maintains the idea that it's closely connected with kinematics, but it inverts the traditional relationship. Here, dynamics are the fundamental thing, and the kinematical space is emerging from the dynamics. So that's why I call CQT a dynamics first interpretation. Now I'm almost out of time, but just before ending, I want to use this interpretation to bust a couple of myths from the first century AQ. Now, many of these are things that, well, all of them, I'm sure, are things that not everybody has always believed, but nevertheless, for each one, I think it's fair to say that the discussions we have in quantum foundations often appears to reflect a belief in these myths. So myth number one is that unitarity implies determinism. The argument seems straightforward. The unitary dynamics act deterministically on the quantum state. And therefore, any interpretation in which the unitary dynamics are complete and universal is deterministic. Okay, so obviously that first statement is true. But that inference to the second statement actually presupposes the dynamics, the state first view of physics, right? So, oh dear, it's not very responsive. Okay, so correction. In quantum theory, the unitary circuit is the mother of histories. Relative to any set of systems, only one history will be born, and which one is a matter of chance. So it's a counterexample to the claim, right? Causal quantum theory is a theory where all the dynamics are unitary. We're just using unitary circuits, but the role of the circuit is to give birth to histories and to do it stochastically. The second myth from the first century after quantum is that being realist about quantum theory means being realist about the quantum state. Well, in CQT, there is no quantum state of the universe, and generically, there's not even a state of a given system within it. States appear as tools for calculating conditional probabilities for events in those places where non-trivial events emerge. And those events are only going to emerge in places where non-trivial decoherence is happening because of the causal structure. So I wouldn't say that this theory is one that is realist about the quantum state. And yet it's clearly realist about quantum theory, right? It describes a way that the world could be, and that description is given purely in the language of unitary circuits and consistent histories. Okay, note also that states in this theory don't correspond to overlapping probability distributions over hidden variables or additional variables. And this allows us to reject a dichotomy from the Harrigan-Speckens ontological models framework, right? In CQT, the state is not psiontic or psi-epistemic, it's psi neither. I'm not comfortable with either term describing the role that it plays. It's just a bit different because things work differently in a dynamics first perspective. Now, myth number three is that realist interpretations of quantum theory are limited to the big three. The argument would go like, if there are no hidden variables and all the dynamics are unitary, then we live in a branching multiverse. Therefore, every realist interpretation must be something like a pilot wave theory, something like a collapse theory, something like the Everett interpretation, or some sort of combination of these sort of approaches. Yeah, both of these claims are false, and oh dear. Yeah, in CQT, although it is a multiverse theory in a broad sense, it's not a branching multiverse theory. Okay. So remember the point earlier that unitarity does not imply determinism. In CQT, there are no extra variables we're adding to the formalism. We're not doing anything to restrict the unitary dynamics. And yet it's not a branching multiverse theory because it's not a theory of a quantum state evolving unitarily. I mean, one of the lessons here is who believes that the unitary dynamics are complete and universal. That doesn't mean that you have to believe the universe is a unitarily evolving quantum state, hence doesn't commit you to a branching multiverse. And so closely related is this final myth that I'll mention, which is taking quantum theory literally means being an Everettian and thus accepting a radical interpretation of probability. Well, I believe that CQT has at least as good a claim as the Everett interpretation to take quantum theory literally, right? Again, the mathematics, it's just unitary dynamics and consistent history sets. And yet CQT is genuinely stochastic and is compatible, therefore, with pretty bog standard interpretations of quantum theory. Okay. And so you might provocatively ask the question, given that, is there a good reason to prefer the branching multiverse approach over CQT, given that they're both taking quantum theory literally, but only one requires this radical interpretation of probability? All right, now to close, what should we make of CQT? Well, although I might have been extolling some of its advantages just now, I do want to emphasize that it's not without its problems. It's a very metaphysically radical theory, right? Radically relational. We're just saying completely different histories happen relative to different sets of systems. And as Emily explained at length, relational interpretations often get led into epistemological problems on account of their relationalism. So it's not clear to me by any means that this is actually an adequate interpretation. Nevertheless, as John was saying, I hope that CQT could be the path to a deeper theory, where rather than these different sets of systems feeling like just completely different parts of reality, we can view them as something more like different reference frame descriptions of the same underlying ontology. All right, but regardless of whether or not there is a deeper theory, it's still interesting to know about this one, because CQT has already busted a number of myths from the 1st century after quantum, and it's taught us a valuable lesson for the 2nd century AQ, right? If you don't want to view dynamics as the governor of histories, then there is actually an alternative conception which you can pin down mathematically using quantum theory, and that's this idea that dynamics could be the mother of histories. Thank you.
That's a fascinating talk.
Thank you, Nick. That was fascinating.
Thanks.
I have a question on which I would like to hear your comments. In the traditional approach to decoherence, and I'm thinking of some of the quotes you showed us from Zurich,
yeah,
and others. Decoherence is a time irreversible kind of process.
Mm-hmm.
I mean, Zurich talks about the destruction of coherence.
Right.
That's what the word really means.
Yeah.
So there's a loss of information going around, and that's why you will never expect that these systems would recohere.
Yeah.
Now, in a unitary framework, where every process is just described by unitaries, there is no loss of information. And,
right.
and I understand from what you and Matt have been, Lucien have been presenting, you could even do it in a completely time symmetric way. So what happened to the time asymmetry of decoherence? Is that another myth?
Right. Okay, maybe what I would say about that is, some people like to talk about quantum theory as an omelet that scrambles together inferential concepts, epistemic concepts, and ontological concepts. And I think that one of the issues with Urich's notion of decoherence, which I think is sort of kind of trying to be dynamics first, but at the end is still kind of state first, is that it is a bit omelety. There are ontological notions in there, but also epistemological ones. So Zurich, it's not our idea that the unitary dynamics alone select preferred bases. Zurich got there like about 50 years ago or so. And that bit of it, right, that form of the interaction Hamiltonian, that's a time symmetric statement, right? So the causal structure, the process responsible for decoherence is perfectly time symmetric. If it's decohering in one direction of time, then it also is in another. So where does the time asymmetry come in? Well, I think it comes in with the state, and in particular with initial states. It comes, I think, in the need to have the right sort of initial state of the environment in order to see the suppression of off-diagonal terms in the density matrix. Yeah.
Yeah, I mean, Jos more or less asked the question I was originally going to ask. Let me ask something different. I mean, in terms of the list of myths, so we knew since, as you know, since the 90s, we had the consistent history of formalism.
Yeah.
And so it was always true. There was a class of interpretations that were consistent history interpretations. And you can map those, you could call, I mean, most naturally you'd call those stochastic interpretations in a normal trichotomy. But the concern and problem of that approach was that it wasn't clear what the sharp precise definition would be to choose a particular consistent history space, and hence to some extent the sort of Galman-Hartle style emergent stories that Simon and I sort of borrowed for the Everett interpretation.
Yeah, indeed.
But I mean, it's not. This isn't a criticism of the approach. The framework you're setting up is fascinating, but it's not. It's not clear that those, if those were myths, why weren't they just busted by consistent history formalism and that approach in like 30 years ago?
I'm absolutely. I mean, I think in fact they were, strictly speaking. So it's not that with any of these myths I think that they were universally believed. Nevertheless, despite the fact that unitarity implying determinism is a myth, and it's one that really has been busted for a long time. Nevertheless, in discussions of quantum foundations, we are often talking as if it's true that unitarity implies determinism, and it's a myth that is closely related to this big three myth that these are your only options. Now, you could ask, why do we often persist in talking like that, even though it's not true and it's been obviously not true for a while? And I suppose that's because many people don't find these kind of many histories interpretations of quantum theory based on the consistent history of formalism overly plausible. And I think that although, as I've emphasized, CQT still retains problems of its own, I hope it's done a lot to address some of the key concerns with kind of consistent histories-based formalism in deriving, at least relative to a set of interacting systems, a unique consistent history. So hopefully, although we have, logically speaking, already had counterexamples to this claim before, hopefully this is a slightly more compelling counterexample.
This is very interesting, and I'm trying to understand it. So you said that reality is described by a unitary circuit. So my understanding of what a unitary circuit is a picture with lots of lines on it,
right?
And operators associated with each of these lines. How do the lines and the operators describe anything?
Right.
What is the notion of description that's at work here?
That's a really good question, and maybe one that I'm not philosophically sophisticated enough to answer in a really satisfactory way. But what I can say is this: I suppose that there are two ways of trying to really get an understanding of what kind of thing of what kind of thing this unitary circuit, what kind of thing this primitive dynamics can be. So one thing that we can do is we can attempt to understand it on its own terms, right? Which I think the only way that we can do that is by understanding our mathematical representation of the thing. Now, when it comes to understanding what a circuit is mathematically, really the sort of picture with the boxes, I don't really think of that as being the fundamental thing. That picture has a semantics, and the semantics is really, it's a directed graph over operator algebras. That's precisely what it is. Every wire is associated with an algebra of operators, and the sort of connectivity of the circuit defines, there's a directedness when two algebras don't commute with each other. And so from any circuit, you can extract a directed graph of algebras. In my thesis, I actually formalized this interpretation of using the directed graph because I think that's more fundamental. It's also more general. Nevertheless, I find pedagogically it can be helpful to start with the circuits that you get these things from. Okay, but that's all trying to understand the thing on its own terms. Another way that you can try to understand what these dynamics are and how they could possibly represent reality is you could just try to understand the the story by which it makes contact with notions with which we're more familiar. So, you know, you can understand the circuit as just whatever it is that gives birth to all of these events that we appear to directly experience. Yeah, and those are really the only two ways we know of making sense of this claim that the dynamics exist in our fundamentals.
Thank you.
Okay.
Hi. Yeah, thanks very much. I really enjoyed the talk. I'm still trying to get my mind around the claims and achievements so far of CQT. So yeah, I wanted to follow on David's comment about comparing and contrasting with consistent histories. I think I agree, but I think you also agree that the claims on this slide and the previous myths were when a consistent historian would have said we've already made those points.
Yeah.
So the pros, would this be right? The advantages here are something like it gets perhaps closer to a solution to the set selection problem. And possible disadvantage, at least as the way it looks at the moment, is unlike big histories, it doesn't look terribly well adapted for talking about quantum field theory with low quantum gravity or events in space-time. At the moment, it feels very sort of circuit-based and intrinsically non-relativistic. What are your thoughts on that? Because
yeah, well, for the first part of the question, yes, I agree. In terms of compatibility with QFT, I mean, maybe this would be, you know, I'd be very interested to discuss this further with you. But when you say that a circuit doesn't feel well adapted to quantum field theory or quantum gravity, does it help at all if I say that it's not a circuit, that I say it's a directed graph of algebras, that I say it's just about operators not commuting with each other?
not sure.
Yeah. So that's the way to think about it.
Thank you.
Thanks. Okay, our very final talk, this wonderful conference, we have Chris Fuchs from UMass Boston, and he's going to be taking us from Wheeler to Cubism and back to Wheeler.
I'm glad there's still some people here. This is good. Oh, so Chris asked me to say something about what's going to happen in the next 100 years of quantum theory, and I thought, well, I'll talk about cubism. Actually, I thought about this morning. I thought about a thing that Paul Simon said to a seminar of the students, teaching them how to write songs, and he said that the main message he tried to give the students is that to start a song, you should say something true, and then after that, the song will somehow flow. So I spent the better part of my day nursing my hangover from last night, trying to think what can I tell you guys that is true to get this talk started. And my mind went back to September 11th, 2001 in Belfast. So you might recognize the date, September 11th, 2001. I had a conversation with Nicolas Gissen, and Gissen told me that the only thing that was making the kind of proto-cubism that Asher Perez and I were developing, the only thing that made it credible were his experiments. He was trying to show that there would be some flaw in quantum mechanics that would then make it all sensible. But because he wasn't finding any deviation from quantum theory, that helped give our point of view some credibility. And then he said, you should cite me more. Well, there have been a lot of no-go theorems recently, and probably I should cite them more, because from time to time, somebody like Matt Leifer will say, I think Matt has said this before, because these theorems make people question the absoluteness of observed events, it gives cubism more credibility than it had before. I've always thought of cubism as a kind of ansatz, and consequently, I tend to ignore the various developments that everybody really gets into, like in some of these talks. I'm sorry, Eric, I missed your talk, but I know that Eric likes to really pick apart all of the details in the various no-go theorems. I tend to ignore all of that because I think of cubism as ansatz here, a definition I looked up, a proposed form or assumed expression for a quantity function or solution made before solving the full problem, often guided by intuition or symmetry. It seemed to us, and I'll give you some of the history of it in this talk, it seemed to us that it was a good way to proceed, and we would proceed along this route so long as we didn't find things breaking. So that's what I'd like to do. I'd like to, in the talk, give you some sense of where cubism came from, and then in the very last bit, I'll talk about the thing that will be occupying us for another 100 years. Where did it start? Well, if you read David Deutsch, this is something I found on the web just recently, great quote. He says, traditionally, science was just straightforwardly understood as being a project of understanding the world. But in the 20th century, for various bad philosophical reasons, people started to question that. In quantum mechanics, things have gone wrong thanks to that bad philosophy. I've seen other things that Deutsch has written that are more directly about cubism, but so I thought actually it's worthwhile trying to figure out whether he was thinking about cubism here. So I went to ChatGPT and I said, would David Deutsch think cubism is an example of bad philosophy? ChatGPT said the short answer is yes. He would reject its core premises as fundamentally misguided and a retreat from the goal of objective science. In his mind, and I wish I had a better quote of it, in his mind, we were distorted with bad philosophy. We read Bohr and that was that. Well, I think that was just spoken from ignorance. I would gamble that David Deutsch has never read a single paper on Cubism. I just gamble that. I don't know. Cubism, I would say, wasn't at all the progeny of some predetermined philosophy. It came from a physicist following his nose in the search of a better physics. If philosophy can help, then so be it. And I have reached out to philosophers for 30 years now. If it can help, so be it. But no specific philosophy was at the root of Cubism. Instead, really, the story starts in 1973. I was a big fan of science fiction movies. I lived in a small town in Texas, and we got 3 television stations, all from San Antonio. And on Friday nights and Saturdays, they would show old B movies about space exploration. Excuse me. In 1973, Star Trek came to town. And I can remember running home at the end of my school day in 3rd grade, and so I could see my first episode of Star Trek. I fell in love with the idea of traveling to the stars, not limited by the speed of light, but traveling to the stars very quickly. And so somewhere in junior high school, I started to think, we had stopped sending people to the moon by then. And if we're going to get to the stars, we'd really better get busy. So being a junior high student, I thought I would take on the task myself. I would read as much as I could. And in fact, I read a lot of Paul Davies books in that period to learn, what could get us to the stars. And so in the process, I learned about black holes. I learned about wormholes, white holes. And I even remember by interlibrary loan, I got a copy of John Wheeler's book, Geometrodynamics, even though, I knew no tensor calculus, but I looked at the pictures and I salivated. This has got to be very, very important stuff. Wheeler, in the process, sort of became a hero. Oh, this is now not working. No, latency. Well, everybody can guess that's John Wheeler. Maybe I don't need to point at anything. Wheeler sort of became a hero, but at the same time, I was really disappointed with everything that I learned from these books, because I learned that basically physics wouldn't allow us to get to the stars the way I wanted to. This is all relevant to Cubism. Believe me, you'll see. I realized physics wouldn't allow us to get to the stars. At some point, I remember talking to my best friend. We're pictured here, and I don't recall exactly which year it was. I remember saying to him, if the laws of physics won't let us get to the stars, then the laws of physics must be wrong. I was semi-serious about that. Now, this event in June of 1982 was significant, actually, because we were elected to go to a kind of Hitler youth camp in Texas called Texas Boys State. It was hosted at the University of Texas. And, you got up, you did calisthenics, and then you acted like a politician all day. And that's when I really realized I hated politicians. They would give us some free time every day where you could do anything you wanted. So I would go to the physics library in Robert A. Moore Hall and just look at the book and go, oh, there's got to be nothing better. And somewhere during that free time, one of the days, I thought, John Wheeler is here and he's my hero. I should meet him. So I traipsed up to the 9th floor of RLM, and I went to Wheeler's office, and his secretary, Zelda Davis, had the office in front. And I said, I'd like to meet Mr. Wheeler. And she said, oh, I'm sorry, he's not here today, which in hindsight was a really good thing, because I think if he had been there, I just wouldn't have known what to say to him, and it would have been a very awkward meeting. But there was a table of preprints. I said, what are these? She said, these are papers that anyone can take. And I said, can I take some? So I took them. Among them was this one little booklet called Physics and Austerity, Law Without Law. And I started reading it right away. I took several papers. But Wheeler was saying things like this. Is the foundation of physics not a great equation that has to be sought out and written down, but a great higgledy-piggledy built on choice and chance, law without law? Today, we recognize that the universe came into being in a Big Bang. There was no tablet of granite with the laws chiseled on it in advance. In summary, actually in a different paper, he says, no law or no law except the law that there is no law. I melted when I read this sort of stuff because here I had been saying perhaps the laws of physics were wrong. And this man went further. He said, perhaps there are no laws of physics. And I thought, in a world with no laws of physics, God knows what you might get away with. So that was really cool, and that was very influential. And I think that Cubism has carried some amount of this forward ever since. I was quite taken with that, and I wanted to somehow formalize this notion of how it could be that we apparently have the laws of physics, but underneath it all, we actually don't. And an important event occurred when I ran across this book by Rudy Rucker, 1986 or 87, as best I can recall. And there was just a short, most of it wasn't about quantum mechanics, but he wrote, randomness is not usually an axiom explicitly assumed in quantum mechanics, but there is a strong feeling that the behavior of a hydrogen atom is, in principle, unpredictable. So we would expect most of the hydrogen atoms to be generating random real numbers. There's one theorist, Paul Benioff, I think someone mentioned him in, is she here? Anyway, there is one theorist, Paul Benioff, who has tried extending quantum mechanics by explicitly assuming that such hydrogen sequences would be random in the sense of answering to no finite description. So Benioff had this idea that if, for instance, if you measure a spin, in this basis, but the spin is prepared in that basis, there's a 50% chance of getting either up or down for the spin. You measure the spin and you get zero. You get up. You measure it again, you get up. Measure it again, you get up. That's possible. Benioff thought it's not possible. Ultimately, every sequence that's generated from quantum mechanical measurements must be random in some formal sense. Well, I liked that idea. So I just started reading everything that I could about this kind of idea of random sequences. It kind of led me down a rabbit hole. It led me to thinking about lots of things. Benioff's papers were actually barely understandable, but it took me to von Mises' notion of probability, where an infinitely long random sequence was the basis of the theory, and then probability came second. I had this crazy idea that perhaps a quantum state was formally identical to one of von Mises' collectives. So a quantum state in some way captured the idea of an infinite sequence. So that led me to study these things. I was rather attracted to Roger Penrose's U and R processes because I liked the R. I liked the R process. Ultimately, in trying to formalize these things, I started reading the papers of Greg Chaitin and Leonid Levin, and it was because of reading those papers about algorithmic randomness that I ran into Carlson Caves. When I met Carl Caves, I should tell you there was an undercurrent already happening because of Wheeler's influence, and that was that Wheeler was asking everyone around him, can you give an information theoretic reason for quantum theory? Quantum theory is surely derived from a deeper principle, and that deeper principle must be of an information theoretic flavor. In fact, one of his PhD students, Bill Wooters, wrote a PhD, wrote a thesis on an attempt to derive quantum mechanics from an information theoretic principle. And it worked. It worked for real Hilbert space quantum mechanics. It didn't work for complex regular quantum mechanics that we know. So anyway, there was this sense that somehow, there was the law without law idea, but there was also the idea that quantum mechanics comes from information theoretic things. I ran across a paper by Sam Brownstein and Carl Caves about information theoretic Bell inequalities, and I thought, that's it, finally. Somebody is talking about the right sort of stuff. So I went to work with Caves. I abandoned my first graduate school where I was doing general relativity and went to New Mexico to work with Caves, but he didn't like any of my ideas. In fact, he hated them. He would say, Fuchs has dangerous frequentist tendencies. And indeed, I ultimately learned that I had, and that they were just inconsistent. Caves recommended a strict regimen of reading E.T. James, a Bayesian and a physicist. But at the same time I was reading James, I still had this deep desire for objective quantum states giving rise to objective probabilities and how best to understand that. So I read papers by Popper, Pat Suppies, Ronald Hira, and Hugh Mellor. And my motivation was much like I still hear today. Quantum probabilities are given by physical laws, so they must be objective probabilities. So trying my best to make sense of the propensitists, actually I came up with the negative conclusion that propensitists are really closet frequentists, and they didn't add anything to the point of view, or they didn't save frequentism from any of its inconsistencies. So I started to take James more seriously at Caves's insistence. Around 1994, came across a paper by James on probability theory, on quantum mechanics. And this famous quote is, our present quantum mechanical formalism is a peculiar mixture describing in part laws of nature, in part incomplete human information about nature, all scrambled up together by Heisenberg and Bohr into an omelet that nobody has seen how to unscramble. Yet we think the unscrambling is a prerequisite for any further advance in basic physical theory. Or if we cannot separate the subjective and objective aspects of the formalism, we cannot know what we were talking about. I finally got the vibe. Quantum mechanics is a mixture of two things, subjective and objective. And if we really want to understand quantum mechanics, we had better recognize that it was the mixture of these two things and do our best to try to pull out the subjective and throw it in the trash bin if we wanted and get the objective stuff, because we want to know, as physicists, what is reality. Despite what David Deutsch says about me, I want to know about reality. So taking quantum probabilities to be subjective is not giving up, not in my mind. It was only displacing the question. It was clearing the underbrush so that we had a chance of seeing what was real in quantum theory. Now, under the influence of James, the natural place to start was to say, oh, well, at least we know that probabilities, James was preaching Bayesian probability, at least we know that probabilities can't be objective. So anything that has some statement about probability, let's pull that out and label it part of the subjective. So going back to quantum theory, of course, we all know this. What do you do with quantum states? Well, you calculate probabilities. So from quantum states, you get probabilities. But because of quantum information theory, we started to learn in those early days, reciprocally, if we consider a robust enough set of measurements, they uniquely determine the quantum state. It doesn't take too many measurements. You don't have to perform an infinite. You don't have to consider an infinite number of measurements, just some well-placed measurements. They imply a quantum state. So if probabilities are taken to be subjective, well, the idea was quantum states would inherit whatever character the probabilities do. So we kind of came to the vision that quantum states must be somewhere in the spectrum of information, Wheeler's preferred term, knowledge, that was more Jaynes. Jaynes would talk about probabilities as states of knowledge. Belief, that was Frank Ramsey and Bruno De Finetti, are somewhere, even looser than belief, just a pragmatic gambling commitment because it's convenient. It took a long time to home in on where we should be in understanding probabilities. But in the meantime, we were doing things. And one example, there was something that started to sort of click in me. I would read statements like these two that I plucked off the web last night. Zurich also demonstrated with Wooters that an unknown quantum state cannot be cloned. This is a fundamental result, an essential distinction between classical and quantum information. Or here was something from Scott Aronson. The subject of this talk is a deep theorem that stands as one of the crowning achievements of our field. I refer to the no-cloning theorem. I'd like to pose this question. Why should our universe be governed by physical laws that make the no-cloning theorem true? So over and over in quantum information, I would hear that the no-cloning theorem really set quantum theory apart from classical theory. But maybe that was just a misconception and that this wasn't one of the crucial things that sets it apart. Particularly, I was under the influence of Asher Perez and Michael Berry, reading some papers about quantum chaos at the time. And this comes from Asher Perez's book. Perez points out the classical analog of a quantum state. He was big on this. The classical analog of a quantum state is a Liouville distribution, not a phase space point. If two Liouville functions are initially concentrated around neighboring points with some overlap, that overlap remains constant in time by virtue of something he called Koopman's theorem. It's just really a corollary to the Liouville's theorem that volumes are preserved. One of the Liouville functions may become distorted beyond description, yet the overlap of these functions remains constant, as illustrated in this figure. So the overlap, there's some overlap between, I don't know if I have a pointer there, and these two regions get immensely distorted, but the amount of overlap in them, between them, stays constant. So one night I was screwing around, procrastinating from writing my thesis, and I was thinking, Perez is right. We should think of all the things that we see in quantum information that might have a simple explanation if we just recognize that quantum states are epistemic, that they're states of knowledge. And I thought about the no-cloning theorem, and it hit me. What powers the quantum no-cloning theorem is that overlaps are preserved. What Koopman's theorem says, overlaps are preserved for Liouville distributions. There is nothing uniquely quantum about the no-cloning theorem. This hit me. It follows simply by quantum states being states of knowledge. Oh, how much might that clarify? Well, it turned out that to us, Rudiger Schoch and me, Howard Barnum, that it had an immediate explanatory power. We could explain a number of things in quantum information that people were considering mysterious, like, for instance, quantum teleportation. And we could say, the root explanation of quantum teleportation is exactly the same as in the no-cloning theorem. States are epistemic, simple, makes it easy. So it had immediate explanatory power. Hayes, David Wallace, who says, cubism has no explanatory power. It has the explanatory power for some things. It didn't stop there. You had the power to lead. So realizing the no-cloning theorem just comes from the epistemic nature of states showed me that the point of view had teeth. But it became more pronounced as we started to appreciate the holding on to the view consistently, even though, I'm from Texas, and we have rodeos there, and people stupidly get on top of bulls and try to hold on. And then the bull throws them off and stomps on their head. Well, okay, so I had this idea that we'll do this with the epistemic nature of quantum states. And here was something that began to bother me, really bothered me. Everybody was talking about unknown quantum states and quantum information. You try to clone an unknown quantum state. You teleport an unknown quantum state. You protect unknown states with quantum error correction. So there was this phrase, unknown state, everywhere. Well, wait a minute. If a state is someone's knowledge, how could it be unknown? So what's being referred to here? The most extreme example of this was quantum state tomography. The usual story is there's a device that's creating little buckets full of quantum states and sending them out. And there's an observer on the outside, and the observer wants to know what state is being prepared over and over and over. The observer doesn't know the quantum state. Well, how did the quantum state get in the buckets? Well, the only thing that I could initially imagine was there was a little Maxwellian demon in the box. And what the observer on the outside was trying to do was he was trying to find out the state of mind of the demon that's on the inside of the box. Well, that's stupid and silly. So there must be a better explanation. But I didn't know what it was initially until I ran across a philosophical paper by somebody named R.B. Braithwaite. In this case, Cubism did have some help from philosophy. He was a philosopher. He introduced us to the notion, or to something called Di Finetti's representation theorem. But in the rest of the paper, he explained that it was bad philosophy. Well, okay. Knowing that the theorem existed led us to a way to reconceptualize quantum state tomography. What quantum tomography is really about, there's nobody on the inside of the box. And the guy on the outside of the box doesn't have a question mark trying to figure out what the unknown quantum state is. Rather, the guy on the outside of the box says, in all of these boxes, let me assume a quantum state assignment for the whole thing with the following symmetry requirement, that if I interchange any two of the systems, my quantum state for the whole will change back to itself. You can prove that if you make that symmetry, that any two systems can be interchanged, then this quantum state, it's a mixed state, can be decomposed into an integral over a probability distribution of many copies of a single state. So there's your unknown state. It's not a real thing. It's just part of a representation theorem. So this was good. We now had a theorem in physics that didn't seem to exist before. Well, we did find out that Hudson and Moody had proven it. But we had a new theorem about quantum mechanics that was motivated by trying to make our point of view consistent, get rid of the word unknown quantum state. We found new physics, and that new physics ended up being pretty important for analyzing the security of quantum key distribution. And it's had other uses since, but the point was, from the interpretation, we found new physics. So we finally came out with a mission statement in what year was that? 2002. We finally wrote a mission statement, Quantum Probabilities as Bayesian Probabilities. We were all younger. We wrote this paper. It gets cited. It's one of my most cited papers in Cubism. But here's the problem. Everything about the paper was just wrong. And it's a shame that the damn thing is still cited as the founding of Cubism, because really it was thoroughly inconsistent. In patching all of the inconsistencies in it, it actually required us to move far beyond E.T. James's notion of probability. we became attracted to Bruno De Finetti's notion of probability. He famously opens a book by one of his books by saying, "My thesis paradoxically and a little provocatively, but nonetheless genuinely, is simply this: probability does not exist." What De Finetti meant was that probabilities are never factual features of nature. If an agent writes down a probability distribution, there is no sense determined by nature, no sense in which the agent is right or wrong. Probabilities are not active, a term that Chris Timpson taught me quite some years ago. Probabilities are not factive. Now, remember this thing about quantum states imply probabilities. Probabilities, in turn, imply quantum states. Well, there was nothing to do but to realize that actually the ghost of De Finetti is still here in quantum mechanics. Now his thesis, paradoxically, provocatively, etc., is that quantum states do not exist. In other words, we ended up with the point of view that quantum states are never factual features of nature. They're not factual features of nature when they're mixed states, and they're not factual features of nature even when they're pure states. Let me show you the sort of argument that would lead one down that path. Consider the following situation. Suppose there's some Hermitian operator. I'm going to draw an orthogonal basis here, for which, forget about quantum states. We don't know about quantum states yet. I am absolutely certain that this outcome will occur for my measurement. Suppose I am. I'm absolutely sure this outcome will occur. Well, from Gleason's theorem, then you know there is a unique quantum state assignment that will make probability equal 1 in that case. Suppose you had the idea, okay, 50-50 is a subjective state of mind, but 1-0 is a fact. Suppose you had that idea. Well, so then that would mean that the probabilities of 1s and 0s over there, they make a unique quantum state. That is factive. That would make a quantum state factive. But then the problem is if you consider the measurement of some other basis, now the probabilities are no longer 0, 1. They have to be subjective. In other words, you're assuming that those aren't factive. So you get that 0 and 1 are subjective judgments as well, and even pure states are subjective. Well, it turns out we weren't the first ones there. It was said by philosopher Richard Jeffrey much more clearly. The Bayesian framework replaces affirmation and denial by a continuum of judgmental probabilities in the interval 0 to 1, endpoints included, or what comes to the same thing, a continuum of judgmental odds in the interval 0 to infinity, endpoints included. 0 and 1 are probabilities no less than 1/2 or 99/100ths are. Probability 1 corresponds to infinite odds. That's a reason for thinking in terms of odds, to remember how momentous it may be to assign probability 1 to a hypothesis. It means you would stake your all on it, but it doesn't mean that it corresponds to truth in the mathematical sense. Once this was realized, what could we do with that? Well, let's go back to the EPR criterion. If without in any way disturbing a system, one can predict with certainty, i.e. with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to that physical quantity. In the hands of some people, like Tim Maudlin, it leads people to say, oh, there's non-locality in quantum mechanics. What Bell proved and what theoretical physics has not yet properly absorbed is that the physical world itself is non-local. He bases that on part of Bell's argument and the EPR criterion of reality. There's one paper where he says, if I could make one change to the EPR paper in retrospect, it would be to alter the characterization of the criterion. The authors call it reasonable and in agreement with classical as well as quantum mechanical ideas of reality, but its status is actually much stronger than that. The criterion is, in the parlance of philosophers, analytic. That is, this criterion follows just from the very meaning of the words in it, very meaning of probability 1. Well, that's not the meaning that cubism adopts for probability 1. Well, philosophers of physics didn't much like this. And I suspect that most of you out there that are philosophers of physics still don't like this. But, you know, I have found myself wondering, what would Wheeler say? Would John Wheeler like this? Well, you know, you shouldn't look to your heroes for solace. Probably not. Not in 1976, at least. Here's a notebook entry from March 14th, 1976. Wheeler writes, in the seminar, Wednesday, 10th March, 7:30 to 9:30. I am almost surprised that Wheeler didn't write down the room number. Because he was, if you look in his notebooks, it's just amazing. He'll write down what room number in what hotel he was in, at what time, 3:25 a.m., Hotel Bellagio, something, and you know, give us the room number, and then he'll write. In the seminar, Andrew Redfield claimed that the wave function represents the state of our information about the electron. I agree. But there's a different wave function for each observer because each observer has different information about the electron. I disagree. If quantum mechanics is a magic clue to the great mysteries, it ought to be especially so on this aspect of observership. So here's a quantum system, and I would say, or in cubism, there are potentially as many quantum states for that single system as there are agents paying any attention to it. So I would agree with Redfield here, though I wouldn't call it information. Wheeler didn't agree, not in 76, but you can see in his notebooks that he struggled with this and he wavered for the rest of his life. You know, was it the case that quantum states were not unique, or was it the opposite? And we'd go back and forth. Well, so maybe Wheeler wouldn't like that part of cubism, but cubism has been going back to Wheeler, and particularly in trying to give a better explanation of, well, what are these probabilities about? The trouble for cubism has always been its very dogged consistency. And you know, a lot of people get happy in life, like Asher Paris, my old friend, was very happy in life because he had made his peace with quantum mechanics, but it wasn't consistent. Or at least I didn't think that it was consistent. I have been tortured all my life because I keep looking for consistency in the views. And here was one. Quantum states couldn't be objective. They had to be non-factive. If you run the argument about, well, where does the quantum state come from? It might come from a collapse rule. Oh, the collapse rule then can't be objective. And where does the collapse rule come from? And you can give a number of arguments that basically, once the quantum states are not assumed to be objective, basically all of the rest of the structure topples with it. One of my favorite ways of seeing it actually was suggested by Lucian Hardy in, I don't know, when it was basically when Hardy and I first met. He wrote a paper where he showed a way of thinking of quantum theory in purely probabilistic terms without ever mentioning quantum states. He had a description of dynamics in probabilistic terms. There were only probabilities in it. Now, my favorite way of drawing this sort of thing is to sort of generalize the double slit experiment and using tools from quantum information. In place of just having a detector at 2 slits here, we have an informationally complete quantum measurement. And so my system goes through, quote unquote, the slits and then ends up on a screen, AKA another measuring device. We can consider the situation where there are detectors at the slits. Don't take that seriously. They're not really slits. It's an informationally complete measurement. And we can consider the case where detection is not being made. It turns out that the probabilities for this case where you're not measuring the informationally complete measurement in the middle, you use the Born rule. You take the quantum state, it's rho. You take the measurement operators, the EJs, take the trace of the product of them, that is the Born rule. That leads to some probability assignments for the outcomes Q of EJ. It turns out you can calculate this same number, Q of EJ, in terms of the probabilities from this alternate experiment. Not this experiment, but from the alternate experiment. And what you get is a formula that looks very close to the law of total probability, except it's got this annoying sort of matrix in the middle that's not the identity. If the matrix were the identity, then it would be the law of total probability, but it's not the identity. Well, Feynman, famously said about the double slit experiment, that contains the only mystery. This is generalized. It's not the double slit experiment, but it does capture a way of expressing the Bohr rule that always works. It's only in terms of probabilities and this extra matrix of real numbers. What are the metaphysical implications of that sort of thing? Well, on the left-hand side, we've got the probability for the outcome of the final measurement. On the right-hand side, we have the probability for a reference measurement, then this phi, and then a conditional probability. I wish I could reach it. The conditional probability for the second measurement given the first measurement. The P of R specifies the quantum state. If you know the probability distribution, you know exactly what the quantum state is. The P of E given R, if you know all those conditional probabilities, they uniquely specify what the measuring device is. So here we've got this situation where a measurement device is uniquely characterized by a set of probabilities. What does that do to the picture of what a quantum measurement is? Niels Bohr would always draw measuring devices as these big, heavy things that were bolted to laboratory tables, very solid sorts of things. In cubism, we say, well, from the formalism and from other arguments as well, you can see that a measuring device is a specification of a conditional probability distribution. And if you're a subjective Bayesian, there is no unique conditional probability distribution that can be written down. So the solidity of Bohr's picture was always an illusion. It's just as diaphanous as a probability assignment is in subjective Bayesianism. So we're left with this distinction from Bohr. Quantum measurement outcomes could not be, to paraphrase Bohr, it couldn't be instances of irreversible amplification objectively recorded for everyone to see in a device whose design is communicable in common language, suitably refined by the terminology of classical physics. Guido, did I do that relatively accurately? So it is a hodgepodge of things that Bohr would say. I put them all together. But I promise you, he used every one of those words at some point. So in cubism, a measurement cannot be that. It can't be this thing that's solid and can be communicated. It's a prior probability. And if I, for instance, wanted to communicate my prior probability to Guido, and he's an experimentalist, well, he would combine my probability, my subjective probability with his subjective probability. There's nothing solid in either way. It's not you can't just draw a blueprint. A probability distribution is not a blueprint. So it required a divergence from Bohr. Actually, one of his proteges gave the crucial idea. In a letter to Bohr in 1955, Wolfgang Pauli, they were disputing a word, the detached observer. Pauli writes to him, as it is allowed to consider the instruments of observation as a kind of prolongation of the sense organs of the observer, I consider the unpredictable change of the state by a single observation. Then he says some non-cubist nonsense, which I didn't include. He said, I consider, because you can consider the instrument of observation as a prolongation of the sense organs, I consider the change of state by an observation to to be an abandonment of the idea of the isolation or the detachment of the observer from the course of physical events outside himself. You might think that I'm a bad translator by writing unpredictable. I'm not sure that's an English word. But Pauli wrote this letter in English. Pauli and Bohr would converse in their letters in English. I guess Bohr didn't speak German and Pauli didn't speak very good Danish. That's where the solution comes. What was recognized was that really there should be a change of vocabulary. One shouldn't be using the word observer. Wheeler drew this in one of his notebooks. I have it cut off, but at the top he would always write subject matter up at the top, and this one was me and the universe. There's another entry, a beautiful entry, where he writes, not one world, many. And in the very next line, he says, oh, the moment I wrote the title, I realized that I may create confusion, people thinking that I'm talking about Everett. I don't mean that at all. I had inner dialogues all the time. So Wheeler's thing was that we have to throw away the idea of an observer and replace it with the notion of a participator. Notice how Wheeler has the measuring devices on the hands. He's thinking, and this is something that Cubism has adopted, is that the measuring devices are actions that one can take on the system. One hand is F, one hand is P. You can only hit one at a time, apparently. So the idea of participator became of greater importance. Cubism ended up adopting precisely that. Here, a nice little cartoon that the guy in Switzerland drew for me. Captain Cubism. A quantum measurement, so this is Cubism's notion of measurement. A quantum measurement is any action. Do you see that? Any action. That's a quantum measurement in Cubism. You don't need a laboratory to do it. Any action an agent takes upon the world and its outcome just is the consequent personal experience this induces in the agent. I had just a little touch of pain on my big toe when I did that. So that was a quantum measurement in Cubism. Now, why would one ever use the quantum formalism? Well, sometimes you do and sometimes you don't. Whether if you're in a quantum optics laboratory, it's much more worthwhile to use the quantum formalism to make your predictions. So now let me just talk about the next 100 years. So you've seen Cubism, including questions, good. Because I don't want any questions. What are we going to do for the next 100 years? I hope I've given you an adequate sense of how Cubism developed, that it wasn't just adopting a bad philosophy. It was about trying to find new results in physics based on the demand for consistency of an ansatz. It was an ansatz. Well, Wheeler had ontological ambitions. And in fact, that's all he had was ontological ambitions. I found a couple of nice quotes. I like this one particularly from March of 1974. He says, we say the participator is made of the material of the universe. If this warrant for thinking of the possibility that the universe is made of the essence of the participator, they get stuck on this idea. What is the essence of the participator? It's difficult, now this one comes from a panel discussion, 1981. It's difficult to escape asking a challenging question. Is the entirety of existence, rather than being built on particles or fields of force or multidimensional geometry, built upon billions of elementary quantum phenomena, those elementary acts of observer participancy, those most ethereal of all entities that have been forced upon us by the progress of science? There's a nice contrast between that and something I've read in one of David Deutsch's papers. He says the Everett interpretation is forced upon us by the progress in science. And Wheeler's using almost the same phrase. He wanted an ontology, but a rather unusual ontology. something that was analogous to an agent's participation in the world, whatever that might mean. John Bell, I like the way he says this. Were we not obliged to admit that more or less measurement-like processes are going on more or less all the time, more or less everywhere? He was being sarcastic. Actually, I would say Cubism takes that notion very seriously. It strives for an ontology of measurement, but maybe measurement in a way. This is a very loose analogy. I hope that Mr. B in PBR is not offended by it. The idea is the essence of what you see in a measurement and abstract from that and say, that's what's happening all around. That's the way I kind of viewed what you and your coworker were talking about. You had the stochastic evolution. That's happening with or without agents. Well, I was wondering if somehow the notion of participation was happening with or without agents. 100 years. We got 100 years to go. Well, I would say Cubism needs help from philosophers. Here's something I put in a paper. I say that a measurement outcome just corresponds to experience. But more work should be done to find the right word for this de-anthropocentrized ontological distillate of Cubist considerations. Other potential terms are pure experience from William James, neutral monism from Bertrand Russell, phenomenon from Niels Bohr, elementary quantum phenomena from John Wheeler, actual occasion from Whitehead, interaction from Karen Barad, transaction from Dewey and Bentley, chiasm or flesh from Maurice Merleau-Ponty. I've even tried the word kubum. I don't know what it is. I don't know if you get a handle on this philosophically, except to study some of those philosophies. But keep in mind that it's about a physicist following his nose. It's not that I want to adopt any particular philosophy. There's technical work to be done. And let me just give you an example. Remember the equation for writing the Born rule purely in terms of probabilities. I think that that captures the notion of this word that I made up, participatoriality, 9 syllables, that really makes Chris Timpson stumble over them. That somehow the Born rule captures that. And if you can find the way of expressing the Born rule that gives you the minimal difference between the Born rule and the law of total probability, then you will have learned something about quantum mechanics. We think we know what the answer is, and it leads to a simple technical question. For a Hilbert space of dimension D, I'm not going to tell you how it got there, but we think we know what the answer is, and it leads to this mathematical question. For a Hilbert space of dimension D, can you find D squared projectors that have a constant inner product between themselves? Simple question. Well, it turns out it doesn't have a simple answer because a growing number of people have been working on the problem since 1999, trying to prove that these things always exist. And recently, Marcus Appleby and coworkers found that the problem turns out to be an instance of Hilbert's 12th problem that's still not solved, and it's over 125 years old, I guess. So next 100 years, some philosophy, some amount of philosophy, some amount of technical development, in the same way that Cubism has always developed. A foundational question pushed for a technical answer. Technical answer was found. Physics profited from the technical answers that were found. I wouldn't be ashamed if it took another 100 years to complete the project of Cubism. And my own arrogant point of view is if you think that you have found the final solution of how to understand quantum theory, then you're probably pissing in the wind. I expect 100 years of work from whatever point of view ultimately wins. Thank you. Yeah, didn't I use up all my time?
We have 5 minutes for some very short questions. Lots of hands. Try and maybe let people know who.
Hi, Chris. So nice talk. I'm really glad you mentioned John Wheeler, because I have a quote from Wheeler.
Are you Tim Palmer?
Tim Palmer.
Okay.
Which I'd like
I
to.
haven't seen you in many years.
No, you did. We'll talk after. I'll have a quote from John Wheeler. I'd just like to preface it by saying that a lot of the discussions we've had in the last few days have been about different ways of interpreting quantum mechanics, cubism, de Broglie, Bohm, Everett, and so on and so forth. But my quote from Wheeler is actually suggesting we might be barking up the wrong tree by even thinking about quantum mechanics as it's formulated. So he says, and this is a direct quote, the familiar probability function of standard quantum theory provide mere continuum idealizations, and by reason of this circumstance conceal the information theoretic source from which they derive. In other words, he's saying that the way we formulate quantum mechanics and the state of the quantum system as a point in Hilbert space, which is a continuum space, is itself a mistake, and we're not seeing this information theoretic aspect of the wave function by insisting on this continuum, what he calls an approximation.
Yeah.
Now, there's an interesting. I mentioned this the other day in a discussion we had, Lucian Hardy's work on the axioms of quantum mechanics, and he says the continuity of the state in Hilbert space is an important axiom. So if you put these two things together, Wheeler's assertion that the continuum is an approximation for something inherently discrete, and Lucian's axiom that what we're really looking for in trying to understand quantum physics is going to be as different as general relativity is from Newtonian physics. It's something that's not just going to be a minor tweak to Hilbert space, it's going to be something profound. And I feel that we don't, as a community, we don't give that notion enough credence and discussion. So that's my point.
Well, thanks. I don't know exactly how to respond. And I think there really is 100 years of work here, because it's not going to be a simple tweak. Whatever it is, you know, what Wheeler was really seeking, who knows, and maybe who cares. You know, we all outgrow our heroes. But yeah, I you know, in his later papers as he got old, he would really emphasize no continuum. You know, no Tower of Turtles, no continuum, no. He had 4 no's, 3 yeses in one of the later papers. Now, Lucian's theorem is about the structure of state space, and there being continuous reversible transitions or maps on the space. See, from my point of view, I would say that's a derivation of the full set of beliefs or consistent beliefs about a quantum system. So the continuum shows up in that, and that's about a calculus for gambling. Whereas the discontinuum that I think Wheeler was talking about, he was talking about the actual stuff of the world, not the space of quantum states.
Matt. Sorry, guys.
Everywhere, and that included state space.
I think so.
I think we'll discuss this later, maybe, because we're already over time.
Okay, Chris, he said he didn't want any questions, so I'm not going to ask you one.
So you had to
however,
ask me one.
I did want to ask Paul Davies how he felt about being part of the inspiration for Cubism, but he left the room so quickly after the talk that I feel like that answers that question already.
Last question. Try and keep it short.
Yeah, I just want to push a little bit on some of the thoroughgoing subjectivity. So, yeah, we found the Higgs boson. We found its mass. I understand that as measuring a parameter in the dynamical equations of particle physics of the Standard Model. What's the cubist understanding of what, if anything, was discovered when Higgs boson was discovered?
Yeah, I don't have a good answer, but I'll give you a sketch of a try. when we do quantum state tomography. So we have a device that's producing quantum system after quantum system. In the Bayesian way of looking, or in the cubist way of looking at that, there is no unknown quantum state. There is only the quantum state assignment of the agent sitting outside. He sees 1 million quantum systems in front of him or her, and he says they have this exchange symmetry. That's by quantum state. A quantum state, I adopt any quantum state that has the exchange symmetry. And as I perform measurements and I update using Bayes' rule, that quantum state converges to psi thereafter. So it looks like he found something objective. And that, the objective thing is the psi that was actually there. So that would be my sketch of an answer of what's going on with the mass of the Higgs boson. That's not precise enough. Another reason I need another 100 years. But it is a really good question. There's a nice talk by Matt Pusey called "Is Cubism 80% right or 20% right?" I think is the title, and he gives the standard model Lagrangian, and he said it's hard to believe that this is a state, this is anyone's belief, and he shows this horrible looking thing across 2 pages, and I think if anything is a kludge job that is just expressive of, well, what will work? Let me adjust things until I start getting good predictions. It would be that. So that's a bit of the same flavor of an answer.
So it's kind of like we'll give up on and the model is bad and broken and needs to be got rid of.
Yeah. Okay. But more work needs to be done. Yeah, I mean, that is a good question.
Let's thank the speaker again. We have some closing remarks.
Thanks, Chris. Oh, that's your one, isn't it? I can start my talk. Well, thank you, everybody. We have sadly reached the end of this part of our celebrations. We don't entirely have to stop celebrating at least the Oxford bit of the UK's bit of the International Year of Quantum Science and Technology, because we have this evening another music event, a quantum music event with Rakat Biyabdisigan and Bob Kirker. This time you'll actually be able to see Bob playing the quantum guitar. In Merton, we could only hear him. This time he'll be right there on the stage in front of us, so we'll be able to see him too. It's in the Hollywell Music Room, where Handel used to hang out, indeed, so it'll be interesting to have some quantum music played there. It's the oldest purpose-built music auditorium in Europe, so if you've not been before, that might be quite nice. So that's this evening. I have many thanks to give. So first of all, thank you all for coming. It's been great to have you here. So many friends, old friends, good to see you again. So many new friends to meet. It's been great to see conversations developing around the place from people I knew didn't meet one another until this meeting. Keep that up. That's excellent. That's excellent. Can I please thank all of the speakers for their amazing talks? Let's have a final round of applause for all the speakers. Especially so for all of those whom I gave directions to and were good enough to actually do what I asked. So thanks to those people in particular. We also have to thank Lorna, who's done such an amazing job in helping get all this to work. Thank you, Lorna. And of course, we need to thank JTF as well, John Templeton Foundation, for their wonderful sponsoring of this conference. We appreciate it so much. Thank you. So we're in the T.S. Eliot Lecture Theatre. Eliot was in fact a student at Merton in 1914. He was a philosophy student at Merton in 1914. He came to work with F.H. Bradley, who was the absolute idealist. Bradley, though, was a bit of a recluse, so I don't think Eliot ever got to meet him. So that kind of didn't work out. And it wasn't too long afterwards that I think, he left the field. I don't know really what happened to him afterwards, but I gather there was some kind of literary career or something. So here's a closing quote that seems appropriate for our place and our time and the discussions that we've had. So this is from Four Quartets, Little Gidding. I spelt his name wrong here, so it should be a single T, of course, in Eliot. We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time. The place is quantum theory. Thank you all.
I could just have your attention for a very quick moment. I will not keep you long. I noticed, by the way, that many of you were dressed very warmly, as our last speaker was. I was just the other day, I came across an article in the news about cryogenic prolongation of life or death or something, and I can assure you that the organizer of this conference was not indulging in an experiment of cryogenic longevity. This was the tiniest flaw in what was an absolutely marvelous conference. To do something like this, to create a conference of this scope, of such quality of speakers, requires a great organizational effort. And the main organizer is standing in front of us, and I would like to ask you to express your thanks and appreciation for his work.
Thank you very much. Thank you, Harvey.
Thank you. Thank you very much.
Thank you. Very nice to meet you.